Hello everyone. I hope that the trailer gave you a good glimpse of what all we will be covering, how we will be covering, and most importantly, in what depth we will be covering. The aim of this course is to make you a Solidity ninja, and it is my personal belief that by the end of this course, you will be very much confident in this skill. This course is divided into two parts. In the first part, we will be learning about the syntax of the Solidity language via its official documentation. Now, why documentation? Well, probably just like you, when I started learning about Solidity, I went through various different opinions and therefore saw the recommendation of different courses, game, etc. But it was the Solidity documentation which I found to be most fulfilling, and for good reasons. Firstly, Solidity itself is a very fast evolving language. In the duration of making this course alone, I saw 2 versions upgrade, and the documentation is the only place we have which is most up to date. Secondly, as we all know, it is a very serious profession as the stakes are very high. Therefore, you must have a clear understanding of the implications of your code, and the documentation provides these very technicalities. At the same time, it is very brief, so don't think of it as very long or never ending. In fact, if I show you, most of our time when learning about Solidity will go in these 3 sections: the type section, expressions and control structure section, and this contract section. Of course, before I jump into Solidity, we will be covering something known as Ethereum Virtual Machine, which I see to be important to have understanding of it, to have a better understanding of Solidity. Thirdly, as it is open source, it has received various corrections by numerous contributors. I myself has been part of that. So these are the reasons why we will be going via documentation. And what is my role in that? My role will be to provide these information in an orderly manner and also which is easy to understand. You see, when I started this documentation, various things were not clear to me, and after going through different applications etc., it finally started making sense to me. And this understanding is what I want to deliver in this course. We will understand these concepts by various different examples that I'll show you. Also, the documentation can serve as a consolidated notes. You can use a highlighting plugin like I'm using Viva here, which you can use to do your highlights. So these can therefore serve as your highlighted notes. But in case you are using that, make sure that you are not on the latest version. Like this, if I click, then this changes into latest, and in case any updates happen to the page, which does happen, your highlights may get lost. So you can use something like a fixed version like I have done here. Also, what are these versions? This is something which I explain in the course. I take this course from the very basics. So in case you haven't done any programming before, even then it is completely fine. And in the next part of this course, we will be going through this site, damnvulnerabledefi.xyz. We will solve the first 10 challenges here. In total there are 13. We will solve the first 10. And what is the motive behind solving these challenges? It is to introduce you through to various different smart contracts used in practice. You see, alone this documentation knowledge is not enough. In practice, there is ERC20, ERC721, and various different utility contracts which are very helpful when writing smart contracts. So while going through these 10 challenges, we will see numerous, really numerous different smart contracts pre-written contracts to be used, which are industry standard. We'll also be looking at workings of Uniswap V1 and V2. When I started doing these challenges, the very first challenge had ERC20, flash loan, reentrancy, and other stuff, which at that time I was not aware, so it appeared very overwhelming. But all this will become very clear. So that is the purpose behind these 10 challenges. Also, we will learn in good detail about ethers and Hardhat. So it's not just a Solidity course, Hardhat part will also be done. And why I'm not covering this 11th challenge, 12th challenge, and this 13th challenge just recently came, I myself have to give a look to this. So 11, 12 we are not covering. Reason being, it's not that I should give you the solution. What I want is that you should have enough experience that you yourself are able to come at solution. And if we go over this 11th problem and this 12th challenge, then it will make this course very overwhelming. And as you will yourself have to go through various different contracts introduced in this 11th challenge. If you want to do it, then of course I will have a video for this challenge 11th and 12th separately after this course. You can watch that, but it won't be part of this course. Lastly, what are the prerequisites of this course? For the second part of this course, since we will be working with JavaScript, knowledge of JavaScript can help. But at the same time, every line of JavaScript which we will write, I will explain the semantics of it. So as such, there is no need to study it beforehand. But in case you want to study, I have a recommendation of a course which I will mention in the repository associated with this video. This course has an associated repository in which I share all the different links which we have gone through in a particular section. Also, any potential corrections that there might be. And also, as a disclaimer, there might be mistakes in this course, and in case there is any, I will correct them as soon as I come to know about it and will mention it in that repository. But what I'm trying to give you is the best of my understanding, and as such, I don't think there is any issue. The link of the repository I will mention in the description of this video. Also, I would like to mention that this Hardhat part, we don't just start it when covering the second part, the damn vulnerable DeFi. Actually, when covering this Solidity, there is something known as events. So when discussing events, I use Hardhat. So Hardhat is introduced there. But events is the only part when covering Solidity that I had to use Hardhat. Otherwise, for everything else, we are not using it. So that is something which I wanted to mention. Also, since it is a very big course, I have provided chapters below the video which you can use to navigate to a particular section of your interest. So with this, let's begin this course. Now this is an unplanned section. It just so happened that YouTube isn't allowing me to upload a video which is more than 12 hours long. So I have split this whole course, which is around 19 hours, into two parts. These two parts have nothing to do with those two parts I explained before, and the link of the other part will be in the description of this video. Let us now talk about EVM. EVM, which stands for Ethereum Virtual Machine. Now, just like how different applications run on your same computer, in a similar manner, different smart contracts run on this EVM. But there is one thing that just like how you can run Linux operating system inside your Windows operating system using something like VirtualBox, in a similar manner, we simulate this machine inside our current operating system. So it is virtual in that sense. A related thing which I want to talk about first. Usually when we write the program, we write it in something called as high level language, which gets compiled down to something known as low level language. I'll explain this further. Consider a function square, which will basically square the number. It will take an input integer. The set of integers I'm denoting by this symbol z, and the name of the input I'm calling it x. So this square function will take an integer and output will be a non-negative integer, basically a set of positive integers including 0. So given the input x, we have to simply output x square. Now let me show you how a potential high level program to implement this function may look like. Inside the program, we can have a keyword function to tell that we are going to write a function, then the name of the function, then the name of the input and the type of the input, then the return statement to signify that we are going to return this value. This is how a potential high level program will look like. Now let me show you the corresponding low level program. Basically, this low level program, I have taken it considering the architecture of this RISC-V or MIPS. Basically, they are quite similar. Also, this low level program that we have written is said to be assembly code. Let me first explain this code, then I'll explain a bit further about this architecture. Then here we have a square label. Inside this, how we reach this square label, let me first tell. In the assembly program, there will be in this program there will be many instructions. One of the instruction will be this: jump and link to this square function. Basically what it will do, our program will start from here, keep on running. As soon as it encountered this line, it will jump to this square label and then execute its instructions. And in the end, what this line is doing, it will jump to the next instruction following this. After we have computed this square function, this last instruction here is telling to jump back to the following line of this, the line which called this square function. Inside this, when we call this square function, the input parameter is in register A0. What we are doing here, we are moving the value inside A0 to the temporary register T0. It is called temporary, this T registers. I'll explain a bit about that more later. Then what this line is doing, it is basically storing in A0 the value T0 into T0, and this will serve as our return value. The return value will be stored in A0 register, just like how input value was stored in this register. And then we are going to jump, and this will basically hold the return address. to where we have to go to the caller. And then the caller can use the value which we stored in A0 to get the answer. Before calling this function, caller would have put in A0 the value which he or she wanted the square of. Now basically in this architecture, RISC-V or MIPS, they are both very famous. There are basically set of registers. One is this argument registers, other is this temporary registers. I'm using this word, registers. So keep that in mind. So this is how this architecture program may look like. We call it, let me first finish this word. We call it the assembly program. This is how a potential low level program may look like. But as you can see, this is very comfortable for us to write. But this is how machine wants to read the program. So this is where compiler helps us. We write in a high level program known as Solidity, which gets compiled down to a low level language known as EVM bytecode, which is what is run in the EVM. EVM does not run this Solidity file. It does not need this Solidity file. It needs the bytecode to run. Now you might be a bit curious to see how this square function actually looks like in Solidity. So let me show you that. Yeah, so this is how the function will look. These two words are of no interest currently, so you may currently just ignore these two words. They are not relevant for our context. So this function keyword, name of the function, and then this type of the input variable which we are calling as x, then we are saying that this will return an unsigned integer. This is something which I will explain later, and then I'm returning the value. Also, let me show you the corresponding bytecode for this. I wrote a smart contract containing only this single function square. I have its bytecode, and now I'm decompiling it, basically making it look a bit easier to read. So this is how it looked, this bytecode, and it's a pretty big just like we have those instructions. I mean, the instruction part is this part, and this part is not of relevance. Basically the bytecode was this for the compiled contract, which is actually, if I make it a bit more readable, focus only on this right part, this mstore, call value, this. Basically 6080, 6040, 60 is signifying this push 1, and 80 is signifying this hex value. It's a hexadecimal value. We will see that later. So this is how the bytecode will look like. It's a pretty big, and now I think you can appreciate why we write in high level program. One thing more, here I wrote this line, could have been removed. What I mean by that is we are moving this A0 value to register T0, and then we are putting in A0 this value T0 into T0. We could have as well done A0 being put the value A0 into A0. There was as such no need to introduce this intermediary register, and that is right, there is no need. But usually compiler is not that smart, and it will it depends upon the writer of the compiler, of course. Usually you may transfer all the input arguments into a temporary registers. Let us now discuss further about EVM. Now, just like how your traditional computer has various different components, like your computer might have RAM. In computer science terms, we usually call it memory, simply memory. Then it might have storage. You hear 256 GB SSD, etc. So storage, RAM, you hear 8 GB RAM, 16 GB RAM, like that. Then you have your CPU, which is like brain. And then various other things. Similarly, EVM has also certain components inside it, like memory, storage. We will explain that further. A bit about these two that I want to say. Usually, like what you see in your computer is basically inside memory. All this, the operating system, all the applications which you are running, and such things, they are basically fetched from memory. And there are things like if the memory runs out, then some storage is also used. But the main purpose of storage was that this process which the OS has to handle to show you various different applications which you are running, some old photo that you might have clicked need not be part of that process. It is not going to be accessed again and again, in the sense when you access it, then it comes to memory and you are being displayed that information. But as such, the information which is need not be seen now is stored in storage, which is persistent. This part is persistent. And this memory, as soon as we reboot our computer, we see that memory is cleared. Again, the previous context is not there. So let us see these different parts of EVM one by one. Let me first look at storage. How storage is there inside EVM? First of all, storage is persistent. Meaning, let me go through the documentation of Solidity. We are in this section, Introduction to Smart Contracts. Which is basically the first section when you visit the documentation. Let's see what they has to say about storage first. Each account has a data area called storage. What does this each account means is what I will explain later, which is persistent between function calls and transactions. Basically, you just understand it to be persistent. Once we will, just like how your normal storage is, the normal drives which you plug in your system, just how the data there is persistent, in a similar way, this data is also persistent. When we will be writing Solidity code, then using these sometimes storage, sometimes memory, etc., things will become more clear. Storage is a key value store that maps 256-bit words to 256-bit words. Now, let me explain this to you. Firstly, this byte. 1 byte is 8 bits. This should be kept in mind. And what are these bits? Now this is, I'm going too basic, but I think I should go this much basic. So if I were to tell about bits, basically if I denote bit by b, then each bit is either 0 or 1. And if I make a sequence of these bits, suppose like this, suppose let me write this sequence like this: b1, b2, b3, b4, and so on, bn. Then each of this bi is either 0 or 1. So when I say this word byte, what I mean, a sequence of 8 bits. So an example could be this: 0, 1, 2, 8. So this is a sequence of 8 bits. Possible how a byte may look. Now, a byte can, what could be the possible number of bytes, possible values of bytes, if I ask, since in each of these 8 positions we can have 2 bits, either 0 or 1. So 2 possible choice here, 2 possible choice here, so on. So in total, to the power 8 choices, which is, I believe, 128. To the power 5 is 32. To the power 6 is 64. Okay, yeah, this is 256. I mean, obviously it was 256 because of everywhere we see. Fine. So usually when we say in a word, this term is there, word. When we say word, it depends upon the architecture. What does this mean? Usually word means, in majority of the architectures, 4 bytes. As you can see, 4 bytes would be how many bits? Would be 4 into 8, which is equals to 32 bits. I just said majority, not majority, but like in common terms, usually word is meant 4 bytes. But in case of EVM, word means 32 bytes. So whenever you see word in the context of EVM, that would mean 32 bytes. Basically, like if I see this link, in computing, a word is a natural unit of data used by a particular processor design. In our case, it will be EVM. Here, these 32 bytes will be equal to 32 into 8 bits. Therefore, to the power 5, as 32 is to the power 5 and 8 is to the power 3, so to the power 5 into to the power 3 bits. So in total, to the power 8 bits. And as we just saw, to the power 8 is 256. So 256 bits. So this is one word. This is one word. I mean, the size is of one word. So in case of storage for EVM, it is actually a key value pair. Storage for EVM is a key value pair for a particular key. Suppose I give a key which is a sequence of 256 bits. If I give a sequence of 256 bits to storage, suppose I query the storage that for this key, which is a sequence of 256 bits, tell me the value. So that is how storage is there. Now if I ask you what is the possible number of keys inside this storage, let me also tell about, you know, the size of this one word. Like when we say kb, you must have heard, kilobytes. This means, I mean, we call it like 1000 bytes. Actually it is to the power 10 bytes. Also, this is also I wanted to tell, basically, if you want to find the order of the large binary number, suppose you want to find the order of this number to the power 256. One way you can go about, basically the intuitive order, what I mean, one way you can go about is just remember that to the power 10 is roughly 10 the power 3. So if I want to compute to the power 256, that will be to the power 256 would be roughly 10 the power 3 by 10 into 256. By the same logic, which will come out to be 10 the power 3 into 25.6, which is roughly 10 the power 50, 75, 76.8, or you can say roughly 10 the power 77. And the interesting part is this is a very large number. If I tell you there are roughly 10 the power 78 atoms in the whole observable universe, I mean, this is of course there, it need not be true in this sense, but yeah, so this is a very big number. And if we compare it to, like, in terabytes, like how big it is. So let me tell you, like, what is 1 terabyte. 1 terabyte is to the power 10 gigabyte, which is to the power 20 megabyte, which is to the power 30 kilobyte, which is to the power 40 bytes. So where is to the power 40 and where is to the power, wait a second, I said to the power 40 bytes, so this will be to the power 43 bits, because 1 byte is 8 bits and 8 means to the power 3. So to the power 40 into to the power 3 is to the power 43 bits. So where is to the power 43 and where is to the power 256? So storage is pretty huge. We need not worry about the storage in that sense. We have lots of storage available in EVM, but of course, I mean, we need to use it whole. There is also some cost involved, as I will cover. So yeah, so number of, since oh, by the way, since each key is of is a sequence of 256 bits, so that means possible keys, if I tell you the number of possible keys is to the power 256 by symbol combinatorics logic. And since each key can hold one word, the size of the storage is to the power 256 words. And in terms of bits, it is 256 into to the power 256. The first 256 is for the size of one word, which is 256 bits. So that 256 into possible number of keys, which is to the power 256. So here on the whiteboard, I have done a mistake. The first thing which I have written is correct, that we have to the power 256 words, but the bit part I have written is as wrong. It is not to the power 256 into to the power 256, but to the power 256 into 256. Also, storage is very costly I mean, when I say very costly, I mean comparatively. Like we have other things which I will shortly cover, like memory, as we also have memory, and the storage compared to memory is very costly in the sense, suppose you have a variable like our square thing, we have an input integer, right? So in case inside the smart contract we have our variable stored in storage, then to access it the cost is very high. Like if I show you, there is this site known as evm.codes. Inside, if I go to its home page and if I look at this instruction sload, here it is, you can see the gas cost is 100. Now what is this gas is something I haven't talked about, but just understand that the larger it is, the larger cost it is for us. So the gas cost is 100, and whereas loading from memory the gas cost is 3. You can see the difference. But there is one more thing about memory, which is memory expansion. There is a cost involved in that. I will cover that shortly. Now for this sload, cost is 100. How do we access from storage? We pass in the key, and for that key it will give me the value. And how do I store in storage? I will, of course, first parameter would be key and second parameter would be value. Like I will pass in a key and second would be the value. Now let me also show you what does the documentation have to say about it, about storage. So we'll start from here. We have done the previous part. It is not possible to enumerate storage from within a contract. Now what does this mean? Basically, as we looked at our storage is a, you give me a key and you get a value. If you want to load from storage, you give me the key and I will give you the value. Suppose, and you know, and what is the address here? Suppose there is this key 0 0 0, the last one is only 1 and the all other are 0. There is this key, and then there is the second key where all are 0, and then this is also 0, only this is 1 and all other are 0. Basically I'm talking about binary number. Let me just tell you a bit about binary number first. Since that app is a bit jittery, so I'll tell about binary number here. So suppose basically when we look at decimal number, suppose I write this number 1 2 3 4, then you understand the value is 1234. It can also be written like this: 4 into 10 the power 3. Wait, sorry. 1 into 10 the power 3 plus 2 into 10 the power 2 plus 3 into 10 the power 1 plus 4 into 10 the power 0. 10 the power 0 is 1, so 10 into 1 is 4. 4 into 1 is 4. So this is 4, this is 30, this is 200, and this is 1000. So this number 1234 can be written like this in case of decimal number. But in case of binary number, suppose we have this number 1001. Then just like how this position was 10 the power 0 and this was 10 the power 1, this was 10 the power 2, this was 10 the power 3. Similarly, this is 2 the power 0, 2 the power 1, 2 the power 2, 2 the power 3. So this number is 1 into 2 the power 3 plus 0 into 2 the power 2 plus 0 into 2 to the power 1. Sorry. Yeah, right. It's right. Plus 1 into 2 to the power 0. So this is 8 plus 0 plus 0 plus 2. This is 10. Here I have done a slight mistake. It is actually 8 plus 0 plus 0 plus 1. We are doing 1 into 2 to the power 0, which is 1 into 1. So it is 1. So the corresponding decimal number is 9, not 10. If I write this number 0, 0, 0, 0, this is equal to 0 in decimal, and 0, 0, 0, 1 is equal to 1 in decimal, and 0, 0, 1, 0 is equal to 2 in decimal, because 1 into 2 to the power 1 is 2, and 0, 0, 1, 1 into is equals to 3. You can see that, and so on. So when I'm writing these two subsequent keys, you can see this one is of value 1 in basically we should start from 0, so just excuse me a bit. As such, the first key should be 0. So 0, 0, 0, 0, and then 1, 0, 0, 0, 0, and then 0, 1, 0, 0, like this. Now here, suppose I am declaring a variable in my smart contract which is to be stored in storage. The very first variable will go in this first slot, that is for the key 0, corresponding to key 0. It will be stored in that word. Now suppose my very first variable was of 128-bit size. The size was 128 bits, and my next variable is also of 128 bits. Then instead of having individual keys for them, for the very first key, the key which is 0, I mean the all bits are 0, they both will be stored in that same value. So two variables got stored in a single word. Since one word is 256 bits, my both the variable size was 128, and 128 plus 128 is 256. So both were able to accommodate in my single value, in my single word. So it is not just that if I give a key, I get a variable. I can give a key and get the whole word slot, that value, but the individual variables inside that value, that whole word, is something the additional steps which the compiler performs. Multiple variables can share the same key. Also, Solidity in itself does not maintain all possible variable keys. For instance, if I were to ask in an easy way to the Solidity, like for this contract, enumerate all possible key locations which are variables are stored in. That is not possible in our high level languages. In this high level language, I mean, the way storage is usually that the very first key will be occupied, then once it is occupied, the next key which is having the decimal value 1, and then the second, I mean the third key having the decimal value 2, so on, the values will keep on getting filled. But if we have some complex type, we will see some complex types. In their case, their elements, I mean, I can have a big set containing multiple elements. This might not be that clear to you as of now, but once we will cover the possible types in Solidity, then it will become clear. Basically, for a big types, their keys are also slightly complex. It is not just linear. Their key location is not just the previous variable's key plus 1, but they are stored in a separate key location. It is not convenient for us to study that at this point, since it will involve multiple terms which we haven't covered. But I just want you to know that not all keys are like this. That is the linear order. Some key locations are obtained in a slightly complex manner. And all this heavy work the compiler is doing for us. When writing the Solidity program, I don't say that in this key put value or in that key put value. I just declare my variables and I play with my variables. The compiler, the Solidity compiler job is includes to specify the appropriate key locations for the variables. But at the same time, I wonder whether mentioning this now might complicate things. But I just want you to also know that this low level assembly program that the compiler writes, that the compiler compiles our high level language to, in Solidity itself, it is possible that we write this low level program. In Solidity also, in our smart contract itself, we can write a low level program corresponding to that assembly language only. I mean, it is not exactly that assembly language, but very, very close to it. And in that program, I mean, in that inline assembly code, we call it inline assembly code, which is written in Solidity itself. There I can mention that load particular key from storage or store at a particular key this word. So that is possible. But if we talk about that whether Solidity maintains some data structure, something like where I can query that give me all possible keys where you are storing the values, where I can query that, that is not possible. I hope you are able to understand this. If not now, when we will be writing Solidity programs, etc., then it will become very much clear. Also, by default, all these values, that is, inside storage, the word corresponding to every key is 0. That is, all the 256 bits are 0. So, in case at a particular key, the compiler is storing the value, the 0 value itself, then nowhere is the Solidity maintaining that whether that 0 value is the default 0 value or the user input 0 value. Basically, by looking at the storage, suppose if you are looking at the storage and at a particular key you see the value 0, you do not know that whether it is the default value 0 or whether a user has put the value 0 there. Slightly additional info which I want to give, not relevant to our discussion as of now, but just that these keys which you are seeing, say the very first key having the binary representation all zeros, suppose it was at address 1, and the second key which we are having the decimal representation is 1 and binary representation is as shown to you. Suppose that value corresponding location was at address 2, then it need not be the case that address 2 is equals to address 1 plus 1. I mean, for the keys, we can see that key having decimal representation 1 is equals to the previous key, which is 0 plus 1. That was fine. But these addresses where they are stored at, they need not be linear because this storage is an emulated environment. So I just don't want you to confuse keys with addresses here. Also, I realize that you might not be clear about what I mean by this word address. Basically, just like you have the address of your home, right? Similarly, in memory, every location is having a address. And when I'm saying memory, I just don't mean Solidity's memory structure, which we will cover shortly. I mean memory in the larger sense. That is, wherever I can put data, I am calling that place as memory. So that place may either be temporary or persistent, but the point where I have put my data will have an address. So that is the address I'm talking about here. So the two values, the two subsequent values although their keys might be subsequent, but their addresses need not be. It is comparatively costly to read and even more to initialize and modify storage because there are some dynamic costs involved in initialization. And usually read operations are cheaper than putting the value, then updating the value. So due to costly nature of these operations, you should minimize what you store in storage to what you actually need in storage. Store data like derived calculations etc outside of the contract. Basically use memory or constant variables. We will cover constant variable later. A contract can neither read nor write to any storage apart from its own. This point, keep that in mind when we will be covering functions about and there is something known as reference types. In that, this will be important, so keep this in mind. So that's pretty much it about storage. So let me now talk about gas. You see the the code which I showed you for this square function, the bytecode, we saw it consisting of all these different instructions: push one this, mstore, call value, and so on. We saw this bytecode. Now each of these instruction is incurring a cost in gas. If we look at the documentation about this gas, upon creation, each transaction is charged with a certain amount of gas whose purpose is to limit the amount of work that is needed to execute the transaction and to pay for this execution at the same time. So by the design of Ethereum, when the transaction is ran in the EVM, each operation is incurring a gas cost. And since we are paying for that gas, we cannot do this infinitely because then it will take infinite cost. So hence it is limited. Also, Ethereum has a limitation about the maximum gas which a transaction can consume, which is limited by the gas a particular block can have at most. So in Ethereum, a particular block can take at most say 15 million gas. Then the transaction which is inside that block cannot consume more than that amount. So gas is limited by that way also. While the EVM executes the transaction, the gas is gradually depleted according to specific rules. Now, gas is just gas in the sense when I showed you all these instructions and the gas cost we saw for the S load and S store. Here they are. So this is just gas. Don't associate it with dollar terms or with Ethereum. It is just gas. So when we look at all the instructions that we have in our bytecode, all these instructions that we have and the gas required, let me denote it by G. Then according to the conditions of the network, we will set the gas price accordingly. Suppose the price is, let me just say in terms of dollar terms now, let's say per gas price is dollar 0.0001. So we have to pay dollar 0.00, I mean, let's call it gas price, denoting by P. So we will have to pay PG dollars. But in case of Ethereum network, we actually pay in Ethereum unit, and this is something which you can keep in mind also. I'll show you the conversions. Here is the table denoting the different conversions. The base one is called WEI, and 1 ether is 10 the power 18 WEI, we call it. So 1 ether is equals to 10 the power 18 V. Similarly, I would say this is equals to 10 the power 9 GUI, as this GUI you can call it gigaway is equals to 10 the power 9 way. So usually we pay for the gas in ether terms in these units. I mean usual unit, or you can say it is denoted in this, the gas price. So for the example, if the required gas was G, then it could be the case that per gas, as I told you, gas is just gas, per gas, suppose I am going to pay 20 GUI. So in total, I will be paying 20 times G GUI. This is the amount. You can write it in terms of ether also by converting accordingly. This is the amount which I must pay when I am sending my transaction to this EVM. Like, let me show you the documentation. Yeah. The gas price is a value set by the creator of the transaction who has to pay gas price into gas upfront from the sending account. If some gas is left after the execution, it is refunded to the creator in the same way. If the gas is used up at any point, it will be negative. An out of gas exception is triggered, which reverts all modifications made to the state in the current call frame. About this exception, we will discuss it later. This also call frame, something which you might not get sense about currently. Just understand that an error is raised. Also, for Ethereum, there is this concept of atomicity. Like, each transaction is an atomic operation. It can't be divided or interrupted. That is, either transaction is completely done or it is not done at all. So when we have a transaction, in that transaction it might be modifying the storage elements, etc. So either all get modified, I mean the transaction is changing the state of the Ethereum network, or the transaction doesn't do anything. Continuing with different parts of EVM, we have looked at storage and gas. Also, the Solidity documentation has a overview which I would like to share. The Ethereum Virtual Machine, or EVM, is the runtime environment for smart contracts in Ethereum. It is not only sandboxed but actually completely isolated, which means that code running inside the EVM has no access to network, file system, or other processes of the host system. Smart contracts even have limited access to other smart contracts. This is, need not pay much attention. Just that, like the possible ways in which you can interact with the other smart contract is by calling the functions which the other smart contract has allowed you to call. So we will see such interactions, and besides that, I see no other way to interact with those smart contracts. So they are limited in that sense. Coming to accounts, there are two kinds of accounts in Ethereum which share the same address space. Now, in case you have received Ethereum or sent someone some token on Ethereum network, you would have seen that hexadecimal address, that 0x something. So that is the Ethereum address, and all addresses share the same address space. So it won't be possible to have the single address being possessed by two different people or two different entities. So these two types of accounts are external accounts that are controlled by public private key pairs, that is humans. In case you have used some wallet like MetaMask, so these address which you normally use is called external account, or it is also simply called EOA, externally owned account. And the other type of account is contract accounts, which are controlled by the code stored together with the account. The EOA account is something which you control. You sign the transactions to send. So it is controlled by you. But the contract account is controlled by the code. So it is following the rule of code. Since we will deploy contract accounts, so that time it will become more clear. The address of the external account is determined from the public key, while the address of contract is determined at the time of the contract is created. So external account, in case you have experience of receiving or sending Ethereum, you provide the address to send to. So that is the address. In case you have learned about this cryptography, you may know that the public key can be derived from private key. Usually, we talk of public address. So public address is sometimes, synonymously used for public key, but they are quite different. So the address of external account is determined from that public key, while the address of contract is determined at the time the contract is created. It is derived from the creator address, the one who is deploying the code, and the number of transactions sent from that address. If you look at your MetaMask account or any wallet which you are using, when you send the transaction, it will tell you like transaction number this confirmed, transaction number that. So that is called nonce, and it starts from 0. If you have your very first transaction will have nonce 0, your second transaction will have nonce 1, and so on. So from this nonce it is calculated along with the deployer address. So it will be unique. Once I have deployed smart contract, my nonce has increased. If I am going to deploy some other contract, even though my deployer address is same, but nonce is different, so I will get a different address. Regardless of whether or not the account stores code, the two types are treated equally by the EVM. EVM does not differentiate, just that the allocated space is there. There is a space to hold code. In case of EOA, it won't be there, but in case of contract code accounts, it might be there. Every account has a persistent key value store mapping 256-bit words to 256-bit words called storage, which I have explained to you. Furthermore, every account has a balance in ether, in V to be exact, and I have told you 1 ether is 10 to the power 18 V. This thing is signifying 10 to the power 18, which can be modified by sending transactions that include ether. That's obvious. This is very important transactions, and they have beautifully summarized it here. A transaction is a message that is sent from one account to another account. So in case you are wondering what a transaction is, this is the transaction. Understanding further, you will become more clear, which might be the same or empty. It can include binary data, which is called payload and ether. Regarding this, that the another account, you may send a transaction to yourself to the same account, or it might even be empty, which is explained below. We will shortly see that, and this is also will become more clear. This is like additional data, and this is like value. We will see that. If the target account contains code, see, I told you we have two types of account. One is like humans account, which is controlled by humans, externally owned account, and the other is contract account. Contract account is containing the contract, so it will have different functions, and I told you to the way you interact with them is by calling the functions in them. So if you are calling the function, you may need to pass an input data, so that will be treated with payload will be used to give the input data. So if the target account contains code, that code is executed and the payload is provided as input data. Payload, since the contract has many functions, payload will have the selector for the function you want to execute. We will see that. We will actually run through a EVM bytecode, the assembly code, to explain how the function is selected, the one which you want to call. We will see that. If the target account is not set, that is, the transaction does not have a recipient or the recipient is set to null, that means the transaction creates a new contract. So in case the recipient is not set, that means this transaction is used to create a new contract, deploy a new contract. So as already mentioned, the address of that contract, we have seen how it is derived, is not zero address but an address derived from the sender and its number of transactions sent, the nonce. The payload of such a contract creation transaction is taken to be the EVM bytecode and executed. So the payload which you are providing in this transaction is actually your EVM bytecode, and that now is getting executed. This is explained next. The output data of this execution is permanently stored as the code of the contract. See, I will now explain this further. But first, let's see what they have written. This means that in order to create a contract, you do not send the actual code of the contract, but in fact code that returns that code when executed. Basically, when you write your smart contract, like if I tell you, you will have many things in your smart contract. There is one special thing. It's called as constructor. This is your Solidity file, and inside your Solidity file you will have different functions, like let me say function A, it's something, function B. You will have other things also, some variables which you have declared and other things which we will see, but there is one thing special. It is called as constructor. Constructor will further initialize the variables which you have. Constructor might query the other contracts to get some value, like it might query an oracle to set a value, like that. So constructor will be used to set some specific things inside it, and once those things are set, that is your final code, bytecode, which is deployed. Actually, when we talk of bytecode, you might see it also. We have this initial bytecode, and then there is which we are sending, and what the finally gets stored in the blockchain is called as deployed. I just wrote it a bit incorrectly. It's called as deployed bytecode. So that is what we see, and that is what was meant. One thing further which they have written, While a contract is being created, its code is still empty. Because of that, you should not call back into the contract under construction until its constructor has finished executing. What this means, better to understand it from example. Inside this constructor code which I have, I should not be calling these functions like uh, precisely, if I were to say, in the sense the way this constructor might query external contracts, it should not in the same way query back to this contract externally, because these functions have not yet been, this code is not yet deployed inside the EVM. I will explain this further when we will be running through actual Solidity files. Like in Solidity, there are two ways you can call the function. Basically two ways. One is internally, one is externally. If you are calling this function internally inside constructor, that will be fine, but you cannot call it externally like how you will call some external contracts function. That you cannot do inside constructor. Don't worry if you didn't understood this point. When we will be writing these smart contracts, since I will take you through that example, so through the example showing this, in that it will become very clear. Covering transactions, one thing which I would like to add is, look at this slide. Transactions cannot be overlapped. So it is not possible that you have some part of the transaction going and within that EVM is running the second transaction. No, that is not possible. One transaction at a time. So transaction must be executed sequentially. When the block is formed, all these transactions are ordered sequentially like this, which gets added to the blockchain. Also, an illustration about these two types of account. One is externally owned account and contract account. So you can see the basic things which will be present in their account state, like nonce, balance, storage hash, code hash. In case of EOA, they are not set, but in case of contract account, they are set, pointing to the actual storage, of hash of the actual storage and code hash of the actual code. Here, keep this diagram in mind, because you will see that we can directly get the code hash of a address from EVM, which is a bit cheaper than getting the code and computing its hash. It's because code hash is separately also present, we can directly get that. And this below information already covered that EO is controlled by private key, EO cannot contain EVM code, contract contains EVM code and is controlled by that. Continuing further about EVM, we covered overview, accounts, transactions. We also covered gas. Inside this, EVM basically has three areas where it can store data: storage, memory, and the stack. There is also call data, but actually call data is part of the message, as you will see. So not as such inside EVM. We will cover that also soon. So storage we covered. Now let's cover memory. Now the main difference between storage and memory is that memory is linear. Storage, I told you, is a key value pair. You give the key, you store the value in a given key, and you get the value from a given key. Consecutive keys need not have consecutive addresses. As I told you in the example, these keys are consecutive, but their addresses need not be consecutive. So this is not linear, but memory is linear. Let me show its diagram. This is how you can visualize memory. Again, we are in that same slide. So memory is linear and can be addressed at byte level. I told you that all the elements here are linear, having consecutive addresses, and you can address at byte level. Here, when they say that it can be addressed at byte level, basically you can give any byte. You may give this second byte here, and it will load from this second byte in total 32 bytes. For instance, like here, suppose I have my memory and I am saying that I want to do this mload operation. This, if I write mload operation at an offset 1, then for this offset it will read these 32 bytes. As we know, this all is 1 byte long, that is 8 bits. So for any possible offset, I can do this mload. That offset could have been 3, this 2, then these 4 bytes, and so on. So in that sense, it is byte addressable. Also, if you will look at the EVM's implementation, there is, let us not make it further technical, but in the implementation of one particular way, like in this language of Go, there is this implementation of EVM. So there I saw this memory was an array of bytes. This thing array will become clear later. Just understand it was the list of bytes. So that is how they were maintaining internally. And similarly, we have this mstore operation, which could be either 32 bytes or single byte. That is, it is possible that if I do this mstore, say for this index here, I should say mstore8. Basically, there are two possibilities which we are provided with. One is mstore8. Here I can give my offset and the value. The other possibility is simple mstore. mstore offset value. This second mstore will write 32 bytes and this will write single byte. So if I was doing mstore8, say offset was 2 and value was say 8, then at this offset 2, value 8 will be stored. And if I was doing this mstore, this second operation with some value, and suppose my value was, now this value will have a low level binary representation, right? So suppose it is like this 0 1 1 0 1 0 0 0 1, so on, right? Let me compress it like this in the groups of say 8. So 1 2 3 4 5 6 7 8. Let me just check it. 1 2 3 4 5 6 7 8. Yeah. So let me call this as B1. Since we have already used small b for binary, so I'll use capital B here. So let me call this byte as byte 1, and then the next as byte 2, and so on. So this is my lower order byte. And finally my number is this B32, B31, so on, B2, B1. This is how my value looks at the low level. And suppose the offset was 3. If offset was 3, then how this will get stored? It will get stored like this. First will come the byte 32, the higher order byte, then B31, and so on. Also, I think it will help if I give an example here. I will cover hexadecimal numbers in great detail later. This is an hexadecimal number, but I will cover them later. For now, just understand this single character is 4 bits long. So this is 4 bits and this is again 4 bits. This 0x just denotes that we are writing an hexadecimal number. So in total this is 8 bits. So 1 byte and I am saying here that at offset 0 put this byte, and mstore8 is for that instruction. Once we will cover stack also, then this will become clear. Basically here we have this mstore instruction which will take two parameter. One is the offset, at what offset do you want to put your value. So we have this mstore8 also, which will also take the offset and what value you want to put. Fine. So fine, if I run this, at offset 0 I want to put this value ab. So one instruction, this second instruction I am running, then mstore8. Now if I see my memory here, by the way I'm in the playground of this evm.codes website. You can see my memories. This is the first byte of the memory, this is the second byte, third byte, and so on. So you can see my first byte has this ab. Now in my offset 1 I am putting this byte ec. So let me run that. Wait a second. Yeah, okay. So you can see at the offset 1 I have inserted my this byte also, ec. Now what I am doing at last, at the offset 2 I want to insert this byte, but I am using mstore instruction. Now since I am using this mstore instruction, I need to put 32 bytes. Fine. So in reality I have here only given the lower order byte, that capital B1 which I showed you. Only that capital B1 is given here. The rest of the bytes will therefore be 0. From B2 to B32 will be 0. So at offset 2 when I am putting this value, this is B32 which will be 0, then B31 which will be 0, and so on. At the very last the B1 will have this value ff. So let me also show that mstore, and you can see these are 0. And to prove that this is indeed 32 bytes long, I'm going to copy this, and if I go in my editor, paste this, you can see this part here. My editor says that it is a column 1, and if I go in the very end, it is saying column 65. So in total 64 characters are there, and as I told you, each character is half a byte long. So 64 into half, 32. So yes, this is 32 bytes long. So I hope with this mload, mstore, etc. is clear. And since I can give any offset here, all these offsets are available to me. So this is byte addressable. That is, I can give any byte offset. So mstore will be your 32 bytes, mstore8 will be your single byte, mload will load the 32 bytes. All locations in memory are well defined initially as 0, just like storage, all values were 0. In case of memory, all these will be 0 initially. Reading through the Solidity language documentation, the second data area is called memory, of which a contract obtains a freshly cleared instance for each message call. This we will see further when we are learning about Solidity in terms of writing actual Solidity code. But whenever you are calling the external contract, basically when you are calling the function of external contract, so that is run inside the EVM in the sense that a new context is generated. This word, context. Like when you see what is the contract getting when it is running, this is the diagram showing that EVM, which we saw this storage, which is persistent, part of the world state. It is not, when the function stops executing, memory will be cleared, memory will no longer be there, stack, etc. But the world state remains. It is the part of the blockchain. So when we are calling the external function of a contract, so a new context is generated, and this contract will start running that function in here in this context. So all this part here in this rectangle is context limited and will get cleared when that has finished executing, but the storage is what remains. And it is also mentioned here that this part is volatile. Now let us look at this memory expansion. First, let us read what they have written. Memory is expanded by a word when accessing, either reading or writing, a previously untouched memory word, that is any offset within a word. At the time of expansion, the cost in gas must be paid. Memory is more costly the larger it grows. It scales quadratically. If you want to see the exact formula, here is the exact formula in that evm.codes/about website. During an execution, the whole memory is accessible but not for free. When an offset is accessed, as I told you, memory is linear. It starts from the very first the address of the very first slot, and then you move downwards from that. In case you touch a very new address space below, which has not been touched before, so memory has to expand till that point. So when an offset is accessed for the first time, that thing is called as offset. Offset, from the base address. For the first time, either through read or write, it may trigger a memory expansion which will cost gas. A memory expansion may be triggered when the offset used is bigger than any used before. Basically, the word was untouched, word or byte. When that happens, the cost of accessing that higher offset is computed and removed from the total gas available in the current context. So our context, we know gas, as I have covered about gas before. So the total cost for a given memory size is computed as follow. Okay. So the formula goes like this: memory size word is equals to memory byte size plus 31 whole divided by 32. What is this memory byte size? Let us see. They are mentioned here. The memory byte size can be obtained with msize opcode. The bytecode has various opcodes. Basically, it is a sequence of those opcodes, you can say. We saw some of them. One of them is msize. So msize, they have given a bit description about it. The memory is always fully accessible. What this instruction tracks is the highest offset that was accessed in the current execution. Highest offset will basically give us the size. A first read or write, the very first read or write to a bigger offset will trigger a memory expansion, which will cost gas, as we have told before. The size is always a multiple of a word, that is 32 bytes. In the documentation which we saw previously, whenever it has to expand, it will expand by word, not in terms of byte, but in terms of word. So the output will be current memory size in bytes. So in case the highest offset accessed was say 31, then in total I have accessed 32 bytes, right? Because the very first byte has the offset 0. So that is why they have plus 1 here. So 31 plus 1 equals 32. So if my highest offset accessed was 31, in total I have accessed 32 bytes. So going back to our formula, where was it? Here it is. So we will get the current size plus 31 by 32. They have their own logics. Why are they doing it this way? Not of our concern. Memory cost is this square of this memory size word. So basically square of the total size of our memory and divided by 512 plus 3 times this memory size only. So we can see that it is for the very large values of memory size word, this term will dominate, this square term. So in that sense, if you have studied asymptotic notations, what I just said will become clear, that the main growth factor is this. So that is why we say growing quadratically. But one thing also you should remember, When a memory expansion is triggered, however, only the additional chunk of memory has to be paid. The cost of memory expansion for a specific opcode is thus basically you subtract the last memory cost from this. You get the memory cost, but from this you subtract the last time you paid. So basically you have to pay only for the additional chunk. That makes sense. So with this you can see that since the memory grows, the cost grows quadratically. It will make accessing higher offsets more costly and discouraging. So memory is also should be, when writing Solidity code, we should write in very optimal manner. Our design itself should be very optimal. So that's pretty much it about memory. Let's now see stack. Now in case of, I showed you assembly code for the architectures of MIPS and RISC. This MIPS RISC, I showed you how their assembly code looks like. And you can see I talked about these registers. So this architecture has registers and you put value in those registers. But in case of EVM, you don't have registers, you have stack. So I will explain the stack. But basically, I hope you are getting that we have storage for our persistent data. And just like how, the reasons why we have memory in computer, we have memory. And then for the very low level operations to do all these operations, we are having this stack. When we will be running through a example bytecode, then you will see the usage of stack very clearly. But just like how here registers, we see the usage of registers here, in a similar manner we see the usage of stack to pass values to memory, to store values to storage, access a value at a particular key from storage. All those operations are done with the help of stack. Where will the key come from? Basically key will come from the stack when we are accessing a value in storage from that key. So EVM is not a register machine but a stack machine. So all computations are performed on a data area called the stack. It has a maximum size of 1024 elements and contains words of 256 bits. Basically we can say it contains words. So if I were to visualize the stack, you can see it like this. The stack where each is we will see how the stack data structure works. So basically each element is of size 1 word and it can contain maximum 1024 such elements to the power 10, which is. To explain you how the stack data structure looks like, basically what is the stack data structure? Imagine a cup like entity, like a shelf. So in case I insert an element in this, suppose I'm inserting one element, so that element gets pushed like this and the bottommost space is filled, just like imagine a well. Imagine this to be like well. You have pushed one item which now sits at the very bottom naturally. Now if you are throwing in some another item, so it will get above the previous item. Now if I throw in one more, I will have this. So basically I just did 3 operations. First I did this one operation, then I did this second operation, and then I did this third operation. Now suppose I do now pop. What the pop will do, it will take out the topmost element and give it to me. So this will get taken out and I will be given this element. If I do pop once again, this will be taken out and I will get this. Now if I want, I can push back 3. If I write push 3, then it will push this element back. And now if I do push 2, it is going to push this element back. So this is stack. We also call it LIFO, last in first out, or you can call it FILO, first in last out. The first element which we pushed in the stack, when we are going popping, it will be the last one to get popped out. So I think this is pretty simple to understand. And in stack you basically have only these two operations: push, you push some value to the stack, or you pop the topmost element from the stack. So for example, in our stack, if we want to implement square thing, basically to do the square of an input, we can do like this. Assuming our stack is having an input number, for instance say -2, the first operation could be to duplicate this, to duplicate our input, which will see the topmost value of the stack and put that duplicate inside. Basically it will take this -2 out and put two -2s in. The next operation could be this multiplication, this, yeah. So this multiplication will then take these two elements out and store their multiplied result in the stack. So this is one example of how the stack is used. So we saw that in place of registers, we were able to do this operation using stack. So now coming back to the documentation of Solidity language, they have this written: access to the stack is limited to the top end in the following way. It is possible to copy one of the topmost 16 elements to the top of the stack, or swap the topmost element with one of the 16 elements below it. Basically, in the stack which I showed you, stack, when we say the word stack in computer science terms, it has only these two operations, push and pop, and we are following this LIFO order, last in first out. But in case of EVM, they have added one little modification to it, is that in their stack we have all these elements like this. Suppose we are having the elements for the top 16 elements. For the top 16 elements, what they are saying is that either we can copy one of these top 16 element and insert a new element in the stack like this, or we could swap this topmost element with either of these 16 elements. So for instance, these two could be swapped. This is an additional twist which EVM provides. Like here, if we have a look at this swap 16 opcode, they have given a very good example. We have this stack input. Suppose this was the stack input when we were calling this swap 16. Then what this will do, it will swap this A with B. So the stack output will be this B at the very top, all these are ignored, and that A got in the very end. Similarly, if we do this copy, suppose we had this dupe 16. This dupe 16, it will duplicate that 16th element. So suppose this was the stack input, right? Now, when using this dupe 16, this 16th value will be copied at the very top. So that is, this will be the stack output. So I hope with this these two operations are clear. Moving back, all other operations take the topmost two or one or more depending on the operation elements from the stack and push the result onto the stack, just like I showed you in case of duplication and multiplication example. Of course, it is possible to move stack elements to storage or memory in order to get deeper access to the stack. Basically, if you want to access more deeper elements, you can pop these elements and store them in memory so that you can access deeper elements. And once you are able to access deeper elements, you can push back those elements which you popped into the memory or to the storage. You can put them back on stack. I mean, that's very basic thing, nothing to see here. But it is not possible just arbitrary access elements deeper in the stack without first removing the top of the stack. So this is just the basic of stacks. Moving on, instruction set. The instruction set of the EVM is kept minimal in order to avoid incorrect or inconsistent implementations which would cause consensus problems. All instructions operate on basic data type 256-bit words or on slices of memory or other byte arrays. We have seen this before. The usual arithmetic, bit, logical and comparison operators are present. Basically, comparison is like I showed you an arithmetic operation which was multiplication. Similarly, for comparison we have like this: is A greater than B, like greater than, less than. It will take an input A, two elements, like suppose 2 comma 3, and output will be it is either 0 or 1. To denote, 1 will denote that yes, left side is bigger, and 0 otherwise. So like that, this is for comparison. And logic, for this bit, there is, you like, in case you might have seen AND operation, bit arithmetic like shift and or. This is something which I will cover later also, so I'm not going deeper here. Here most likely from logical they mean your and, or, not, such operations, and from bit they will mean shift left, shift right, like that. Conditional and unconditional jumps are possible, like I showed you an example. Just like in our normal assembly language, we have this jump to the square label. This could be conditional, that jump, if this result is true, then jump to the square label. Just like in normal assembly, this is possible. Furthermore, contracts can access relevant properties of the current block, like its number, timestamp. Like blockchain, there is a timestamp thing, so that you can query, get the block's timestamp. That opcode is also there in EVM. So for the complete list of opcodes, they have given a hyperlink which you can see. Moving on, this is another very, very important section. Contracts can call other contracts or send ether to a non-contract account by means of message calls. Basically, when we have our smart contract, it is possible this smart contract, suppose it needs to call a function in some other contract. So that will happen by a message call. I told you that it will have the data called as payload, in which it will tell which function it wants to call and the input parameters of that. So this is happening via message call. Similarly, it is possible that this contract sends some ether to the EOA, externally owned account. Also, it's not that it can send ether only to EOA, it can also send ether to the other contracts also. Moving on, message calls are similar to transactions in that they have a source, a target, data payload, ether, gas, and return data. In fact, every transaction consists of a top level message call, which in turn can create further message calls. Basically, this is one message call we are doing. Similarly, this contract can call other contracts function, or and so on. So all these message calls, once our main thing which we wanted to execute has finished executing, all these message calls were actually part of that single transaction only. Moving on, a contract can decide how much of its remaining gas should be sent with the inner message call and how much it wants to retain. Basically, when the smart contract is calling this external function, at that time it will forward some of its gas. Suppose it is having 8000 gas, then it may forward 5000 to it and have remaining 3000 with itself. That is what they mean by that. If an out of gas exception happens in the inner call or any other exception, suppose this contract gives an exception that gas has run out, or maybe you're doing something wrong here in this contract, then the exception is raised and we go back to our caller. This will be signaled by an error value put on the stack. In this case, only the gas sent together with the call is used up. In Solidity, basically you are having the remaining gas, suppose you forwarded 5000, but not all of it would have gone used, so you will get the remaining back. In Solidity, the calling contract causes a manual exception by default in such situation. So what by default, basically, when the exception, just one second, so that exceptions bubble up the call stack, basically what they mean. So suppose we forwarded 5000 to this gas, this contract, and this also calls some other contracts function, forwarding say 2000 gas. Suppose out of gas exception is reached in this contract, then we will go here to the caller, where the caller will receive the exception that something wrong happened. Here, by default, unless you do something, by default this will also return here to its caller, and this caller will know that something wrong happened. And if we don't do here also anything, then this will also return the exception to our original caller, and we will get the error. Sometimes you might have experienced this also, your transaction doesn't go through and you get this some error, the transaction reverted due to this reason. But it is also possible to catch this error. Suppose this contract, there is something known as try catch in Solidity, with which you can catch the exception, and instead of having it bubble up, you can handle it if you want. So that is what they mean by default and this bubbling up thing. As already said, the called contract, which can be the same as the caller, will receive a freshly cleared instance of memory, as I was previously explaining you. When this smart contract calls a function of other contract, then a new context is generated. I mean, new instance you can imagine for EVM they get, in which they have like new stack, memory, these things. It is also possible to call same contracts function externally. There are two things, calling a function externally and calling a function internally. If we call the function externally, then it's like same as we are calling some other contracts function. and a new context in the new context is generated in that case. However, if we call the function internally, then the context remains the same and we execute that function via simple jump statement. This is something might not be clear yet. I will cover this also later. We will cover this later in detail. So n has access to the call payload, basically the data which contains the input, which will be provided in a separate area called the call data. When we, as I told you that there in the beginning, that there is something known as call data, this payload, when the contract receives the input for the function, then this is an area called as call data. Just a second. And it is very similar to memory, just that it is immutable. I'll cover this a bit more in detail later. So after it has finished execution, it can return data which will be stored at a location in the caller's memory pre-allocated by the caller. All such calls are fully synchronous. Like if I show you here, yeah, just 1 second. Yeah, arguments and return values are passed using memory. Basically, suppose we want to call some other contracts function, the input will first be copied to our memory, and then from memory they will be passed as the payload, which is in the call data of the new context generated. Similarly, the return is passed via memory. Since return is passing something to another contract, it goes via this memory and is getting stored in the caller's memory. And this synchronous part basically means that we are waiting for the operation to get completed. It's not that we are letting it happen and in the meantime we also start something else. No, one operation at a time. Calls are limited to a depth of 1024, irrespective whether you are calling internally or externally. There is this concept of internal call and external call. External call is our simple message call, which is what being talked about here. In that case, the stack, there is one more stack besides the stack which we have already covered. What the stack we covered is also called as expression stack. There is one more stack known as call stack, and that also has the maximum size of 1024 and where each element is one word long. This call stack I will cover up later, and whenever we are calling an external function, this call stack is also will also get incremented, and thus we are limited to this. And in case we were calling the function internally, in that case there won't be a message call, but even then our the stack, the expression stack which we have, at least one slot will get used. So even in that case we are limited to this depth at most. When calling function internally, instead of message call, we simply jump to that label in assembly, you can say, which means that for more complex operations, loops should be preferred over recursive calls. This you might not understand, loops part or recursive part, in case you haven't done programming before. So I'll explain this later when we are doing Solidity coding. Furthermore, only 63rd by 64th of the gas can be at most forwarded in a message call, like here. If this contract had 8000, at most it could have forwarded only 63 by 64 of 8000. Fine. Which causes a depth limit of little less than 1000 in practice due to this forwarding thing. As the gas limit of the entire block is 15 million and we are forwarding at most 63 by 64. So if I were to do this math, suppose we are having 15 million gas and we are forwarding 63 by 64 of it. Suppose we forward it n times, so this should be less than, so that we are not able to do any further calls, 100 at least, because if I show you in the opcode for the call, here yeah, it is taking at least 100 gas. So this should be at least less than 100, so that we are not able to do any call. So if I take logarithmic, this is log 15 plus 6 into log 10 plus n into log 63 by 64 less than 2 into log 10. This and this will somewhat get cancelled, so I have log 15 plus 4 times log 10 less than minus n into log 63 by 64. In case you know about the logarithmic graph, log of 1 is 0. This is less than 1, so this is negative, and we also have negative here, so this entire thing is positive. So if I divide by it, the sign of the equality will not change. So let me divide. I will get log 15 plus 4 into log 10 divided by minus log 63 by 64 n. So this is this for this value of n, we will have this less than 100. So let me compute that value of n. So that value of n comes out to be around 756. So further calls than 756 won't be possible. Also, we can read this little description which I have found in this link. Block size. A final important note is that blocks themselves are bounded in size. Each block has a target size of 15 million gas, but the size of blocks will increase or decrease in accordance with the network demands, up until the block limit of 30 million gas, which is 2 times the target. That is the upper limit. The total amount of gas expended by all transactions in the block must be less than the block gas limit. This is important because it ensures that blocks can't be arbitrarily large. If the blocks could be arbitrarily large, then less performant full nodes would gradually stop being able to keep up with network due to space and speed requirements. I hope with this you are able to get further sense. And even this 15 million gas, 30 million gas, that is now, it might change in future. So yeah, we should be careful of this when we are writing our smart contract. So because of gas itself, irrespective of whether your stack can hold 1000 or 10,000 elements, irrespective of that, because of gas itself, we cannot go beyond this number. Or you can say that even if it's instead of 15 million it was 30 million or whatever, you get the idea. We won't be able to go over 1000. So now we have covered quite much of part of our EVM. We covered this stack, we saw memory, which we saw storage. There are this some gas, how much is the gas available, that is also stored somehow in EVM. Similarly, program counter. Program counter is basically telling which line we are. Like program counter here means we are in this line. After this operation, program counter will be here to execute this line, and so on. You can also get program counter's value. There is an opcode for that. Here is that opcode for the to get the program counter value on our stack. Now regarding call data, the call data region is the data that is sent with a transaction in payload. In case of contract creation, it would be the constructor's code, as I told you. This region is immutable and can be read with instructions. They have these instructions in EVM, these which you can run to get to read it. And as it is immutable, you cannot write it. Now, one thing which I would like to say is, as I told, this EVM is a virtual runtime environment which is simulated via another high level program. So in case of Geth, it is Go language, Go. So this diagram is just illustrating that we have a EVM bytecode which is running on EVM, which is simulated using either Geth or Parity. There are different systems which they are simulating, and this high level program is running on its own hardware. And if you want to look like, you can see the Geth code, how it looks. You can go through these slides or their GitHub repo in case you are interested in that. Now I would like to cover this page of the documentation, layout of source files. Here, this part, language of layout of Solidity source file. So let's see it through an example. First of all, when we are writing our contract, we should decide firstly in the name of the contract, what are we going to name that contract. Here in this example, my contract name will be layout. So my file name should also match with my contract name. Basically, if I show you this style guide, here in this section, contract and library names, this is style guide. We are here, this part, style guide, which is an additional material. So contracts and libraries should be named using cap word style. First, let me create my file here. So I'm gonna just create my file. And I'm going to open it. Now I'm going to do this contract layout. So I have now, when we are write the contract, we use this keyword, this contract keyword, to say that the following is the contract, which is inside this curly braces. For this reason, Solidity is also said to belong to curly braced language paradigm style. So this is how we say that this file contains this contract named layout. A file could contain multiple contracts. I can have one more contract here, contract some other. But whenever we name the contract, we follow this case, just as mentioned in the documentation. This cap word style. And the other thing which I was saying, contract and library names should also match their file names. Besides contract, there are other things also which we can write in our Solidity file name, like library. We will see that later. So if a contract file includes multiple contract and or libraries, then the file name should match the core contract, the main thing. But this is not recommended. Usually try to have only one contract per Solidity file. So That is why I named my file to be this layout.sol to match with my contract name. Continuing further, in our Solidity file, the very first line which you will see in almost all the Solidity files is this SPDX license identifier and the name of the license. First of all, notice that it is in form of comment. Usually in almost any programming language, the code that you write has the support of including comments which are ignored by the compiler. Compiler simply skims over them. For instance, hi, this is comment 1. This is a single line comment. If I jump over to next line, you see I'm no longer present in that comment. The color is not gray. To have multiple line comments, we use this syntax. Now this can have everything as you can see. This multiple line comment syntax is this / asterisk ends with asterisk and /. Single line comment, to write single line comment, just use 2 /. Now, although I have said you that the comments are ignored by the compiler, however, this is a special comment. And this comment need not be at the top. It could very well at the bottom or anywhere in between and will serve its purpose. What is the implication of this comment, I will explain shortly. But usually the best practice is to include it in top. That is how it is usually done. So let us now understand the meaning of this comment, which we see in almost every Solidity file. Trust in smart contracts can be better established if their source code is available. Since making source code available always touches on legal problems with regard to copyright, the Solidity compiler encourages the use of machine-readable SPDX license identifiers. Every source file should start with a comment indicating its license. There is this body known as SPDX, which you can read about. They are involved in various different things. So they have all these licenses. If I show you, the compiler does not validate that the license is part of the list allowed by SPDX, but it does include the supplied string in the bytecode metadata. This bytecode metadata I haven't explained yet, and I think it's best to show it with the example. We'll now start working with Remix. This is the URL remix.ethereum.org. Inside, on the left hand side, you will see various folders. The contracts folder is the one where your contracts will be stored. Let me just remove these contracts and let's create our own contract. I right clicked and selecting new file. I'm going to name it layout.sol just like we did before. So now I'm going to insert my license header like so, SPDX, and the name of the function that we wrote. But to compile this contract, I'll just add one more thing. You need not, you won't know its meaning yet, but I'll explain it shortly. And here on the very left hand side, this thing here, I will select 0.8.14 version. Alright, so this thing which I just did and this you can ignore for now. So I just wrote the simple contract, just having almost having nothing inside. So in the generated files, if we go into this artifacts folder, inside this artifacts folder, notice this file layout underscore metadata.json. If I open that up, you can see here we have this information also, MIT. If I rename it to something, anything, say, anything XYZ, and I saved it, you can see that this has changed and I have now new license file here, new license name XYZ. And on the bytecode side, which actually is passed to EVM, if I go here in the layout.json, we have this bytecode and this is the bytecode. If I go to the very end and let me show it you two times. Here I have pasted the two bytecodes, one having the license header as MIT and the other having the license header as XYZ. I have basically copied this portion, this object variables value here, and I have pasted here. The left one is for MIT, the right one is for XYZ. And if I find the differences, these two lines are different, but if you look very carefully, the difference starts from here, 22072, 220 EB. This last part is what is different in both of these files. Actually, this last part is the hash of the bytecode metadata. How this hash is computed is not of our concern, but I just wanted to tell you a bit about contract metadata. The Solidity compiler automatically generates a JSON file, as we saw, the contract metadata, that contains information about the compiled contract. You can use this file to query the compiler version, the source use, the ABI, NetSpec documentation, to more safely interact with the contract and verify its source code. As I showed you in the metadata, we had the license. There is also other information like the version and various different things is there. So that is what the Solidity documentation meant. And having the source code along with contract metadata, we can compile and regenerate the hash and see whether the deployed bytecode has the same hash. When we have the source code, like here, suppose I change this to 0 and save. Here again the version is 0.8.14, although I wrote 0.0. I haven't explained this to you yet. What I just mean to say that alone source code is not sufficient. There are some settings that we otherwise did, like here I selected 0.14, which was included in our metadata. So source file along with this metadata, when we compute the hash, this metadata will give us the settings, these additional settings, and when we compile our Solidity file using these settings, if we get the same hash which was put in the very end of this file, we can indeed verify that yes, this bytecode is legit, this belongs to this source code only. And to clarify any potential confusion, like previously I changed my source file but I did not change any settings, so you might think that we should get the same hash because it is called metadata hash, and the way I said it made it feel that metadata only contains settings, but that is not true. Metadata also contains source hash. Here you can see sources, contracts, my file. Metadata also contains its hash. For instance, here I have just written this simple Solidity file. Here I am declaring a variable x Ignore this int and private keywords. Simply understand I'm declaring a variable named x and putting the value 2. Now, when the compiler as such compiles, there is no, I can name it anything. It should not make a difference. Here I'm having the metadata. Now, if I change from x to y and see the new metadata and compare these two files, you will see that there are three differences, which is due to the change in source file. So even though there is as such no change, because if I look at the bytecode and compare the bytecodes, you will see that the bytecodes are different, but their initial part is same. The initial part which ends here to uh, you can see this initial part is same. The later part is bytecode metadata hash. So only that is getting changed, because our metadata also include the hash of the source file. Moving back to this which we were reading, so they are encouraging that we make our Solidity file open to the public to read. So whenever the code is made open, it touches the legal problems, legal boundaries. I'm as such not a legal expert, so better to include the license to tell which license your code follows. MIT is the most common one. You can read about different licenses online. The compiler does not validate whether you have put the genuine license name or not, but it will include it, the supplied string, in the bytecode metadata as I have explained you. If you do not want to specify a license, or if the source code is not open source, please use the special value unlicensed. Note that unlicensed, which means no usage allowed, not present in SPDX license, is different from unlicensed grants, which grants all right to everyone. Solidity follows the NPM recommendation, which you can read if you want to. And NPM recommendation, I opened their page, is basically saying the same thing. So many things you will see that Solidity has taken the ideas from NPM, and similarly for various other things, ideas have been taken from what has been in practice. Supplying this comment, of course, does not free you from other obligations related to licenses, like having to mention a specific license header in each source file or the original copyright holder. Technical, legal stuff. But what I want you to know is that, first thing, it is not compulsory to mention this. It is up to you. You feel you need to mention. As such, there is no it is not compulsory to mention. If you comment this out and compile, like if I show you, if I comment this out and compile, my code has compiled, although what I'm getting is just a warning. I'm not getting an error, just a warning to what they're telling me is to, you have not provided this license identifier. It's a warning, but my code will work. Second thing which I want you to know, if you're mentioning, you have to mention it each and every of your Solidity file. Next, let us move to this line. Pragma Solidity caret symbol 0.8.0. Now what does this mean? For this, let me first tell you here what it means. It simply means to include all compiler versions greater than equal to 0.8.0 but less than 0.9.0. Basically, as I previously told you, we write in high level language, in our case Solidity. We are writing a smart contract in that. Now, the compiler's job is to compile down this program into a low level EVM bytecode. Suppose in our high level program, we added a new functionality that by typing just maybe 2 asterisk 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 4 comma 3 I could imply to the power 4 whole to the power 3. Basically, suppose I want to add this functionality that whenever a user writes this number a followed by 3 asterisk followed by say 4 comma 3, this the compiler should be able to compile down this thing to an EVM bytecode implying this to the power 4 whole to the power 3. So I will modify my compiler to handle these cases, and so I will release, once I'm done, I will release a new version. So this is what all these compiler versions are. So when I'm writing this line, what this is implying that you can compile this source file using any compiler version lying in this range, greater than equal to 0.8.0, less than 0.9.0. And this is happening because of this caret symbol that we used. If I remove this caret symbol, then what this will mean that you can only compile this Solidity file using exactly this version 0.8.0. See, I saved it, I'm getting the error, but if I change it to 0.8.0, then save, the error disappears. But what I want you to understand that this caret symbol doesn't always work like this. For instance, here I have opened this website somewhere.npmjs.com. By default, like if I refresh this, by default it has this Lodash package, and if I write caret 1.1.0, you can see that it is selecting version 1.1.0, 1.1.1, 1.2. Notice this middle digit has increased. In our case, this middle digit was not allowed to increase. Only this last digit was allowed to increase. But this middle has also increased. Basically, when we are using this caret symbol, when the first digit is 0 and the second digit is non-zero. For instance, if I select this one, then it will go like 3.0, 3.1. It will select all the versions where these first two digits remain the same. But in case the very first digit is non-zero, then this will select all the versions where this first digit doesn't change. Now, why is this? First, let us understand what these three digits actually mean. Like if I open this website, somewhere.org, given the version number major.minor.patch, so the first digit signifies major, second minor, and the third patch. So you increment the major version when you make the incompatible API changes. You increment the minor version when you add functionality in a backward compatible manner, and you increment the patch version when you make backwards compatible bug fixes. Now, from this, you can see that usually there should not be an issue incrementing the minor version and the patch version because it is backwards compatible. You might have written code assuming some version. Even if the minor or patch is increased, you will still be able to run it fine. But here is the catch. In case of Solidity, notice this line, the fourth point. Major version 0, that is, if we have this type of notation, is for initial development. Anything may change at any time. The public API should not be considered stable. But in case of Solidity, what this will signify that when you increase the Z, then it is backward compatible, bugs are getting fixed, and it is almost safe. I'm saying almost because you are trusting the Solidity developers that they have done what is supposed to be done. So if you have written the code assuming version 0.8.0, this code will be fine even if it's 0.8.1.2 or so on and forward. But when the breaking changes are introduced, then this number, the second digit, will get incremented. So until our major version becomes 1, we are following this convention where incrementing z will mean added functionality, bugs getting fixed, etc. And the breaking changes will only be introduced when this y integer will get incremented. So using caret symbol is safe also in this case, and otherwise also when the major version is greater than equal to 1, even then caret symbol is safe. So it should always be safe to use the caret symbol, and that is why you see it as a common practice also in npm packages in general, and this is following those specification only. And you can do other combinations also, like there is this or, if you want to combine two versions, and all these you can try and play with in this website. Reading about pragmas in general, like here we use this pragma directive to specify about solidity versions. So what is this pragma? The pragma keyword is used to enable certain compiler features or checks. In our case we use version. A pragma directive is always local to a source file, so you have to add the pragma to all your files if you want to enable it in your whole project. If you want to restrict our compiler versions in all of the files, you will have to mention this in all of the files. Also, one thing more, this there was no it is not necessary to write this. You could have as well ignored it, and depending on what you select as the compiler version, you can compile with your desired compiler version. So it is not necessary, but since you would want to restrict the compiler version because breaking changes are introduced in the other versions, and some added functionality which you might be using is only possible for the current compiler version and onwards. So that is why you should restrict. If I now save it, it will compile but with a warning. Also, one more thing which I would like to add, since we will be learning considering Solidity version 0.8.14, so when you are writing your own smart contract, you should use pragma solidity, that caret symbol 0.8.14, not 0.8.12 or 0.8.0, but 0.8.14, because all the learnings that we will be going through have the assumption, since we are reading the documentation of 0.8.14, and therefore the features that we are learning are supported in that version at least. So we should follow 0.8.14 or higher. Like many things which we will learn are actually added, their support was added recently only, and therefore why I am saying this. Like here, I am in the Solidity releases page on GitHub. You can see they have the description of various versions release notes. For this 0.8.18, they have some added functionality in the language level, the high level part, that you can do this, etc. And we also can see 0.8.14 changes. I don't see any high level change here. So when going through the documentation of the Solidity, sometimes you will see me that I will be reading the documentation version which I will be reading for will be 0.8.18, but since no added extra things were there in the language level, like what I can see, we have some bug fixes, some compiler features which they have added, and yeah, they're mentioning some important bug fixes, but they haven't added the high level language additions like here they have done in 0.8.13. So that is why I did not feel the need to move to 0.8.14 when I was covering my notes. Also, sometimes you might see me when we will be going through various numerous examples. You might see me write pragma solidity caret symbol 0.8.0, not 0.8.14. Well, that was simply because at that, I knew that this will work with 0.8.02. But for you, I would recommend that always go with that version whose documentation you have read. One surprising thing I just noticed while doing this recording is that my name is also there. So, the little support which I added to the repository by fixing the few typo etc. in the documentation have got me here. Continuing in the documentation, if you import another file, the pragma from that file does not automatically apply to the importing file. What I haven't talked about import, I will talk about it shortly afterwards. But basically, here if you are importing some other file, then in that other file there might be pragma directive etc. So suppose that other file might have that I will support this compiler versions, but here you might have that I will support other compiler versions. So that pragma need not apply to this file. It does not automatically apply. You will have to manually specify your own pragma here. Continuing, this version pragma I have already covered. This pragma solidity thing I have already covered. And this ABI coded pragma, I don't see any need to explain it at this point. You can read about it later, because in you might see in some Solidity files that they might have written this pragma ABI coder v2, but actually it is enabled by default in our version. Like, since it will be activated by default starting from Solidity this version, there is the option to select the old coder using this. Basically, this additional coder has some additional features like the new ABI coder is able to encode and decode arbitrarily nested arrays and structs. You, of course, haven't talked about structs and array, so that is why I'm not going into detail here. But I don't see much point also, because it is anyway enabled by default. But you can read about it after this course. Now, regarding import statement, before I begin, I would like to say that they are saying to avoid using like this, but instead use either this or this. But the thing is, we usually don't work with global symbols. I personally haven't seen them in practice. So mostly you will see this only. But since they have mentioned it, I thought I will go over this also. So better I do it with example. Yes. So here is this file layout.sol. First line is our license identifier. Then the which compiler versions I am allowing. Then this is a global symbol x having value 2, an integer x which is having value 2. Constant, ignore this keyword for now. Then I am having a contract named layout which is having a variable z, an integer variable z of value 4. Ignore this word internal for now. Now I am going to import it to my other Solidity file, which I am calling iLayout file, in which I am defining two contracts. I told you that usually we do only one contract per file, but here I am doing two contracts in file. This will also show you, makes it a bit easier to show. Here in this iLayout file, I am going to import my two global symbols x and layout. From this, even if I don't do this, if I remove this curly brace part, then Also, and I also have to remove from part. Then also it is going to import these two variables x comma layout. Basically it will import everything, every global symbol present. In our case we have these two, which I'm going to import. Now in this first layout I am declaring a integer y which is having this value x, and as I showed you, even if I remove this, then also it is compiling, so that's working otherwise also. And this is function, which is basically, I will tell you the meaning. You need not understand all this public, view, assert. The For now, since we haven't covered these keywords, we will shortly cover. But what it is doing, it is simply checking whether y is equal to 2 or not. Since x is 2, I want to know whether my y is 2 or not. And this other contract which I am defining, it is inheriting now other symbol. I have one x and it is inheriting the other contract. This inheritance is something we will see in detail later, but basically you can imagine that since we are inheriting this contract layout, in layman terms you can just for now understand that we will be able to use this z variable, what is inside this contract, since we are inheriting it, just like we inherit assets. So we have inherited this z, and this function will tell me whether is z 4 or not, because in original contract z is 4. All right, so now if I have saved it all, if I go here and let me just move, now let me select my I layout 1 which I'm going to deploy. Inside it I'm going to call this function is y2 by clicking on it, and it has successfully worked. There has been no exception, because if I show you the exception part, if I make it 3, save and deploy it, now call y2, you will see there has been a revert, error has been raised. So that was fine. Now I'm deploying this other contract, I layout 2, deploy is z4, I'm writing the function, running this function. So it is also successfully ran. Now since I have imported them specifically, I can also do one thing. Just as what they have said, I can rename them. Like I can do this as say k, then instead of x I can put here k. So this will allow me to avoid conflicts. Suppose I have some variable int x equals to 5. So this way I will be able to avoid conflicts. Even better would be, in my opinion, to do something like this. Then you can do like this. Here I am replaced make my import as layout, so any global symbol inside it I can access using this dot notation. So dot x dot, I'm saying the contract name, and like that. So this is also fine. Now if I read through the what does documentation have to say, now having seen the example, I'm sure you will be able to understand this better. This part no, we need not do. Okay, so import file name. The file name part is called an import path. This statement imports all global symbols from file name, and symbols imported there, I mean this file name could also be importing some other things, so that whole chain gets imported to us into the current global scope, which is different from ES6, some JavaScript thing, you need not bother. This form is not recommended for use because it unpredictably pollutes the namespace, since there might be some collisions, you can understand. So but as I told you, we rarely work with global symbols. So if you add new top level items inside file name, they automatically appear in all files that import like this from file name. it is better to import specific symbols explicitly. Basically, they are saying that if you do simply like this and you declare a new variable in that original file, that will get imported to all others. So it might pollute, it might lead to collision. So better you do something like this: import file name as symbol name, or something like this: import star as symbol name. They are both equivalent. The following example creates a new global symbol name, whose members are all the global symbols from file name, like this, which results in all global symbols being available in the format like this, which we used also. A variant of this syntax that is not part of ES6 but possibly useful is this, which is exactly what we used, which is equivalent to this previous one. If there is a naming collision, you can rename symbols while importing. I told you an example for this also. For example, the code below creates a new global symbols alias and symbol 2 with reference, which reference symbol 1 and symbol 2 from inside file name respectively, as they have showed. Now, if you may remember, I told you that we will go through a example bytecode. So let me fulfill that promise. This is the article through which we will be going through, written by Knox. He has done other deep dives also. For our case, we will be focusing on this one. We will also learn few things which will also be useful for us otherwise. When we opened our remix tab, initially there were some files which I deleted here. One of those file was this one_storage.sol. What is present in this file? A license header, pragma solidity version which we covered. Then the name of the contract is storage, and this file has only one contract of name storage. Inside that storage contract, they have declared a number variable of basically you can say non-negative integer. I will explain this keyword later. For now, understand this is non-negative integer. And then we have a function name store, which is going to take a non-negative integer and put that in this variable number. Similarly, we have other function retrieve, which is going to give us this number. We will return this number to the caller. You please ignore these other keyword public view, etc., because this is something I haven't explained yet, but I have explained you the semantics of the code. Now once we have compiled this contract, this file, we will get this bytecode. This is the runtime bytecode which we will get. In that bytecode, there is this section which is of our interest now, because as I've shown you the examples where we are calling some function of the contract of some other contract. Now, how does that happens? How does the called contract know what function is being called? That happens due to such bytecode sequence which I have highlighted here. For this example, this is that function selector logic. This snippet which I have highlighted represents the function selector logic. We will go through this snippet and understand it. One more thing, opcode is 1 byte long. Now here I will cover about hexadecimal digits, which I haven't explained before. Now I think it's a good time to explain. We saw what a binary number is, right? A sequence of binary digits, like say, I forgot to press the record button. Anyways, so consider this binary number. Binary number, as I told you, is a sequence of binary digits. So consider this binary number. This position is having the weight 2 to the power 0, this 2 to the power 1, and so on. This last one 2 to the power 7. So if I want to convert this number into decimal, I will do 1 into 2 to the power 7 plus 0 into 2 to the power 6, which is 0. So I'm ignoring these 0 terms and straightforward I'm just writing these 1 terms, which is 2 to the power 5 plus 2 to the power 4 plus 2 to the power 2 plus 2 to the power 0, which is equals to 2 to the power 7 is 128, plus 2 to the power 5 32, plus 2 to the power 4 16, plus 2 to the power 2 4, and plus 2 to the power 0, which is 1. So this 16 plus 4 is 20, plus 1 21. This you can simply view it as 130 plus 30, so this is 160. So in total 181 in decimal. Now if I were to break this binary number into the chunks of 4 digit, like so, say this binary number which we had 1 0 1 1 0 1 0 1. If I break it into chunks of 4 starting from the right hand side, then we can see this in itself is 2 to the power 0 plus 2 to the power 2, this is 5, and this one is 1 plus 2 plus 8, 11. This one is 11. And if we look at the possible range of a 4 digit binary number, a 4 digit binary number can either be 0 0 0 0, then 0 0 0 1, 0 0 1 0, 0 0 1 1. This is in decimal 0, this is in decimal 1, this is in decimal 2, and this is in decimal 3. So on, if you go, in the end you will have this 1 1 1 1, which is in decimal 15. To verify that, you can see this is this number is 2 to the power 3 plus 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0, which is, you can see it to be 15. So yes, so in case, so a 4 digit binary number can range from 0 to 15. And how it is denoted in hexadecimal system, for 0 to 9 we use the same digit, that is a binary number having decimal value 9 is simply written as 9 in hexadecimal notation. And for the numbers ranging 10 to 15, we use English alphabetic characters A to F, like 10, 11, 12, 13, 14, 15. For 10 we have A, then B, then C, then D, then E, then F. So 15 is represented as F. Here, yeah, sometimes people use capital alphabet, that is up to them. So in case, so here this binary number will be written as, in case of hexadecimal system, we can write this binary number as this B5. So if somebody gives me a hexadecimal number B5, I know what this will mean. I will expand each of these characters into their corresponding 4 digit binary. For 5 I know it is this 0101, and for B I have this 1011, and this is my data which I had. Ultimately, you know, the data is sent as binary, and you know, binary is suitable for us as 0 can represent low voltage and 1 can represent high voltage. I mean, very basics of computer I just told. So this is the hexadecimal character system I talked. So moving backwards, this is our bytecode, and you can see we have E here, B here, so on, A here. So each of these is a hexadecimal character, and since we are given this representation, we know that it is assembly language, in the sense that each of the opcode is 1 byte in length. Now what is 1 byte? 1 byte is 8 bits, as I told. 8 bits. So we will need 2 hexadecimal characters. As one hexadecimal character is of 4 bits, so 2 hexadecimal characters. So one opcode will take 2 hexadecimal characters. So if we go here, consider this part of the bytecode. If you write it here, this left section is the bytecode, and we can see first 4 digits, which is 6000. 6000. Here the 60 means push one opcode. Each opcode, as I told, is of 1 byte. So 2 hexadecimal characters will make up 1 byte. So this is push 1. Push, what does push 1 means? It means to push 1 byte. So when we encounter this 60, the EVM knows that it has to push 1 byte. So it will see the next 1 byte, which is 2 hexadecimal characters, and put them in stack. If I show you, here we have this push 1. Place 1 byte item on the stack. Similarly, there is push 2, push, or push 6 will take the next subsequent 12 hexadecimal digits, basically 6 bytes in the bytecode, and push them on the stack. So this is the first, you can say, line of the assembly. Then 35 maps to call data load. To know which this byte represents which opcode, you can head over to evm.codes, and here you can see that 35 maps to call data load. Basically it means this. So 35 means that. 60 means push 1, so it will look at the next byte which has to be pushed on the stack. 1C, if we go here, there should be 1C somewhere. 1C means shift right. I will explain what is shift right. So similarly we have all this part of the assembly language. So in EVM, opcode is 1 byte long, and that means it will be possible to have 256 different possible opcodes, because the 1 byte can hold 256 values. Just like how 4-digit binary number can hold values from 0 to 15 in total, that means 16 values. Similarly, an 8-digit binary number can hold 256 values. You can try that and verify yourself. But not all of these is used. At the time of writing this article, there were only 140 unique opcodes. So now when we call the function of a contract, there is a particular way to do this. How it is done, if I were to tell you, first, like, we find the hash of the function which we want to call. For instance, in this Solidity file, there are two functions. One is store and one is retrieve. Retrieve is taking no input parameter but returns a variable, and store is taking an input parameter. What we do is we found this hash catcheck it is said 256, and we write the name of the function along with the type of the inputs that it has, and we find its hash. If I open this link which the author has shared, inside if I put this value store uint 256, I am getting this hash. What now we have to look at is the first 4 bytes. As 1 byte is 2 hexadecimal characters, we will look at first 8 hexadecimal characters. So 1 2 3 4 5 6 7 8 till this 1D. So yeah, so we have the same output here, 6057361D. Same as here. Similarly, catch check 256 hash of this retrieve function. Find the first 4 bytes. You will have this. So when we are calling a function of some other contract, in that message our payload, the first we give this 4 bytes of the function hash which we are going to call, and then we concatenate it with the input value. In our case, if we are want to call this store along with number and non-negative integer of say value 10, then we would have it like this. This part is first 4 bytes of the catch hash of that store function, and then this last part is what I will now explain. Basically, when I told you about hexadecimal character, we saw that A represents 10 in decimal number. So here this last digit A signifies 10. But why do we have so many zeros? Because this is not a 4-bit number. This is a 256-bit binary number, and to compensate that we have these zeros to put value 0 in those other binary digits. Each of this is getting mapped to 4 of the binary digits basically. If I write a number like this 000A, this would imply that it is a 4, 8, 12, 16, a 16-bit binary number. Having the value, the decimal, the binary representation of 10, which is 1, 0, 1, 0. This will map to 0, 0, 0, 0. This 0, 0, 0, 0. This 0, 0, 0, 0. So we got our 16-bit hexadecimal, 16-bit binary number. Similarly, when we'll expand this, we'll get our 256-bit binary number, which is what we wanted to pass. Yes, this U in 256 just basically means 256-bit binary number, according to what I have explained you before. So now this is what we have passed in the payload in our call data. This not this. Yes, this is what we have passed in that. So now let us see what does the bytecode does. When the EVM is running this bytecode, it will come to this part, and this is where the magic will happen. It will be able to select our function which we want to do with the help of call data. So let us go through this bytecode sequence, which is this. So let us go through this. The very first instruction is this push 1 0x00. We start with the push 1, which tells the EVM to push the next 1 byte of data. In our case it is 00, which is equal to 0 in decimal. Also this 0x is just like a prefix to tell us that we are writing a hexadecimal number. To the call stack I have explained you in detail. Just to clarify any potential confusion, here from call stack the author means expression stack only, not that call stack which I explained before. Why we do this will become apparent later. Next instruction is call data load. This instruction call data load. What this will do, it is going to first of all pop the first value, the topmost value on the stack, which is 0, and it is going to load the 32 bytes at the offset of call data. Basically, if this is our call data, where we have put that value, the first 4 bytes of the catch hash along with the 256-bit binary number representing 10. So at the 0th offset, we are going to load the first 32 bytes. Basically one word. If you notice carefully, our message is 36 bytes long. 32 bytes is for this 256-bit binary number, and 4 bytes is for the function that catch a hash stuff. So in total 32 plus 4, 36 bytes long is our this. Whenever we do call data load, it loads the one word from the offset which we got to the stack. So this opcode loads in the call data to the stack using the input as an offset. Stack items are 32 bytes in size, but our call data is 36 bytes. The pushed value is message.data. This is something I will explain, so need not bother about this. So now after this call data load, we have the first 32 bytes in a stack. But what the logic wants is only these first 4 bytes. So this first 4 bytes ending till 1D does not want the remaining part. So one way to achieve it is by using arithmetic shift operations, which I'm going to explain next. Basically, suppose I have a binary number this 0 1 1 0 0 0 1 1. This is the binary number suppose I have. Now if I shift 4 bits to the right, meaning suppose I shift only 1 bit to the right, that means I'm basically imagine this as a tape or something, and I'm shifting it one place to the right, then I'm having it like this. This is how it will look. This is going here, this here, and this here, 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 and here. And our region is this. So what will happen when we shift a 1 bit to the right? This bit is lost. If I change the color, this one is lost, and an additional place is available which by default has 0. So we will get this number when we shift 1 bit to the right. If we shift 1 bit again to the right, what we will end up is this 0 0 0 1 1 0 0 0. This is what we will have. So we get this from this if we shift 2 bits to the right. This is what is meant by shift right operation, where we tell how many bits we want to shift by. For example, in this, if we shift right by 4 bits, then what we will have is basically this part 0 1 1 0, and then remaining 4 bits will be 0. Now covering shift left. This was shift right. Shift left if we do, which is very similar in that what will happen, the leftmost bit will get lost and the new right bit will be introduced having value 0. For instance, if I give you a simple example, suppose we have this binary number, right? Only a 4-digit binary number. If I shift 1 bit to the left, this will get lost. So if I shift this 1 bit right, I will have this. This got lost and these are the remaining, and this new bit got introduced. This is shift left. Here also you can shift by how many bits you want. So when we got the first 32 bytes, we only want first 4 bytes. So we should shift right by 28 bytes, because 4 bytes are of interest to us and the remaining 28 bytes we don't want. So in this big number that we have, if we shift right by 28 bytes, these 4 bytes will be available to us, and these 28 bytes is equal to 28 into 8 bits. And if you do math, this 28 into 8 will come out to be 224. You can verify that. So what does next instruction has? Next instruction has this push 1 E0, which is in decimal means this only 224. Then there is this shift right operation. If I look at its code here, shift right, it will take two values from the stack. One is shift, how many bits you want to shift by, and the value, and output will be this. This operation is denoted by, like if I tell you, we saw shift right operation declared by this 2 greater than signs. That is how it is denoted by. If I shift by 1 bit, what I will write is this number 1, meaning I have shift right by 1 bit. Shift right by 3 bits will be written like this. Similarly, shift left by 4 bits will be written like this. Just like how we write A plus B. Similarly, this is the symbol for this operation. Moving on. Now output is this, what we wanted. Basically here the author has shown only the least significant part. Basically, when we write a number, suppose we are working with 8 digit binary number, which is suppose this 10110001, then this is called, the rightmost part is called least significant bit, and the leftmost one is called most significant. And if you pay attention, this is having the weight of 2 to the power 7, whereas this is having the weight of 2 to the power 0. So this weight is also big. And usually when I just write in decimal also, if somebody writes only say 4, then, and if suppose we are working with 2 digit numbers, and if somebody writes 4, then it means that the left digit is 0. We usually omit them, right? So in similar case, if a binary number is suppose this, in that case one can simply write it as this 110. One basically omits these leftmost trailing zeros, and just like how we do in decimal. So here also the least significant part is shown. The leftmost bits are 0. Next instruction is dup1, which is going to basically duplicate the stack item. And then next instruction is this push for some number. What is actually this number? If we since we had two functions in our smart contract, store had this hash first 4 bytes, whereas retrieve has these first 4 bytes as this, which you saw. So it is that only. Here, yeah, this is that other function retrieve. Next instruction is equal. It will check whether these two, the topmost two stack items, are equal or not. In this case, this is not equal, so 0. So that means the function which the user wanted to go is not retrieve. We saw 0, and then it is going to push this value, which means 59 in decimal, which is actually denoting the line number. You can, if you read what the author has written here, you can view the program counter location in a similar way to a line number location in your Solidity code. If the function is defined on line 59, you can use the line number as a way to tell the machine where to find the code for that function. Basically, if this was 1, if 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 this instead of 0 turned out to be 1, denoting that yes, the user wanted to go to the retrieve function, then the code knows that the retrieve function is at this place of the like basically we will set the program counter's value as 59, and program counter you can simply view it as line in simple terms or abstraction. If we do, just like how we have different lines in our code, program counter not exactly line, but you can think of it as line number only. So if the retrieve function was at line 59, the program will now have to jump to the line 59 to execute this retrieve function. So jump I stands for jump if. It will see that if this value was 1, then it would have jumped, but it was not. So now we are back here. Next we do this duplicate process, and this time putting the other functions, the store function, which is exactly what we wanted to go at. So equal turns out to be 1. Now it is at this line 89, and here we would be able to jump to that, and this is what we wanted. So here you have also understood about this first, how the function selector logic is done, which is first 4 bytes of the catch-check hash. And in case if you want to visually like manually go yourself through this process, the author has provided this link in which you can manually run this code one by one to see. This is at offset 89, which you can view as line number 89, where our store function would have been present. For the first line is usually jump dest, denoting it is the destination where one has jumped to. Very low level stuff. You need not bother that much. Just that in the low level program, if I am jumping to some place, not this, this. If I am jumping to some place, but that place does not have this, that means I have done something wrong. That is how they have designed the EVM. Need not bother, but I wanted you to understand other things, which I hope you have understood. You can go through this article if in case something is not clear, you want to read something more here. So with this, I think I have explained quite a detail about EVM. Now our next focus will be mainly on Solidity. Let us now discuss about types. So we are at this URL here in the language description under types. So Solidity is a statically typed language, which means that the type of each variable needs to be specified. Ignore this state local for now. Solidity provides several elementary types which can be combined to form complex types. We will see all this later. So main thing which I wanted you to know, that Solidity is a statically typed language where each variable that we use, we specify its type, like here we wrote int, etc. In contrast with a language like say JavaScript, where at runtime it will see what it gets. So like my professor used to say that even if you're at gunpoint, don't code in JavaScript. So Solidity, in contrast to that, is a statically typed language. The concept of undefined or null does not exist in Solidity. It exists in JavaScript though. But newly declared variables always have a default value depending on its type, which is, you can say, the byte representation would be 0. I will explain this. To handle any unexpected values, you should use the revert function to revert the whole transaction or revert a tuple. This is you need not bother. Basically, every variable already has a value assigned to it. If you assign a value, for instance, here if I declare some variable in some var, if I assign the value, then it's fine. But if I don't assign the value, then by default it will have the value of 0. Basically, if I show you in this section, if you read under control structures, under this heading, basically here under this expressions and control structure, here a variable which is declared will have an initial default value whose byte representation is all 0. Like for integer, in case of this this u into 56, which I told you was simply a 256-bit binary number. So in that case, since it is of 256 bits, so initial value will be all zeros. All 256 bits will be 0. Provided we haven't assigned any value to it. If we don't assign that, all will be 0. Similarly, other types, wherever they are stored, they will be taking some bytes. So what those bytes will be initially 0 for each and every byte, for each and every type. Here if we go forward, the default values of a variable are the typical 0 state of whatever the type is. For example, the default value for a bool is false. A boolean basically holds only two values, either true or false. False is, you can think of it as 0, just like we saw in that bytecode, and true you can think of it as 1. So 0 state is like false here. The default value for uint or int type is 0. For arrays and other elements, we will see them later. So for now, I just wanted to tell you that it's like 0. The byte representation contains 0. Regarding this revert and this tuple, we will see them later. So if I were to tell you, in Solidity, there are two types of types. Two types of types. One is value type, and the other is reference type. This reference type has only 3 participants, which is arrays, structs, and mapping. This arrays also contains string, bytes. There are also types like string and bytes, which we will cover. They are basically arrays only. So value type has various different types, which we will see, like integer, like this u into 256 and an integer. What is unique in them both, as we will see also later, is basically they are always copied. There in reference type, reference could also be passed. You need not understand this, I will explain them later, but just I want to summarize or give a high level overview. Here we don't have any concept of data location. Here we have concept of data location. I mean, obviously these are also, the value types are also being stored somewhere, but we will see what I mean by this data location. So if I look at the different value types, The following types are also called value types because variables of these types will always be passed by value, that is, they are always copied when they are used as function arguments or in assignments. What this means basically, suppose I am doing something like this: int y equals x, then this x variable already had some value, either default 0 value or something else. Then this will get copied to y. Basically, a new space will be allocated for y, and in that the value of x will be copied. Now in case even if I modify y, there will be no change in x. If I suppose we had this int x to be 2, and now if I do if I now modify y to be 4, then the value of x will not change, although I have changed the value of y. But in case of reference type, if it is passed by reference, we will see that even if we change y, the value of x could also change. We will see that later, and that time it will become more clear. One of the value type is boolean. Bool values only have two possibilities, either true or false. These are some of the operations. Basically, if I do this, if I do negation of x, suppose I have bool x2 equals true. Maybe I can show you in Solidity. Like here, ignore the rest of the part, focus only on these two lines. If I have written bool x to be false, this means that x variable is having the value false. Now if I do this negation operation on x, then this right hand side will become true. So I am updating the value of x to be a value of true. This is how negation works. Logical AND means if I do this is true and suppose true. So true and true is true, true and false is false, false and false is false, and yeah, these were the possibilities. So I have shown you the possibilities of how AND operation work. Basically, if either of the left hand side or right hand side is false, the answer is false. It gives the output as true only if both of these are true. That is how negation works. Or will give true if any of the part is true, and will give false only if both are false. Equality, you can understand that if I do something like some if statement, we will cover if statement. If x equals true, do something. This is checking if x is equals to 2, then then we will execute this code block. This is how equality will operate until compare the left and right, and output will be either true or false. True if this matches, both are equal, and false if otherwise. Similarly, we have inequality, just basically opposite of equality. The operators OR and AND apply the common short-circuiting rules. What it means that in expression like this, as I told you, if either of them is true, that means it is true. So it will see the first f of x. If f of x turns out to be true, it need not evaluate this expression. This might be a function call or whatever. It need not do this because it knows the output is true. So we have short-circuited like that. G of I will not be evaluated even if it may have side effect. What this means, that if we were to execute this function g of I, it might be modifying our storage. It might modify our storage, so that will be a side effect. But we won't be executing this if f of x turns out to be true. So the modifications, the side effects done by g of I will not happen. So you have to be careful. Like if you expect some side effect to happen, even if this statement turns out to be true or false, you should not do like this because it might get short circuited. Then we have next type, integers. Now let me clarify about this integer thing. Till now we have been delaying it, so let's finally do this. There are two types of integers. One is signed and the other is unsigned. For the unsigned, it is just as that binary number I told you. But for the signed, there is a catch. Let me show you for the example of 8-bit number. Suppose we have a 8-bit number. If I have this 8-bit number, suppose 1 0 0 0 1 1 1 0. So 1 2 3 4 5 6 7 8. Yeah, it's 8-bit. In case of unsigned, this is to the power 7, right? In case of unsigned, in case of a normal binary number, this was to the power 7 and this is to the power 6, so on. This was to the power 0. This is what we had in case of unsigned. But in case of signed, if I were to just copy this, this one, oh wait, not this. This one, this most significant bit, instead of being positive to the power 7, it will be negative. It will become negative to the power 7. So, whereas in the case of unsigned, the range means all the possible outputs was from 0 when all bits are 0 to a number when having all bits 1, which will be, if you were to do this summation to the power I, where I goes from 0 to 7, this will turn out to be to the power 8 minus 1, which is equals to the power 255. So range is from 0 to 255. That is its range. But in case of signed integer, I told you everything else remains the same. This is to the power 6. This is to the power 0. Only the most significant bit is minus to the power 7. So what will be the most negative number in this case? This will be obviously when only this bit is 1 and remaining are 0, because remaining will add positive. We don't want to add any positive. So having this all as 0 and only this as 1, this will be equals to minus of to the power 7, which is equals to minus 128. Yes. And what will be the most positive number, which will obviously when this is 0 and remainings are 1, 2 3 4 5 6 7 8, and this will be equal to summation I going from 0 to 6 to the power I, which is equals to the power 7 minus 1. This is a simple geometric progression. You can Google about geometric progression if you don't know. So this will be equal to 127. So here the range is from minus 128 to 127. Again we have this 256 possible outcomes. Like here also we had 256 possible outcomes. Here also 256, because 256 possible values of binary are possible, and each of them is getting mapped to a unique integer following this system. This system is called as 2's complement. We need not go into much detail about 2's complement, like what is 1's complement and things like that, but I have explained you the outcome of the summary of the 2's complement, which is this. So this is for the 8-bit number, where the range turned out to be minus to the power n minus 1 to the power n minus 1 minus 1, where n is the number of bits. Right? Number of bits was 8. 8 minus 1 is 7. So minus to the power 7 to the power 7 minus 1. Similarly, for this, the range turned out to be 0 to the power n minus 1. So this is the difference between unsigned and signed number. Signed number allows for negative values also, unsigned doesn't. And because unsigned doesn't allow for negative numbers, it range allows for more positive values. Now reading what the documentation has to say. int /uint signed and unsigned integers of various sizes, like this, like from uint 8 to uint 256. Uint 8 will mean 8 bits, uint 256 will mean 256 bits, and you can go on increasing it in the steps of 8. Similarly for int you can do. And if you just use uint or int, like here, if I just do int x, this is equivalent to saying int 256x. They are aliases. Instead of writing int 256, you can simply write int. Similarly, instead of writing u int x, you can simply, instead of writing this u int 256x, you can simply write u int x. So that's what they have written. Now they have operators less than, equal to, less than, equal to. These are simple comparison operator. This is not equal to, this is greater than, equal to, this is greater. Each of them will evaluate evaluate bool. So if 3 less than equal to 2, this is output will be false. Now this is bit operations. I haven't talked about bit operations, so let me talk about them. Okay, since each number have a binary representation, suppose I have two numbers, this is their binary representation. Okay, let me work with 8-bit only. 2 3 4 5 6 7 8. Assume the next number is this: 1 2 3 4 5 6 7 8. All right, now I will output the various results of them. If I do OR, what does OR do? It will look at corresponding 2 bits. If either of them is 1, it will give 1, otherwise 0. So OR is this: 1 1 0 1 1 1 1 1. This is the OR output. Next I will look at AND. What will AND do? It will give 1 as an output only if both corresponding bits are 1. So let me show you about AND. So 1 0 0 0 0 0 1 0. This is AND. Now about negation, or NOT, you simply call it. Simply NOT works on a single binary number. So assuming we are working on this, we have to just negate each of the bit. If it is 1, make it 0. If it's 0, make it 1. So 0 0 1 1 0 1 0 0. This is NOT. And if I look at other operations, we did AND, this is AND, this is OR. Okay, this was NOT, bitwise negation. How you write it? You simply write it like this. Like if I do this, int y is equals to NOT of x. That is how you can write it. This is exclusive OR. So let me tell you. Exclusive OR is also simply written as XOR. What it outputs? It outputs 1 only if exactly one of the corresponding bits is 1. For example, here both are 1, so 0. Here exactly 1 is 1, so 1. Here we will also output 0. Here 1, because exactly one of the corresponding bits is 1. Here 1, here also 1, here 0, and here 1. This is XOR. Moving on, we have our shift operations. Shift is just that, as I have previously explained you. Like if I do here, suppose we have a variable int z is equals to 4, which has binary representation of this. This is binary representation of 4. I mean the left bits are 0, and then this is the least significant part I wrote. Now if I do int some variable k is equals to 4, this shift operation, to 2 bits. If I shift it by 2 bits on the right, the output should be 1. This is what we expect, and I have to do it like this, making this to be Z, and I'm getting a warning which is simply saying that this is unused variable, we need not bother. So let me use this unused variable. So I'm going to assert that k is equals to, it should be equal to 1. So it should be equal to an integer 1. So let us try and run this. Okay, I'm going to run this function bool. So it ran successfully. So yes, it worked. Now one thing which I would like to add, here I wrote u in 2. If I do this like this, even then it is working, because Solidity by default will assign an unsigned integer type to this. I need not, what I was previously doing, I was specifically making it an unsigned integer. We will see this typecasting, it is called. We will see that later. But my point was just to show you this, that it will get the final value here would be this 1, and which is what came out also. So this was right shift, left shift. Whenever we shift, this thing has to be an unsigned integer, because we shift by positive thing. I cannot do -2 here. This is giving me an error. So this has to be an unsigned integer type. Then arithmetic operations is normal. For any integer type x, you can use this type x.min and type x.max to get the minimum and maximum value representable by that type. Like I have already told you, for unsigned and int, and for unsigned and for signed, what are the minimum maximum possible. You can also see them if you write this type int, let's just say of 8-bit dot, how they do this, like this. If you do, and you can assign it to the value int 8, and this is working fine. This is just getting the unused error, that's it. Next, let's just read this warning. Integers in Solidity are restricted to a certain range. For example, with uint 32, an unsigned integer of 32 bits. This is 0 up to the power 32 minus 1. Like here, as I showed you, for 8 bits, for any n bits, it is 0 to the power n minus 1. So in that case, 0 to the power 32 minus 1, which is what they had. Yeah. So there are two modes in which arithmetic is performed on these types. Now there is this concept which I will explain you now. Suppose I have this max int, which is equals to this. Now to this max int, if I do this, can it hold this value? Because it should not be able to hold this value, because already it is having the maximum value. Now if I run this program, I have saved it, deploy, calling that function, it got reverted because we crossed the range. That is what is happening. In usually languages like C, you will not get any error like this. What will happen, that if we look at what we wrote in the here, for the signed 8-bit number, this was the range, and this is how 127 was represented as. Now if I add 1 to this number, in case of Solidity we are getting reverted, but if I show you by adding 1, it will have the binary representation of this, the most significant bit being 1, and remaining being 0. This is how it will have the binary representation. If we do our usual addition, like how we do the usual addition, how most likely the computer logic will be doing the addition. But notice that this turns out to be, in case of signed integer of 8 bits, minus 128. So in case of languages like C, most likely you will get this output, minus 128. But in case of Solidity, since this is not what is expected, we will get a revert. Initially this was not the case. Initially in Solidity 2 you will not be getting revert, an exception would not have been raised, but starting from, I guess, version 0.6, this has been introduced. So previously you might have seen something like safe math. I mean, there were these things like safe math libraries, etc. So they are not useful now. So yeah, so there are two modes in which arithmetic is performed on these bytes. One is the wrapping, and the other is the wrapping, which is also called as unchecked mode, and the other is checked mode. By default, arithmetic is always in checked mode, which means that if the result of an operation falls outside the value range of the type, the call is reverted. In our case, we were expecting this addition we were doing on the max possible type. What was the max? Max was 127. So 127 plus 1, we were expecting 128, which is not possible. It's outside the range. So hence the exception was raised. The call is reverted through a failing assertion. You can switch to unchecked mode using this, in which case the exception will not be raised. And if I do that here if I do this unchecked, let me bring it to new line. Now if I do assert max int 8 is equals to type int 8 dot min, I believe this should work correctly. Let me check. And yep, it worked correctly. We did not get any revert. So yeah, as I told you, adding plus 1, we went through the most negative value, which was minus 128. And this is what is verified here also. So that is how unchecked is used. Bit operations I did, and then shift operations I also did. Here you can notice about shift operations that x right shift by y bits is equivalent to x dividing by 2 the power y. You do some hand numerics algebra and you will see this to be the case. In fact, in almost all languages, if you want to multiply by 2 the power something or divide by 2 the power something, this is cheaper. In Solidity also, this will consume less gas compared to this. Okay. We have this note. Overflow checks are never performed for shift operations as they are done for arithmetic operations. Instead, the result is always truncated. What this means, basically, for any number, any 8-bit number, suppose this 127, which is having this binary representation, if I left shift by say 2 bits, then the output will be this 1 1. First let me write the original number, which was 0 1 2 3 4 5 6 7 8. This was original number. Now I'm shifting it by 2 bits, so hence I'm going to get this. This is how, and these new zeros will be introduced. Now notice that these 2 bits are overflowing from the 8-bit convention, 8-bit slot that we had. So these will simply be discarded. This will be discarded. And this will be our output in that. And thus I just realized a mistake. I wrote a 9-bit number. So let me remove one of the digits. Now it is an 8-bit number. So I I left shifted by 2 bits. So it should have been multiplication by 2 the power 2. But here it is not the case. Since this was an int 8, I wrote a code to check, to show you that let me define this number right 2, which is having this 127 value. Exactly the example which we went through, this thing. I'm shifting it left. Did I just say right? I guess I'm shifting by left. Sorry. I'm shifting by left by 2 binary digits, and if I do, I'm getting this. Now, as we knew, the most significant bit has the weight of minus 2 to the power 7. And then you have this to the power 6. So you add all this for this one, and you will see the answer turns out to be minus 4. And that is what I have verified here too. I have verified through this site also, which is showing that decimal from sin 2's complement form is minus 4, same as what calculator gave me. So this is what truncation meant, and this is also true provided the original type can hold that value. Now about addition, subtraction and multiplication, the expression negative x is equivalent to this 0 minus x, where t is the type of x. This is how the logic does it, the computer logic in the low levels. It can also be applied to sign types. The value negative x can be positive if x is negative. That's obvious. There is another caveat also resulting from 2's complement representation. This is what I'm going to explain. If you have int x, type int dot min, then negative x does not fit the positive range, as I showed you in case of integers, signed integers. Negative, we have range from minus 128 to 127 for 8-bit integer. It is not 2 plus 128. So negative of negative 128 is plus 128, which is outside this range. However, if we go by this logic, let me show you how the computer will do the negation part. In the negative part. If you have studied computer logic, you will know that to compute the negative of, say, this number, which we have are this negative number, and in fact any number, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8. Yes, to compute its negative, first we will find the ones complement. There is something known as ones complement, which is basically negation only. You do the negation of each bit, which will give us 0 1 2 3 4 5 6 7. Yeah, and you add then 1 to it, and if you do that, adding 1, we will have this 1 plus this is 0, then here also. So ultimately this is what you will end up. So you ended up to the original value. I talked about ones complement, which I said to be actually equal to, you just find the negation of each bit and then you add 1. This how we do addition of 1 is something I haven't explained. This you need not know, but in case you were able to understand, then well and good. Just like how when doing normal additions we have something like carry forward, so here also when I'm doing this number plus 1 here, then 1 plus 1 is 2, and I have no digit for 2, so 2 is actually 1 0. This is how 2 is, because this digit has weight 2 to the power 1, which is equal to 2 only. So we write like this. We write 0 because this is 1 0, right? 0, and then 1 gets carry forward here. So similarly 1 plus 1 again 2, and so on. Ultimately here we have 1 and this 0, so this is how we have. This is how we will find. So both are equal. So this is what they have written. When we do this minus x in case of our checked environment, we will of course be reverted. The transaction will raise an exception because it does not fit the positive range. But this works because minus x, as I told you, for this case is actually equivalent to that original number itself. Works, and the expression minus x when used in check mode result in a failing assertion, I have told you. Now regarding division, since the type of the result of an operation is always the type of one of the operands, this is the rule in Solidity, division on integers always result in an integer. In Solidity, division round towards 0. This means that minus 5 by 2, instead of being equal to minus 2.5, it will round down towards 0. So not minus 3 but minus 2. Note that in contrast, division on literals result in fraction values of arbitrary precision. We will see this later. This part, ignore for now, we will see this later. Division by 0 causes a panic error, and this cannot be disabled in unchecked environment. The expression this by minus 1, as I told you, this will overflow. So in unchecked you can use, but not in checked, is the only case where division causes an overflow. In checked arithmetic mode, this will cause a failing assertion, while in wrapping mode the value will be this. Next we have modulo operation in integer. The modulo operation, this a mod n yields the remainder r after the division of the operand a by the operand n, where q is int a / n and r is a minus n star q. If you look at this expression carefully, this means that modulo results in the same sign as its left operand. It could be 0. I mean, yeah, instead of, like, if it's positive negative, but it could also be 0. And a mod n is equal to this. This is a bit too algebraic thing, you need not bother about this. Holds for negative a. It seems obvious, but formal proof we need not bother about that. So remember all these operations that we are talking for integers. So under value types, under integers is where we are talking about these operations. So modulo for that. So you can see about various examples here. Look for this q value, since it is always rounding towards 0. Now to formally prove that the sign of r is same as sign of a, I have this written. Now sign of n star q is equals to sign of n into sign of q, which is equals to sign of n into sign of a by sign of n, which is therefore equal to sign of a. So one thing I have proven, that both these have the same sign. Now what is left to prove? That if the magnitude of this is less than magnitude of a, then the sign of r will be same as sign of a. So let us prove that also. And regarding this magnitude thing, kindly note these two properties, that magnitude of two numbers is equals to multiplication of magnitude of them individually. Similar is for division. Here b is, of course, for this second case, b cannot be 0. So now for this n star q is equals to n into this floor thing a by n, where I am defining this as rounding towards 0. Now as this thing is less than equal to a by n, because say 2 is less than equal to 2.5, right? So that how. So n into this, now n is getting cancelled, and therefore what remains is a. Therefore magnitude of n star q is less than equal to magnitude of a, and therefore from a we are subtracting something less than it, and which has the same sign as a. Then sign of r is indeed sign of a. And we can also from this note that the magnitude of r is less than equal to magnitude of a. So I hope this part is clear now. I think it would be better that we see some examples, and they have given 4 examples. So 5 divided by 2, quotient will be 2, and thus remainder will be 5 minus 2 into 2, 4. 5 minus 4 equals 1. So 5 divided by minus 2. In this case, quotient will be negative 2, and 5 minus negative 2 into negative 2, that would be 5 minus 4, which is 1. In case you got confused, let me write this for you. We had this 5 minus minus 2 into minus 2. So this is 5 minus 4, which is equals to 1. This is for this case. And this case, here also quotient will be minus 2. Basically, if you are confused about the sign of the quotient, just always do this. Suppose you are having this minus 5 divided by 2. You just find the answer by normal calculator. It will of course be negative. Minus 2 point something. It will be minus 2.5 by the way. So always find. So if it is 5 by minus 2, here also the quotient will be same, minus 2.5. So always find the quotient in decimal terms, that is in fractional, whatever it be, and then just round it towards 0. So in this case, rounding it towards 0, this will be equal to minus 2. So for this case, if we were to find the remainder, this will be minus 5 minus 2 into 2, which is equals to minus 5 plus 4 and is equals to minus 1. So I hope that clarifies about quotient. So, and then we have this case. Maybe I will do this case also quickly. Minus 5 divided by minus 2. This is equals to 5 by 2. This is equals to 2.5. So remainder is minus 5 minus of rounding it towards 0. This will be 2. I hope you understand this rounding towards 0 thing. This is 0. This is minus 2.5 and this is plus 2.5. So we have to find the closest integer when going towards 0. Okay. Yeah. So this is quotient into this minus 2. This is equals to minus 5 plus 4 is equals to minus 1. And I think that was the answer. Yeah. So modulo with 0 causes a panic error and this cannot be disabled through unchecked even. Now moving towards exponential, there is a slight confusion which you might have regarding exponential, in the sense that it is of for two cases we have. One is for integer type and one would be for literals, as we will see shortly. There is a slight difference in both of these with regard to solidity in exponential, which might lead to confusion. So you will have to read carefully so that there is no confusion. And that confusion is basically arriving by noting that this exponential is talked with regard to integer types, all these int types which we saw, and you can see this, that it is with regard to this integer type, whereas that is for literals, and we will see that. So exponential is only available for unsigned types in the exponent. When we do this a the power b, so this thing has to be unsigned. The resulting type of an exponential is always equal to the type of the base. This thing is called as base. Please take care that it is large enough to hold the result, otherwise it will revert. And prepare for potential assertion failures or wrapping behavior. In checked mode, there is this note: exponential only uses the comparatively cheap exp opcode for small cases. For the cases of x to the power 3, the expression might be cheaper, in the sense it, instead of doing x to the power 3 in EVM, x star x x star x might be cheaper. Like if you look at EVM, this exp thing, this takes a base and the exponent from these stacks, and output is this a the power that exponent, and you can see its gas cost is 10, and this also has additional dynamic gas cost. If I hover over the question mark sign, you can see, whereas in case of our multiplication, gas is comparatively cheap, and this does not have any dynamic cost. So in any case, the gas cost tests and the use of optimizer are advisable. Moving forward, note that 0 to the power 0 is defined by the EVM as 1. This is as such an indeterminate form. In case you have studied calculus, you might know, but anyways, EVM is defining it as 1. Now, regarding this fixed point numbers, it is best to ignore this because you can just declare them, but you cannot assign them any value. For instance, in Solidity you might write u fixed space variable name, but you cannot say that to be equal to anything, and nor can you use that value later. So it is best to completely ignore this section. If you read the warning, fixed point numbers are not fully supported by Solidity yet. They can be declared but cannot be assigned to or from. Moving forward, we have this address type. Now, if you study the address of Ethereum wallet, any Ethereum wallet, you will notice that it is a string of 40 hexadecimal characters. Since each hexadecimal character is 4 bits, 2 hexadecimal character make 1 byte. This is equivalent to saying that it has 20 bytes. Continuing, so the address type comes in 2 flavors which are largely identical. Address, which is normal address, holds a 20 byte value size of an Ethereum address. We have talked about it. And address payable, which is same as address but with additional members transfer and send. The idea behind this distinction is that address payable is an address you can send ether to, while you are not supposed to send ether to a plain address. Suppose I declare an address. If I declare some address payable some address is equals to, I give it some value. Currently I'm not planning to give it a value because address there is also something known as checksum. It has to pass that, so we'll see that later. Now if to this address I plan to send some ether, I'll do something like this: some addr dot send, and I'll put in the value, which will be an unsigned integer of 256 bits. But usually we use an Open Zeppelin library to help us with that. We will see that when we will be going through damn vulnerable DeFi problems. Continuing. If you need a variable of type address and plan to send ether to it, then you should declare it as address payable to make this requirement visible. Also try to make this distinction on conversion as early as possible. Otherwise you will have to explicitly convert it to address payable type. Explicit conversions to and from address are allowed for uint 160. If you notice carefully, address is of 20 bytes. Each byte is 8 bit. So 8 into 20 will be 160 bits. So you can convert it to an integer, an unsigned integer of size 160 bits. Integer literals, which we will cover shortly, and there is a bytes 20 type also, which is a 20, it holds 20 bytes, so that is also available. Also, explicit conversions from bytes 20 or any integer type to address result in address payable. They have mentioned this later, but I have mentioned it here so as to make comparisons easier. Okay, it also has some operators just like normal operators, which are very rarely used. There is a warning: if you convert a type that uses a larger byte size to an address, for example bytes 32, then the address is truncated. It will take the first 20 bytes. To reduce conversion ambiguity, version 0.4.24 and higher of the compiler force you to make the truncation explicit. You cannot implicitly do it. Like, there is two types of type conversions. One is implicit, one is explicit. For instance, if I were to explain you, if I have this u, just 1 second, u int 8 some variable z equals say var. Now if I do u int 16 some variable k equals z, then here this variable z is implicitly converted to this type uint16. It had the type of uint8, but since uint8 can easily fit inside uint16, there is this implicit conversion. We will talk about these implicit conversions in detail later. But for the bytes, but if I were to make it explicit, then I would have written this k is equals to, I'll write the full line. It will be uint 16 k equals to uint 16 z. Now I'm making this conversion explicit. Take for example 32 byte value. They have given a 32 byte which will be a sequence of 64 hexadecimal characters. You can use this. At first you take the first 20 bytes, which is here. You will take the first 20 bytes and then you can convert it. This was as such not required here. You could have converted to address anyways. Also notice there is some small and some capital. That is because of checksum. We will see that. Or you can use this uint 256b. Now if this is considered as an integer, then this is the first 20 bytes will be taken from here. This is how integers are stored, and but bytes are stored in a different manner. For bytes, they like the address slots which the bytes occupy, they start from here for the bytes 20 type, but in case for the integer it will start from here. So if they do like this uint 256, then they are taking this bytes. Here this was necessary to truncate it, but here this was not needed. Since you can see that when we do bytes 20b and when we do uint 256b, we are getting different output. That is why this this conversion has been made explicit now. That is my assumption. So now talking about members of address. If I open this link, members of address type, you can see we have various different members. Balance to get the, if I want the balance of say this address, if I have some address, if I want its balance, I can simply do sum dot balance. I have to call this. They have mentioned in parenthesis this uint 256. It does not take any input. You just type this dot balance. It's not a function. You don't do like this. You just do like this and you will get the balance of that, which will be this uint 256. It will return a uint 256 value. Similarly, code you can use, which is again not a function but will return you a bytes memory, and code hash will return you the hash of this code. It is better if you want the hash, better you use this instead of first getting this and then computing its hash. By the way, this will be your EVM bytecode, which the code will return, obviously. And this hash is the Ketchuk 256 hash. For example of balance and transfer, you can see they have given an example, address payable X. So that means you can send something to this address X. They have given it some dummy value. Address, my address is equals to address this. If you want the address of the contract, like contract will be running this code, right? So that address you can simply get like this by typecasting this variable to address. So if the person you are going to send has the balance of less than 10 and your balance is greater than equal to 10, then you can do this transfer. This 10 is not 10 ether but 10v here. We will be playing with these things a lot when we will be doing damn vulnerable DeFi problems. The transfer function fails if the balance of the current contract is not large enough, or if the ether transfer is rejected by the receiving account. There could be various reasons. We will discuss some of these reasons later. The transfer function reverts on failure. Basically, it will raise an exception when it encounters a failure. Regarding this note, we'll go through this note, but we will explain this later when in other sections. So if X is a contract address, its code is this X could be externally owned account or it could be a contract account. When we send the ether to a contract account, then its code, more specifically its receive ether function, and if this receive ether function is not present, then there is this fallback function. We will discuss them later, but we will just read this now. If it might not make sense now, but I will cover this later. Will be executed together with the transfer call. This is the feature of EVM and cannot be prevented. If that execution runs out of gas or fails in any way, the ether transfer will be reverted, and the current contract will stop with an exception. It will bubble. It will the caller will then receive the exception call, and it is up to the caller what it wants to do. It can either bubble it up or catch it and do something else. Send is the low level counterpart of transfer, main difference being it does not raise the exception. If the execution fails, the current contract will not stop with an exception, but send will return a false. It will you can then use this true false value to determine what you want to do. And they have given this warning. It is very important for you to have a clear understanding of what this warning is saying. So let me first read it. There are some dangers in using send. The transfer fails if the call stack depth is at 1024. This can always be forced by the caller, and it also fails if the recipient runs out of gas. So let me break this down. Firstly, regarding this call stack, we have covered stack in EVM, but that one is different from this call stack. That one is also called as expression stack, whereas if I show you, this is the Ethereum yellow paper, and here if we notice in the execution environment, there is also this, the depth of the present message call or contract creation, that is the number of calls or creators being executed at present. Basically, just understand that we have one more stack for this purpose. Like in case of message call also, in the case of executing a message call, several parameters are required, one of them being this, the present depth of the message call contract creation stack. So it turns out that this stack also has the maximum limit of 1024, just like our expression stack. So each time I'm calling some function, this is getting incremented, and this can always be forced by the caller, meaning, let me now give you an example. Suppose, suppose there is this function, a solidity function, in which we are having some lines, and one of them line is sending something to an address, some address variable. It is sending some amount to this. Fine, some amount. I'm not putting exactly what amount. Now suppose I have another contract which is deployed by an attacker. This attacker is an independent contract besides the contract containing this function. Now this attacker will have a function, say by the name of attack, and the attacker can first of all recursively call some functions until the call stack depth is close to 1024, slightly less but very large, and then it will call this function, which is what he or she is planning to attack. Now in that function, since the call stack depth is already very high, sufficiently high, so that this function will fail. Dot send function will fail because this is also going to increment the call stack depth, but the limit will be crossed and this will fail. And then I'm going to execute, the function will be executing other lines. But if I have not properly addressed this attack vector, then I would be assuming that this has been successful, whereas this would have returned fail. And if I'm not putting it in some if statement, like if, better would have been, instead of having it alone like this, I should have put it in an if statement, that address var dot send, so that if this is equals to false, then I should do something. I should have handled that case also. But I have given you an example where this can fail, and which is when the call stack depth is sufficiently high so that when calling this function, it overflows. Also notice that instead of send, if I would have used transfer function, then it would have raised an exception. So instead of just having this thing return false, instead of send, if I would have used transfer, then it would have raised an exception. I would have been out from this function. So transfer as such is more safe. Now regarding also this if thing, I haven't explained you this if. Basically if is simply that if what is inside the parenthesis is true, then you execute this function, something which is present inside that code block. So here, if this is returning false, so false is equals to false. So when I do false equal to false, then this expression is true. So this would have been true and I would have been able to handle this properly. Now going back to what they have written, the transfer fails if the call stack depth is at 1024. I have shown you, and I have also showed you how caller can achieve this. And it also fails if the recipient runs out of gas. That is obvious for you. So in order to make safe ether transfers, always check the return value of send. Like I showed you here, we should have checked the return value of send in some if statement type of thing. Or using transfer is better because it would have raised an exception. You might have some specific need of send, that is up to you, but transfer would have raised exception instead of returning false. Or even better, use a pattern where the recipient withdraws the money. Here, inside this function, I was doing various things. I might have been modifying some of my variables, and I'm also sending value to some address and doing the remaining things. Better would have been that I would have isolated this thing, this send part. Like I think I should then also tell you about this. Let me show you an example. So now let us look at this Solidity program, which I have taken from their official documentation. Here in this Solidity by example, there is this section. And this is the example which I have taken. It might look big, but actually it's very small. And with this example, I will also show one more vulnerability. So let us understand this example. It is a bidding. Suppose I am the beneficiary. I'm going to put one item for auction. You all people will be putting your bids on it, and the highest bidder will get that item by paying me the amount, the bid amount. So when I'm deploying this contract, there are two variables which I'm setting. Beneficiary, which is declared here, which is of type address beneficiary. These keywords, public, etc., you might not understand, but just understand the semantics which I'm explaining you now. So I have this variable declared beneficiary. To that I'm assigning it this value, which at the time when I'm deploying this contract, I'm going to pass in two inputs. One of it will be my address, because I am the one putting the item on auction. One of them is the bidding time. What is bidding time? It is the interval. Suppose I am putting the item for auction now. I want it to end in say 1 day. After 1 day, auction completes, the highest bidder will get it. So that is the bidding time. So auction end time will be the time the contract is deployed plus this bidding time. And the current time is obtained from this. It is the global variable which we can access. We'll talk about these global variables. It is the timestamp of the current block. So when I'm deploying this contract, I have assigned these two values. Here I have inserted that same contract in Remix, and you can see when I'm about to deploy this contract, it is asking me two parameters, which is what is this bidding time and beneficiary address, as I have told you. Now in this smart contract, let me show you this auction end function. So we will call this auction end function. If the auction end time has not yet been reached, then we are going to revert with this error that auction not yet ended, auction is still going on. And if we have already called this function successfully in the past, because then we will be making this variable true, which was initially false. So if we have already called this function successfully, auction end already called, we are reverting with this error, this exception. Else we will end this and make this variable true. This part, this emit thing, basically you can ignore this for now. This is sending a signal to the front end that auction has been ended. The highest bidder was this and the amount was this highest bid. You can ignore this for now. Then the beneficiary, which was me in this case, when I was explaining you that we assigned this beneficiary here when deploying this contract. To the beneficiary, we are transferring this highest bid amount which was paid. After understanding this function, let me explain you this bidding function, how the participants will bid on this. This is a payable function which would understand for now imply then the design of this smart contract is when the person is bidding, he or she will transfer the amount to. Amount will also be transferred. So only serious bidders are allowed here. So when we are inside this function, if the auction has already ended, we are going to revert that the time has gone for auction. Now, if this message.value is basically telling the amount of V which the participant sent for bid. So if the participant's bid value is less than or equal to the highest bid which the other participants have already, which one of the other participant has done, then we are going to revert with the error saying that your bid is not high enough because we have this bid already. Then if the highest bid is not equal to 0, basically when we have reached this point of line, that means that the current bidder's bid is higher than the previous bidder's bid. Also, as the initial value of all the variables is 0 by default, like here we have this highest bid variable, it has the value of 0 by default. So if it is not equal to 0, that means somebody in past already paid. Somebody in past already paid to our smart contract, because if somebody was say putting the bid value of 0 itself, then 0 would be less than equal to 0 and we would have reverted. So somebody has paid to us and we are saying that somebody which was the highest bidder, we have to return the amount. Suppose in future this highest bidder which may bid more high amount, say some competitor put the higher bid and then he or she is forced to put even a higher bid. In that case, we that is why we are doing plus equal to here, not a simple assignment. So because each time when he is putting the bid, he or she is actually paying the smart contract. So we have to add all of those up. Okay, now we are updating our highest bidder to the message.sender is basically who called this bid function, the current bidder's address. Highest bid is the value which he sent, and this is again linking to our front end that this person gave this value, highest bid increased. This is just the front end thing. Now here is the catch. If instead of first let me before basically we want to return to the previous bidders, right? Once their bid has been crossed, we want to return their funds. But if we would have done this here, then we won't call it withdrawal pattern. If we would have done that here, then it is possible that the person whom we are sending the amount, that entity could be a contract itself. We are not verifying what it is. It could be a contract itself, and it is possible that that contract, whenever somebody sends funds to it, it might raise an exception. It is possible that the smart contract will always raise an exception when somebody is sending funds to it. So in that case, this will be blocked because exception would have been raised, and in this case nobody will be able to place a higher bid, and that bidder would have won. So this is like a denial of service type of attack. So this is why withdrawal pattern is preferred. Withdrawal pattern basically means instead of sending the funds here, we have isolated that withdrawal part where the where the caller can receive his funds. So if the bidder wants to receive his cancelled bid funds, he can call this function, and here this pending returns, which was this basically this is a map. Just like how storage is key value, for every key we have a value. Similarly, map is like this only. For every key we have the value. So pending returns for that address, this is the amount. If the amount was greater than 0, basic check that yes, the persons we need to give his funds back. So we update it to 0, and then we send it. And in case the send failed, we would have reverted these things which we did from 0 back to the amount, and we are going to return false, that you were unable to withdraw. Otherwise we are going to return true. The simple if statements, I haven't talked about them in detail, but I have as such explained that if something inside this parenthesis is true, only then execute this block. Else there is no else statement here. Once this block is done or not done, we follow up with the next line. So I hope I have explained you this. You can yourself also go through this smart contract from that example. So this is the withdrawal pattern where we are isolating the withdrawal part, this send part. Also, one more thing which I would like to add about this transfer and send, that they forward 2300 gas, which is not adjustable. That is, you cannot adjust it to some other value, say 2400 or 1900. It will be 2300 only. And similarly for send, it will forward 2300 gas only. Also when we do some other function calls, say I'm calling some function G of some contract C, then in that case I have an option to specify how much gas I want to forward. We will see that later. But in case I'm not specifying anything, then by default it will forward 63 by 64th of the gas which is currently available to the caller. This is something which we will see also later, so don't worry if it's not clear now. But for this send and transfer, understand it that only 2300 gas is forwarded and you cannot adjust it. Moving forward, let us now read about this call, delegate call and static call methods which the address type has. In order to interface with contracts that do not adhere to the ABI, or to get more direct control over the encoding, the functions call, delegate call and static call are provided. Now with regard to this line, I will first like to explain how do we call function of some external contract in Solidity? From my experience, I have seen 3 methods, and they mostly rely heavily on ABI. That is, they adhere to ABI. What is ABI will become clear when we do the example. Then I'll go over that too. So one of the example which I wrote for you is this. I have this simple contract called functions. It is having only one function, namely sum, whose job is to take as an input 2 integer and return their sum. So it takes the input as 2 integer. It is going to return an integer which is their sum. Ignore this external and pure for now. When we will do functions in detail, then we will understand these terms. Now, suppose I am some other contract, then how do I call this function of this contract? We already saw some part of it when we were doing this EVM deep dive by Knox. When in Solidity, here are 3 ways which you can call that function. I have made a contract by name call functions, whose job will be to call this function inside this functions contract. So the very first method, if I were to tell you, this will be my first method. How do we do this? We declare an interface. What is interface? Need not bother by now, but just understand the English meaning of this, literal meaning of this word interface. Think of it like that. Of this function interface by the name of functions, where I am just given the syntax of the sum function, not the definition. This was the sum function. Basically, I have copied this part and pasted it here. Now, when I am deploying this contract, I will give the address of the already deployed functions contract. For instance, like if I close all this, here are my different contracts. If I save this file, so this functions contract, I will deploy it. Now this function contract is deployed at this address. Fine. I'm going to copy this address. Now I'm going to save this and deploy this address. But when I'm deploying this address as my constructor is like the initial thing. A Solidity file, a contract can only have one constructor, and constructor will initialize this contract. So I have few of these variables, hyphen variable, fun variable, and functions variable. To initialize them, this constructor is taking an input, this address, which in my understanding is the address of the already deployed functions contract. So I'm going to put that address here. This function call function, putting its address here, and I'm going to deploy it. Now I have deployed it. Inside this constructor, I'm going to make a typecast to this address as a iFunctions, which is my interface. Ignore these two part. I will explain them later. Now I have this function getSum, which will take as an input 2 integers, and first it will compute its sum. Then it will verify whether the sum function is being called here or not. Because if it is equal to my sum, that means it was being successfully called. So I simply called it using this -.sum. Here the cool thing about using interface was there was no need for me to write the complete contract. Even if this contract had various sums, various functions. For instance, if I had this function sub, even then, and I want to call only the sum function. I don't care about this subtract function. I only want to call the summation function. even then this is valid. I need not write here about sub function. No, only what I want to call I can specify here. So this is cool thing when using about interface. So this was the first method. Now the second method is that you write the complete contract here in this file. Either you write the complete contract or you import it. Like here I could have imported this file since it was in the same directory. This will imply same directory and then the file name. I could have either imported it like this or I could have copy pasted the complete contract here, and then I have declared a variable of this contract type. Yes, contract types also exist. So I have declared a variable of this contract type, and then when I have received the address, I am typecasting it. Basically, now since there are two things, when I have the contract, I can get its address using this address and the contract name. This will give me the address of the contract. And if I have the address, I can typecast it to its contract type. Then I can also then again call like this. But as you know, as you can see that here we needed to write the complete contract or we needed to import it, and as such better way would have been this interface. As such, both the first two methods, the method 1 using interface and method 2 having the whole contract imported, are as such same, because in the second method also the purpose was to know the interface. Just like contracts, there is also something known as abstract contract. We will see that later, this abstract contract, and that could also be used. So all these three things, interface, contract or abstract contract, the purpose when using them is to know the interface itself. And the third method where all of this is not needed is this. We declare an address of type functions and we have its value here. Then we are using this call method, which is what being talked about here, this call method. And then here is the ABI part. We are encoding with signature. I will explain this. The function which I want to call, I type it like this, its name, then all its type, I write them fully. I just don't write int, I write int 256, comma, I don't put here space, and I continue like this, and then the input values which I want. What does this ABI dot encode with signature does? We have, like, if I just do ABI dot encode and then if I do a comma b, what this does is like when we send data to interact with some other smart contract, that data need to be encoded, and depending upon the convention, since we are adhering to ABI in this example, we are encoding it via the ABI scheme. So what this will return is, it will return a long hexadecimal number. The first 32 bytes will represent the integer a, and the next 32 bytes will represent the integer b. So total 64 bytes. If this a variable was of type integer, which is 256 bits, I wonder whether I told you, but int is an alias for int 256. So instead of being 256 bit long, if a was say int 8, even then this total will be 64 bytes, because ABI encodes them in a multiple of 32 bytes. So the first 32 bytes will be for a itself, the leftmost bits will be 0, the last 8 bits will represent a and b, I told. Now what this encode with signature is doing, I told you about the signature. How do we find its hash? We take the first 4 bytes of the catcheck hash of when the name is put like this, As you can read in that Knox article, function signature are defined as the first 4 bytes of the ketchup hash of the canonical representation of the function signature, and canonical representation of the function signature is the function name along with the function argument types. So in that example which the author was referring, the input is like this. In my example, I have told you how do I put it like this. So encode this along with signature. That is what encode with signature does. Like if you read the official Solidity documentation about ABI, this ABI first let us see encode with selector, which take the first 4 bytes as selector, and then ABI encodes the given arguments starting from the second. This second from the second input is what is being talked about here, and prepends it with this thing. Now what does encode with signature does? It is equivalent to this first this only ABI encode with selector, where they take this string and do that what I told you about catch-check hash and take its first 4 bytes. Here they are typecasting it to bytes. We will see its meaning later. So I hope this you got. Now let us discuss about this ABI. I will finish this later. Now when we deploy our smart contract, for instance this functions contract, if you look at its ABI, if you look at its bytecode, this is functions and here will be its bytecode. Just give me 1 second. This is its bytecode, and as such we cannot make sense out of it. It is difficult for us to know how do we call the function. And now if this smart contract is following the ABI convention, then I know that to call the function, what ABI wants is that you specify the first 4 bytes of the function signature. You specify function signature, and then we saw how the contract tries to match and go to that function. So this happened because our smart contract was following that convention, and that convention is what you can think of as an ABI. Let us now develop on this idea further. So here I am calling this call method, passing in the data, the payload, the way I know that my compiled smart contract's bytecode expects. This contract's bytecode is expecting an ABI convention, so hence I am passing the data using that. And what this will return as bytes. There is something bytes as the normal bytes which we have studied. That is what is returned by encode with signature. Like here you can see that it returns bytes. Ignore this memory keyword for now. Just focus on this bytes, that it is returning the bytes. I will cover the bytes data type later. Just understand it to be the usual bytes which I have explained you previously. Alright. This call method of the address expects that you give it the bytes which we have given. And now what it returns? It returns 2 values. The first value I have completely ignored because I don't need that value. But the first value is a boolean telling me whether it was success or failure, whether the call went through or there was some error encountered. And the second output is the bytes, basically the return data that I got. In my case, my return data should be the sum, but it is again encoded. I need to decode it back. So there is this method, from method I mean function. So there is this decode function in ABI in Solidity. I am passing it this bytes which is return data, and I am telling the ABI decoder that decode it assuming that it is an int type. Basically there could be multiple function. A single function can return multiple types, multiple values. So suppose this sum function could have it is possible for a function to return maybe an int and a string. So in that case, that is what I will mention here. This in parenthesis, you tell the values all which you want to decode. For instance, if the function was returning two integers, and that then I can get those two integers like this. I can simply say that a comma b, sum a sum b is equals to abi dot decode return data if the return data had two integers. That is how I can get it, where I had previously declared these two variables. Alright, I think this makes sense. So that is what I have done. I have decoded it to get the integer value, and I am verifying that yes, that integer is equal to the sum. So yes, my call went through successfully and has worked as expected. But all this happened because we were assuming the ABI convention. If the deployed byte code doesn't follow this convention, even then you can use this call. You won't be able to use these other methods, other ways which I told, because they were relying on ABI. But you can use this call because this is a low level provision provided by Solidity, where it will call to that function with this data payload, and this could be anything. If the deployed byte code is assuming some other convention, then you can put in that convention here. So I hope you understood about ABI. Let me go through some of the answers when somebody asked about ABI. So maybe these answers will give you more insights. So let me go through them. ABI stands for Application Binary Interface. In general, an ABI is the interface between two program modules, one of which is often at the level of machine code, in our case bytecode. The interface is de facto method for encoding decoding data into out of the machine code. I think with my example this line is making sense to you. In Ethereum, it's basically how you can encode Solidity contract calls for the EVM, and backwards how to read data out of transactions. And there is this other answer. You can also see that. I suggest you to go through this answer also, and you can look for this question in Stack Exchange. Continuing here, so in order to interface with contracts that do not adhere to API, or to get more direct control over the encoding, the functions call, delegate call, and static call are provided. I have explained you in detail by going through the example for the call case. They all take a single bytes memory parameter. I told you that they took bytes as an input parameter. But what is the use of this memory keyword is something will be explained later. Parameter, and returns the success condition. The first output will be the success condition, and the return data will be the second output. I mean, it will be a single output containing these two values. So like here, the first value and the second value. The functions abi.encode, encode packed, encode with selector, and encode with signature can be used to encode structured data, as we saw. They have this example where they got the payload by encoding with signature just like we did, and then they called it to this address. Okay. This warning you need not read. What they are just saying simply is that when you call some other function, maybe to explain this now, it is better that when we will see a reentrancy example, something known as reentrancy, and then this will become clear that how malicious things happen. We need not bother about this at this stage. And don't worry, whenever I say that something we will do later, we will do it later. I have everything noted down. Continuing, it is possible to adjust the supplied gas with gas modifier. Basically, when you are calling, you can specify exactly how much gas you want to forward from your own quota. So yeah, this is what they're doing. And also, if the function can accept ether, we will see how to make a function accept ether. So in that case, you can put that value also, and these two can be combined in any order, like gas this, value this. Either you could have written first value then gas, it should not matter. The order does not matter. Also, in this call, if you don't explicitly specify the gas, then by default it will forward 63 by 64th of the available gas. Continuing further, we have delegate call, and this is something I will cover as soon as I have covered libraries. So first let me cover the libraries and then I'm going to come back to this delegate call. So for now we will be skipping this. Since Byzantinium and Ethereum upgrade named Byzantinium, so once that upgrade happened, static call can be used as well. This is basically same as call but will revert if the called function modifies the state in any way. What is this state? This is the state of the entire network, entire blockchain. So to show you the example so that it is clear to you, I have this contract with name static call target in which I am declaring a state variable. I haven't talked about state variable till now. The thing is, the variables you can see here which is declared within the contract but are outside any further nested blocks, for instance say outside these functions, but inside the contract are by default stored in storage and therefore we call them state variables. As such, when we say some variable as state variable, that means that variable is stored in storage. So any variable which is part of the contract's storage is said to be state variable. Once we will cover various types etc., then this idea will become more clear. I will also formally show you the state variable definition which is present in the documentation later. So this is stored in our persistent storage, and this is what is our state variable. So I have one function named change state var which will take in the new integer and update my this variable with that new integer. Pretty simple. And similarly there is another function which will take an integer and return its value plus 5. It is not modifying my this variable and hence it is not changing the state. So this contract is named static call target. I have this another contract with the name static call. Inside it I have this function with name static call. This will take the target address to which we will call this method. Ignore this external view. So I am doing this static call. This will again return two things. One is a boolean denoting whether the call successfully went through or not, and the other is return data. I am ignoring this return data and hence I am not put up any value here. Now this should fail if it is calling that change state variable function, because static call does not allow any modification to state of the network, state of the blockchain you can say. So I expect this. Here I am also passing the integer value too. I am typecasting it to integer. So I expect this call to fail, and if it has failed then this assert will pass. Similarly I am doing another call. This, by the way, this target is the address of this contract. This is what I will pass. Similarly I am doing another call, but for that other function, doesn't change state variable function, and this should pass. So yes, if it passes, this assert will be verified. It will successfully hold this assert statement that success2 is equal to true. This is for equality sign. Single, by the way, maybe the single equal is for assignment and double equal is for equality. For the boolean types we have seen the comparison operators. Okay, now I'm going to decode this return data to see that yes, 5 plus 2 is indeed 7. Yes, everything worked correctly. So for this, let me first deploy this contract static call target. I have deployed. I will copy its address and static call. This also I'm going to now deploy. And for this static call, I'm going to call this function static call, passing in the address of the target contract. So if after pressing this button there is no revert, then it means everything happened successfully. So yes, there is no revert, so all our operations were successful. So this is static call. All three functions, call, delegate call and static call, are very low level functions and should only be used as a last resort, as they break the type safety of Solidity. Here, as you see, compared to calling the function by the other method which I told you, having interface or contract imported, that time we will not passing any data here. Basically this is just a data and it need not correspond to actual function. For instance, I might do some thing like this. Instead of it being int, I might make it u int, and if I save it, I get no warning, no error. Whereas in our interface example, if I make it unsigned integer, say unsigned integer having value 2, you see I get an error. So this is what I feel that they meant by this type safety. The gas option is available on all three methods, while the value option is only available on call. Note, it is best to avoid relying on hard-coded gas values in your smart contract, regardless of whether state is read from or written to, as this can have many pitfalls. Also, access to gas might change in future. One of the pitfall being this itself, that the gas access to gas might change, and these opcodes which we are using, even their cost might change in future. So yeah, it's best to avoid it. Code and code hash I covered. All contracts can be converted to address type, I showed you. So it is possible to query the balance of the current contract using this. This we have discussed. Now reading about these contract types. Every contract defines its own type. You can implicitly convert contracts to contract they inherit from. Contracts can be explicitly converted to and from the address type. This to and from the address type, we have done various examples for it. Every contract defines its own type. We have seen that also when we did this call function. I declared this variable fun, which is of this type contract. I could have declared multiple variables too. Alright. And you can implicitly convert contracts to contract they inherit from. This is something we will see when we will be doing inheritance. Explicit conversions to and from address payable type is only possible if the contract type has a receive or payable fallback function. There is this keyword receive and fallback, payable fallback, that too. If either of these two functions are present, we will see what they are later, but if either of these two functions are present, that means contract can accept ether. So when we convert it using this address and I put in the value of the address of that contract, then I will get an address payable. Similarly, other way also, from address payable I can get a contract type, like what we have seen previously in our examples. Instead we do like this only. You might think that here we need to do address space payable. No, not like that. Simple address. Previously also, when I was covering address, let me show you. Let me see where I can find it. Yeah. That explicit conversion from bytes 20 or any integer type to address results in address payable. Okay. So there is this subtle detail when you get a address payable type. But in case this is not possible, that contract does not have a receive or payable fallback function, and you somehow still need address payable type, you can of course go via this route. So if the contract type does not have a receive or payable fallback function, the conversion to address payable can be done using this, because any address you can first this will give you the address, and then you can explicitly convert it to address payable like this. This is possible for any address. Okay. This note is not of our relevance. So if you declare a local variable of contract type, like we did previously also, you can call functions on that contract. Take care to assign it from somewhere that is the same contract type. Basically, in this, when I'm doing this assignment, I should assign it when it is of same contract type only. So that is the caution which one has to take. You can also instantiate contracts, which means they are newly created. You can find more details in the contract via new section. How to create new contract using contracts, we will see that in this section when we will be covering that. The data representation of a contract is identical to that of an address type, and this type is also used in the ABI. Since the data representation is identical, that is why we could convert from address to contract and contract to address. And this type is also used in the ABI. Like if I show you, this is the ABI specification page in the Solidity documentation, and you can see mapping Solidity to ABI types. The following table shows on the left column Solidity types that are not part of the ABI, and on the right column the ABI types that represent them. So for address payable, which is not in ABI, we get address. For contract also we have address. So this is why they have said that, in my understanding, that this type is also used in the ABI. Contracts do not support any operators, so you cannot do equal to, plus, minus like that. The members of contract types are the external functions of the contract, including any state variable marked as public. By the way, in case you know about public functions are also included when they say external functions. And this is something will become obvious when we will see about functions. Basically, when you call a function in a contract, you can call only those functions which are external. Public functions are also external. And when the variable is marked as public, then the Solidity generates something known as getter function, which also has external visibility. We will see that, and then this will become crystal clear. For a contract C, you can use type C to access type information about the contract. This is something which won't be clear to you by reading this. So I have this about everything about this type information. The expression type X can be used to retrieve information about the type X, but currently there is limited support for this feature, as X can be either a contract or an integer type. So only when X is an integer or a contract is when you can use this type X to access type information. When X is a contract, then it has these things. You can read about them if you feel they are of use to you. And for an integer, we already saw that we can find the minimum and maximum. Only these two it has. Anything which is an integer can also, for that also you can use type X. Like there is a type known as enum, enum. We will see that shortly. So for that also, since it is an integer itself, so for that also you can use this type that to get its minimum and maximum value. We will see that. This is the word I just said, enum. Alright. Continuing further, we have this fixed size byte arrays. These are value types. This bytes 1, bytes 2, bytes 3, so on till bytes 32. These are value types. I told about value types and reference time at the very beginning. So these are also value types. I mean, we are in value types itself. All these address, integer, booleans, etc. All that is here is value type. Once we'll reach reference type, and I told you only 3 reference types are there: struct, array, and mapping. Now where was I? Okay, here, fixed size byte array. So bytes 1, bytes 2, bytes 3, bytes 32 hold a sequence of bytes from 1 up to 32. I think it is clear in itself. And it has these operators, arithmetic operators are there along with comparison operators too, where these above ones are the comparison operators and this left shift right shift are the arithmetic operator, this bit also, but I don't see plus minus here, so you cannot apparently add two byte arrays or subtract things like that. Index access, if x is of type bytes I, then you can access the kth byte, where k of course goes from 0 including 0 but less than I, and it will return the kth byte. When we will see an example of this, it will become clear. The shifting operator works with an unsigned integer type as the right operand, just like how it was for our integers, but it returns the type of the left operand just like integers, which denotes the number of bits to shift by. Shifting by a signed type will produce a compilation error. There is a member in this dot length which yields a fixed length of the byte array, which is a read only. Basically, for if I have a variable of type say bytes 3, and in that variable if I do dot length, I will get the answer as 3. Like here I have an example for you. I have a simple contract named bytes where I have this variable b3 of which is of type bytes 3. Basically it will have 3 bytes. By default it is initialized to 0. That is, all 3 bytes will be 0. I have this function get b3 length which will give me its length, and I have told you the output will be 3. So if I deploy this, run this function, I am getting the output as 3. Here 0 denotes the first output. Now I have modified that example. Also by mistake I wrote that it will have default value of 0x000, only 3 zeros. Since 1 byte is 2 hexadecimal characters, I should have put there 6 zeros. So I have corrected that now. Assuming this has value this, now the 0th byte will be this one. First byte, index 0th byte will be this one. Index first byte will be this, and index second byte will be this. In computer science, you will usually see that we start from 0 instead of starting from 1. Even the set of natural numbers, in case you will see computer science books, they will also include 0 in that. So this first byte should give me this 0x12, and the index access returns the bytes 1 type. So let me deploy this and see whether it works. Okay, deployed. Now getting the first byte function I'm going to run, and yes, it has run successfully and I'm getting the output as expected. Continuing, the type bytes1 array is an array of bytes, but due to padding rule it wastes 31 bytes of space for each element, except when you put it in storage. It is better to use bytes type instead. Now except in storage, because this is a reference type, this thing is possible to put it in storage. This in itself I don't want to explain now. I will explain it as soon as we do arrays. Moving on, we have this dynamically sized byte arrays. These are actually reference types, both these bytes and string, and we will see them later. But you can see the description: bytes, dynamically sized byte array, see arrays below. Then string, dynamically sized UTF-8 encoded string, you can see arrays below. These both are not a value type. Now we have address literals, hexadecimal literals that pass the address checksum test. Now there is something known as address checksum test, and they have explained it here. If you open this link, you can read about this mixed case address checksum. So basically you see some capital A, sometimes small hexadecimal characters, sometimes capital. This is because of that checksum. You can read about it in this link. Hexadecimal literals that are between 39 and 41 digits long and do not pass the checksum test produce an error. even if they are, address literal is always 40 digits long. It can never be 39 or 41. It is exactly 40 hexadecimal digits. But when you are assigning some address and hexadecimal literal of 39 digits, then the compiler will assume that you might have done some silly error. For instance, I asked about this and the author has replied, like here you see, try appending a single digit at the end of the address from the example, you'll get this error. Since it will be 41 digits long, this is the error. This looks like an address but is not exactly 40 hexadecimal digit. If this is not used as an address, please prepend 00. For more information, see this. And if you append one more character, making it 42 digits, that error will be type something 43 digits, whatever they omitted, and is not implicitly convertible to expected type address. So for the 42, they thought that it's a clear cut error, that you did not mean address. But for 39 to 41, the compiler will think that you meant address. So basically the compiler assumes that 39 or 41 digit hex integers could be mistyped addresses and adapts the error message to that. So I hope it is clear. And you can of course prepend or append to remove the error. So that's it. Moving on to rational and integer literals. Integer literals are formed from the sequence of digits in the range 0 to 9. They are interpreted as decimals. For example, mean in the decimal notation, the usual number system which we work with. For example, 69 means 69. Octal literals do not exist in Solidity and leading zeros are invalid. So octal literals, just like we have binary, there is something known as octal. So need not bother about it, though we have hexadecimal in Solidity. Leading zeros are invalid means, as you can see in this example, I just declared this variable int no leading zeros, though, so the starting digit should not be 0. The trail should not begin from 0 sequences. Decimal fractional literals are formed by a dot with at least one number on one side. Examples include 1.1 and 1.3. So these will all be fractional literals. Scientific notation in the form of 2e10 is also supported, where the mantissa can be fractional, but the exponent has to be an integer. The literal me capital E is equivalent to m times 10 the power e. Examples include this, as you can see. All these are valid. Underscores can be used to separate the digits of a numeric literal to aid readability. Sometimes you will see in audits which the firms do that make your variables more readable by including these underscores or use scientific notation like that. So instead of writing an 18 digit number, or say instead of writing 10 the power 18 in an expanded form, better to use scientific notation having 10e18. Sorry, 1e18, because 1e18 will translate to 1 times 10 the power 18. So yeah, usually 1 ether you can easily write it to be 1e18, as we will see when we do some problems in that damn vulnerable DeFi. Capture the flag. Alright. For example, decimal 1, 2, 3, hexadecimal, this, scientific decimal notation, these are all valid. Underscores are only allowed between two digits and only one consecutive underscore is allowed. There is no additional semantic meaning added to a number literal containing underscores. The underscores are simply ignored by the compiler. Number literal expressions retain arbitrary precision until they are converted to a non-literal type. That is, by using them together with anything else than a number literal expression like Boolean literals, or by explicit conversions. Instead of Boolean literals, there could be some type variable also like int 8, int 16, which we have seen before. Whenever that is encountered, they are converted to a non-literal type, and we will see examples of that too. This means that computations do not overflow since they have arbitrary precision, and divisions do not truncate in the number literal expressions. For example, to the power 800. This is not possible in our int type because that an unsigned integer of 256 bits can hold the maximum value to the power, as we saw, which was to the power 256 minus 1 if I remember correct. So to the power 800 plus 1 minus to the power 800 is valid even though the intermediate results will not fit the machine word size, which is 32 bytes. Furthermore, 0.5 times 8 results in the integer 4, although non-integers were used in between. Moving on, they have this warning. While most operators produce a literal expression when applied to literals, like this plus operator was producing a literal expression because both were literals itself, there are certain operators that do not follow this pattern, namely ternary operator and array subscript. You might expect expressions like 255 plus true this or this to be equivalent to using the literal 256 directly, but in fact they are computed within the type uint 8 and can overflow. So here this ternary expression, we expected that it will return a literal expression, but instead of returning a literal expression, it returned the smallest type in which this could fit. An unsigned integer of 8 bits is considered smaller than signed counterpart, so an unsigned integer of signed 8 bits was used. Now when this is returning an unsigned integer of sign of 8 bit size and doing plus with a literal expression, then this 255 will get typecasted to this uint 8. This typecasting rules why this conversion is happening we will see at the very last, but when a literal expression is combined with a type, then it has to convert to that type. So this is also uint 8, that was also uint 8, but we saw that uint 8 can hold maximum of 255, so 255 plus 1 would overflow in that case. Similarly for array, telling a bit more about ternary expression, as we saw it is of this form: expression 1 question mark, expression 2 colon, expression 3. Now if expression 1, it must return either true or false. If it returns true, then expression 2 will be evaluated and its value would be returned. But if it evaluates false, this expression 1, then expression 3 will be evaluated and its value will be returned, and of course the return type of both expression 2 and expression 3 have to be same. Continuing, any operator that can be applied to integers can also be applied to number literal expressions as long as the operands are integers. If any of the two operand is fractional, bit operations are disallowed and exponentiation is disallowed if the exponent is fractional, because that might result in a non-rational number. Now here is a catch. Now in case when we were discussing about integers, in that we told that exponent should be an unsigned integer, whereas here the exponent can be signed. Like I had this comment in my notes. Yeah, if I show you, 1 raised to the power minus 1 is valid, but not because this is literal expression. Both are literal and exponentiation is then happening on these literal expressions, but not int 1 raised to the power minus 1, because the base here is now integer, and for integer the exponent has to be unsigned. Now I have this example to show you. Just to confirm what we have studied, I have declared this variable x but I'm doing 1 raised to the power a negative number. Now 1 raised to the power minus 1 is simply 1 by 1, which is equal to 1 itself. So this will fit in an integer and thus it is valid. Negative is allowed because it is literal expression, both left hand and right hand side. There, now here I'm doing simple y example just to to explain the very basic exponentiation also. Now this thing 2 raised to the power minus 2, this will result in a fractional number, a rational number, that 2. Now this cannot fit in our integer, so I have used this u fixed 8 cross 2, and because of that I am getting this error that this is not yet implemented, the fixed point type, and that is the very reason why we did not cover them. So I'm going to comment this out, so in case it might get implemented in future. So that is how you can create sense of negative exponent in your head. Regarding a ternary expression, just to ask you, what will be the value of this integer? Either it will be this small guy or will it be large guy? So that is what you have to think. Now I'm going to run this. I deployed and I'm going to run this. As you can see, I'm getting all the expected output. This was indeed smaller guy because this expression is 2, so this expression will be evaluated and its result is returned. Both are of the integer type, both left expression and the right expression, so both are of the same type too. Next, they have written shifts and exponentiation with literal numbers as left or base in case of exponentiation operand, and integer types as the right or exponent operand are always performed in the uint 256 for non-negative literals, this base thing, or int 256 for negative literals type, regardless of the type of the right exponent operand. Some additional technical information they have given. For the when the left hand side is literal and right hand side is integer for the shift and exponentiation operation, they have this warning that division on integer literals used to truncate in Solidity prior to version 0.4.0, so it was changed in this 0.4 version, but it now converts to a rational number, that is 5 by 2 is not equal to 2 but to 2.5. These are useful for intermediate expressions. Of course we cannot store them in its own type because we don't have a fixed type here, fixed point type. This note and this note is for your info. If you want to read, you can read. As such, I have explained you the basics. Moving on, we have string literals. So string literals are written with either double quotes or single quotes. For example, this they have shown, and they can be split into multiple consecutive parts. So I can write this single string foo-bar as this, which can be helpful when dealing with long strings in case you want to split long strings, but as such they will be one single string only. They do not imply trailing zeros as in C. In C, when we have a string which is like an array of characters, the very last character will be a null byte to denote the termination of the string array. For example, a string, say Solidity in C, will be of the form a list of characters, you can say, so on, then T, Y, and the last character denotes the end of this array. So that is how in C it is there. So its length, instead of being 1 2 3 4 5 6 7 8 bytes, in C it will be 9 bytes, but in case of Solidity it will be 8 bytes only. This does not exist. So This example foo represents 3 bytes, not 4. As with integer literals, their type can vary, but they are implicitly convertible to bytes 1 so on till bytes 32 if they fit in them, or to bytes and to string, of course. Basically, in case we had integer literals like we saw to the power 801, right? So in case of those integer literals, the final expression would be converted to a solidity type, the smallest one in which it can fit. Similarly, will be the case with string literals. So in case I do bytes 5, some type variable of type bytes 5 equal to this foo, in that case the first 3 bytes would be foo and the remaining 2 bytes will be having representation of 0. For example, let me show you, they have this example. For example, with bytes 32 same var equals to string literal, here the first bytes, which would be 1 2 3 4 5 6 7 8 9 10 11 12 13, the first 13 bytes would be occupied corresponding to the byte representation of the character, and the remaining bytes would have 0, like I have written. In case you will inspect the value of this variable same var, you will have this, and the remaining would be 0. How many are these characters? This is 1 byte, 2 byte, 3 4 5 6 7 8 9 10 11 12 13. As we saw, 13 bytes. So the remaining bytes are 0. You can ignore this. I mean, these are something which I have written. Also, string literals can only contain printable ASCII characters, which means the characters between and including this range. So all these characters, if I for instance look at this S in the string literal, look at this S, it will have its corresponding byte representation, which is following this ASCII set. For example, I have this table, and in that if you look at the byte, this is ASCII code character to binary. For the character S, it has this binary representation. Now, can you tell me what is the corresponding hexadecimal digits for this? If I were to tell you, this last one is 2 plus 1, 3. So it is just 3. And this one is 4, 5, 6, 7. So it is 7, 3. So in case what my same var, the first two characters should be 7, 3, which it is also the case. So I hope this string to bytes is all clear. Also, it has these additional escape characters because we are using single quote to tell the string end and beginning, right? So I cannot use this single quote character in between. So to use them, we escape them using this backward slash. So that is what is the escape character is. So they have given various escape characters. You can look at them if you want. But I will cover this example, which is going to clarify many things about these escape characters. So we have this string starting from this double quote, ending from this double quote. It has a new line character. This means that there is a new line. So if I were to write this, here I am going to write this string, how the output will be. So the first is new line. So if this is line 1, so we are in line 2 now. Then we have a double quotes, then a single quote, then a backward slash, then A, B, C, and this thing just means that they have split their string in multiple lines, but as such there is no new line. So it is escaping the actual new line in your code, but the string does not get any new line. And then we have D. Wait a second. And then E and F. E and F. So how many characters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, and this new line character. So in total 10 characters. And if I read what they have written, the string in the following example has a length of 10 bytes. Yeah, each character is taking 1 byte, as I showed you in this table. It starts with a new line byte, followed by a double quote, single quote, backslash character, and then without separator the character sequence A, B, C, D, E, F. Regarding this new line, if I show you this backward slash actual new line in your Solidity code, so it is going to escape that actual new line. Now looking at this Unicode literals, while regular string literals can only contain ASCII, Unicode literals on the other hand, which when you write you prefix with this Unicode keyword, prefixed with the keyword unicorn, can contain any valid UTF-8 sequence. So you can put your emojis also. They also support the very same escape sequences which we have already seen for our string literals. Moving on, we have hexadecimal literals. Hexadecimal literals are prefixed with the keyword hex and are enclosed in double or single quotes like this. And they also again can have these separators. Their content must be hexadecimal digits, which can optionally use a single underscore as a separator between byte boundaries. The value of the literal will be binary representation of the hexadecimal sequence. So I hope this has made sense to you. Multiple hexadecimal literals separated by white space are concatenated into a single literal, just like in case of string literals. So this thing is equivalent to a single hexadecimal literal. Hexadecimal literals behave like string literals and have the same convertibility restrictions, namely those bytes 1, bytes 32 and the dynamic arrays of this bytes type and the string type. These two arrays we will see shortly. Now we have enums, and all of this is very important to read, but let us first see an example which they have provided. We have this contract. The name is not important for us. Now they are declaring, the very first line of this contract is declaring an enum which is having the name action choices, and suppose I want to instantiate here a variable of this enum type action choices. That is what they have done in the second line. Now this enum of defined type action choices can contain only these 4 values. For instance, here, like if we look at the third line, action choices, they are declaring this variable default choice of an enum type action choices, and the value they are assigning is the enums this go straight value. For this, ignore this constant keyword for now, it will be explained later. Now regarding this choice variable, we have not initialized it here in this example. By default it is this go left, the very first value, because the very first value is also having an integer value corresponding equal to 0. Basically its byte representation is 0. So if I typecast it to an integer, it will be having the value 0. Now they have this function go straight in which set go straight. So in that case the choice will be set to go straight. So in this itself, I think the enum part is an example of enum is clear, because how we declare an enum is this line. We first specify this keyword enum, which will tell the compiler that we are going to declare an enum. Then we tell the name of the enum, and then we tell the possible values that enum can have. This will have the integer representation 0, then 1, then 2, then 3, and so on. By default, as the 0 state is there, so this go left would be the value this choice variable will be having by default. And we can assign like this. If I have put equal to say 1 instead of say equal to 2 instead of this action choices dot ghosted. If I had put 2, then also it is going to have this value itself because its integer representation is 2. Like here I have put that same example just to illustrate that these two are same. I have one variable default choice which is having action choices dot ghosted and another variable which I am putting this action choices. In the parenthesis I am putting 2. Now I will show you that both of them are having the same value. So if I deploy this smart contract, you can see this default choice is having value 2 and this underscore default choice is also having the same value 2. Now let us read what they have mentioned for enum. So enums are one way to create a user defined type in Solidity. They are explicitly convertible to and from all integer types, but implicit conversion is not allowed. Basically here if I were to do just this, which would mean an implicit conversion because I am not explicitly typecasting it. You see when I save I am getting this error. The explicit conversion from integer checks at runtime that the value lies inside the range of the enum and causes a panic error otherwise. At the runtime it will check here the enum's value ranges from 0, 1, 2 and 3. So if I put here 4 here, since the compiler can see that I have put in value 4 which is outside this range, it is giving the error itself. But if I say modify it to a user given input, for example like here I simply created a new function set default choice which will take an input an unsigned integer of 8 bits and is going to assign it to this. So if I now deploy this, and first I will call this function with 3 which lies within the range to show you that it is indeed working. And now if I query my underscore default choice variable, I am getting the answer as 3. Suppose now I put the value 4 which is outside the range. Now if I set the function, I should get a panic error. You saw this cross symbol? It is for the exception that has been raised. And regarding this panic error, we will cover it shortly. So enums require at least one member. I mean there should be at least one member inside this curly braces. And its default value when declared is the first member because it is 0. Enums cannot have more than 256 members. So this list cannot contain more than 256 elements and thus it will fit inside our uint 8. And that is what its type is also. The data representation is the same as for enums in C. In C there is also an enum, so they are saying that it is similar. Need not bother about this. The options are represented by subsequent unsigned integer values starting from 0. This is I have explained. Using type of enum.min and type of enum.max, you can get the smallest and respectively largest value of the given enum. So for here, in this example, can you tell me what is the smallest and the largest? Smallest is 0 and largest is 3. So I have this comment also written in my that let me show you the remaining functions in this code. This get choice function will simply return the choice variable's value, and this get default choice will return the default choice value. Then the get largest value will return this type action choices dot max. So the maximum possible value in this enum type. So this should output 3, and you can verify also that it will indeed output 3. I have written it in my notes that it outputs 3 itself, and this will output 0. And they have this note: enums can also be declared on the file level outside of contract or library definitions. Basically here outside this contract itself you can declare an enum. Like I did this small modification and you can see the code runs exactly fine. So in case I am importing some other file, this can be a global symbol in that, provided the enum is defined in that file. So I hope you understood about enum. Next, we have user defined value types. Let us understand it with the example which they have given. So what they are trying to do is they are trying to represent a 18 decimal, ignore this 256 bit wide, an 18 decimal fixed point type using a user defined value type. So let me explain this thoroughly. What they want is to represent an number which can have 18 decimal digits. For instance, suppose the number can be this 6 point, then x1, x2, so on till x18. So that number can have these 18 decimal digits. Now in Solidity, you know we don't have this concept of floating point numbers. Basically, we don't have a data type in which we can store such numbers. We saw integers which cannot store these decimal values, right? So how we can achieve is, since we know that this can have at most 18 decimal digits, if I multiply this number with 10 to the power 18, I will get an integer, right? So that is what they are doing, is that they have this 18 decimal digit number which is 256 bit wide, because the underlying type is actually this u in 256. So ultimately it is 256 bit wide, and whenever suppose they want to get this number from a given integer, suppose I want to represent 6.000 so on till the last 0, 18th 0, so that we have 18 decimal digits. Suppose I want to represent this in our system, then I would have to multiply it by 10 to the power 18 to get 6 into 10 to the power 18. Basic idea is, suppose I have these two numbers 83.68799628 so on. Suppose the last digit here is 1, and I have this another number 544.7987632 so on. Suppose here the last digit is 4. Let me add one more digit here, suppose 5. Now internally I will store them as an integer 83687999628 so on till the last digit 1. Similarly, the other will be stored as an integer. Here these are 18 decimal places, exactly 18, which will be 5, 2, 3, 6, 7, 8, 9, 7, 4, 4, 5. So if I want to add them, I can now simply add them to get my answer, and in that answer if I divide by 10 to the power 18, I will get the corresponding decimal place. So that is the idea here. If you look at this number will take an integer, and output will be that integer multiplied by 10 to the power 18. And now before I come to this, let me show you this add function. It will take two such numbers, and then it is first going to unwrap it. Unwrapping will simply give me this underlying type u in 256. So if I unwrap it, I will simply be getting this type u in 256. So my first integer I got, and I also got my second integer. I added them, and then I again wrap them. Wrapping simply will give me this alias instead of uint256, now it is of this type. This is what wrapping does. So this is how the addition happened. And here I told you how to get that number. We get that number into 10 to the power 18, then we wrap it, because internally this is how we are storing that number. Now they have this multiplication where they are multiplying this number with an integer, not that with not the same type but some integer. For instance, suppose I want to do this 6 into 10 to the power 18 into 3. Then this is what that function. The first number could be your that type, which is actually in integer representation having 6 into 10 to the power 18, and the code semantics is that it is equal to 6.0000, and to that I can multiply by say 3 to get that. This is what this is basically doing as a multiplication, not on the same type but on this type with an unsigned integer. Now what is this floor doing? Suppose you are having this 6.32 etc. Now when I unwrap it, I will get that big integer where all the decimal places will not be there now. To that, if I divide by 10 to the power 18, like in integers, this division rounds towards 0 as we saw. So I will get the floor. So if I give you an example, as the floor of 6.32, so 6.34 should be equal to 6. So internally that is having 634, so on. These are 18 in number, 18 digits. When I divide by 10 to the power 18, since the actual number is a fractional number 6.34, it is going to round towards 0, and the closest integer it will encounter will be 6. So that will be my output. This is what that floor function is doing here. Although this the code here is very limited, you won't be actually be able to put a decimal number using this code, because whenever we enter this, we are having an integer into 10 to the power 18. So those 10 to the power 18 will always be 0 for their implementation, since this implementation is not complete. Now let's read what they have to say about this, a user defined value types. So a user defined value type allows creating a zero cost abstraction over an elementary value type. This is similar to an alias but with stricter type requirements. Here, when I'm doing this, type u fixed, declaring my own type is something. So I'm not paying some extra cost here. So this is like zero cost abstraction. Now a user defined value type is defined using type C is v. We saw that, where C is the name of the newly introduced type and v has to be a built-in value type, the underlying type. So the built-in value type, it should be there. It has to actually exist in our ABI as a value type. The function c.wrap is used to convert from the underlying type to the custom type. Similarly, the function c.unwrap is used to convert from the custom type to the underlying type. Type C does not have any operators or bound member functions. Here, when I did this wrapping thing, even though integers have this addition, subtraction, etc., my wrap function will not, my wrapped type does not have that, or bound member functions. In particular, even the equality operator is not defined. Explicit and implicit conversions to and from other types are also disallowed. Regarding this bound member functions, like we saw in bytes, fixed bytes type, like bytes 3, bytes 4 till bytes 32, they had this length member function. So that is what is being talked about. The data representation of values of such types are inherited from the underlying type, and the underlying type is also used in the ABI. I think this is self-explanatory. For instance, here inside the ABI, the type will be uint256. The following example, they have this, which we have covered up already. So that is what I wanted to say about user defined value types. Function types I will cover as soon as I cover functions, so this will be covered later. Now coming to a very important section, reference types. This might be confusing, but it is very simple, so let me explain it thoroughly. First, if you look at the value types, like we had boolean, integers, address, then we also have fixed size byte arrays, like their size was fixed. This dynamically is a reference type, it is not a value type. Address literals, these are the literals, we need not bother about them. Enums, as we saw, maximum range is up to 256, so they are also bound by a single word. 256 bits is 32 bytes, which is one word here in our architecture. And literals, we saw that ultimately we had to convert them to a type, which could be a reference type, but uh, when we convert it to a value type, then their size is fixed. So the idea here is that they are bound. These types are bound. But suppose we have a list of numbers, a very large list of numbers, then its size is not fixed, or it could be fixed, but it is something which could be very large, which might not fit in a single word. And thus, for these complex types, we have this concept of data location. First, let me tell you a bit about arrays. So here I have a simple example of an array. This first line is declaring an array. This notation means that I am declaring an array of type whose elements are of type integer. Example, this notation simply tells that I am declaring an array whose elements are of type this. So an array could be this. Here, this array, which you can think of as a sequence or a list of elements, and each of the element is having the type integer. So that is what we are having here. Ignore this public keyword. The name of the array I am giving this array in storage, because as I will tell you that it is in storage. Now suppose to this array I want to, like in this example, if I want to add an element 5 at the end of this array, then the new modified array will be this. So that is what that function is doing. It is adding the element to the end. So it takes the input and then pushes that value to the end of that array. Similarly, I have this get function to which I give the index, because this is at index 0, this is at index 1, index 2 and index 3. As in almost every programming language, we start from 0 index. The first index has the value 0, not 1 as you might think, but 0. So if I put as the input 0, I will get the first element in that array. So before moving to this function, let us run this and see and play with it a bit. So I'm going to deploy this contract. Now in this deploy contract, I have this add function. Initially, my list is empty. My array in storage as such is an empty array. So I'm going to push some value. Let me push to this, suppose 4. I'm going to add. I have added. Then let me do 7. Then let me do 2. So I've added 3 values, 4, 7, 2. So my array should be this 4, 7, 2. this should be the structure of my array. And if I suppose get the first element, then the answer should be 0. I mean answer should be 4 because the 0th index contains the value 4. So as this is the index 0, so when I want the 0th index, which is the first element of that array, I am getting 4. Since this is at index 2, now if I put 2 in that, I should get 2 itself because both these are same. So yeah, 2. Now if I put 1, I should get 7. And here I got 7. Let us add one more element, say 2000. And now if I query the fourth element whose index is 3, now if I should get the answer as 2000, which is what I got also. So this was a simple example of array. Similarly, here I have specified a keyword memory. What I want you to know for now, that this array had no fixed size. I did not specify any size, and it can go arbitrarily large till the, of course, the limits of EVM. But this array, named array in memory, I have set the size to be 5. So it should contain exactly 5 elements, and I have given those 5 elements here also, 1, 2, 3, 4, 5. And if I verify that the index 1, which means the second element in array, should have the value 2, and if this assertion passes, that means yes, it was indeed 2. But to make it a bit more clear, I'll make it here 7, and this also I'll make it 7. And now if I run this smart contract, let me first deploy it, and now run this function memory array, I should not get any error. And yes, it ran successfully. There was no error. So for now, what I want you to know is about that this is static, in the sense that its size I have predetermined, whereas this is called dynamic array because it can go or shrink. I mean, it can grow arbitrarily large. There is no fixed size to it. So if we read about arrays, arrays can have compile time fixed size, or they can have dynamic size, as I told you. The type of an array of fixed size k and element type t is written as tk. Here, as I showed you, this array containing 5 integers is written like this. So this is what they wrote in this line. And an array of dynamic size as t and this square brackets. So if I want to declare an array of dynamic size whose each element has type t, I will simply write this t and like this. So I hope this made sense. They have given an example. For example, an array of 5 dynamic arrays of uint is written as this. Basically, they want 5 dynamic arrays of uint. Suppose the dynamic arrays of type uint I am denoting as d, and since I want 5 of these, I am writing here 5. Here d denotes dynamic array of type, I guess they put as int or uint, of type uint. This is how I will write. And now what is d? My d is, this d is, as it is a dynamic array of type uint, I will write it as this. So overall, my expression which I should write in Solidity should be this: u int and then 5. So I hope this is clear why they wrote in this way. The notation is reversed compared to some other languages. So if you don't, you need not bother about this line. In Solidity, x3 is always an array containing 3 elements of type x, even if x is itself an array. I think this is obvious because of our previous example. This is not the case in other languages such as C. So if you know C, fine. If you don't, you need not bother. Indices are zero based, as I told you, and access is in the opposite direction of the declaration. What this means is basically, suppose I have this array. This large array, we can call it as a multi-dimensional array. So suppose if I want to access, say, let me first name it. Suppose I name this array as x. Now what will this specify? Let me give an example like this. This will mean, let us break it step by step. x5 would simply mean, if I call this whole thing as suppose R, then x5, and suppose x has this structure R1, R2, R3, R4, R5, so on, R6, and so on, then x5 will simply give me R5. Here I have done a slight mistake. In this list, this RI list, which I have written in green, I forgot to add the R0 element. The first element is R0 that I forgot to add. Please put that there. That is, consider this array as R0, R1, R2, R3, R4, R5, and so on. Basically, the fifth element in this array, in R square brackets array. Sorry, not the fifth, but sixth. And then when I'm putting here 8, this part, and suppose this thing, I'm calling it as L, then what I am getting is this R5, 8, which is basically L8 provided R5 was of this form, an array where each element I am denoting by Li. So this might be a bit confusing. Let me first also show you their example. For example, if you have variable this, which is what? A list of 5 dynamic arrays of type uint. You access the 7th uint in the 3rd dynamic array using this x26, and to access the 3rd dynamic array use x2. So when I am doing x2, I have 5 dynamic arrays, each of type of 5 dynamic arrays, where those dynamic arrays elements are of type uint. So if I want to access the 3rd dynamic array, I am doing this x2. Again, if you have an array t5a, I think this line will make it very clear to you. Again, if you have an array t5a for a type t that can also be in itself an array, then a2 always have type t. So that is how you can create multi-dimensional array, and their access I hope is clear to you. Moving on, array elements can be of any type, including mapping or struct. So the elements inside your array could also be of type mapping or struct. These mapping and struct we will cover shortly. The general restrictions for types apply in that mapping can only be stored in storage. We will see that in case of array, We have first of all 3 data locations. Our data locations, if I tell you, are namely of 3 types. One is storage. What is this storage if I show you? This storage which each account is maintaining, which is also accessed by our EVM, which is persistent and all. We have seen the properties of the storage. Next is memory, which also we have seen memory in detail, and there are various examples which we will cover for internal calls, external calls shortly after covering this array itself. So that all this becomes very clear. This call data part also needs to be very clear in R, because it might be confusing when the function has the call data parameters. We will see all of this in very much detail. So these are the 3 possible data locations. Array can be in either of these 3, but for the mapping, the restriction is that mapping always have to be in storage. So they have mentioned that itself, that if your array contains a mapping, you must put it in storage. The general restrictions for types apply in that mappings can only be stored in the storage data location, and publicly visible functions need parameters that are ABI type. Since when we say publicly visible functions, means that those functions can be called by some other contract. So if the other contract is calling that function, that other contract should be able to give in the inputs. And as you saw, we give inputs using ABI convention. So so for that, the function need to follow these convention. So that is why they have written this, that publicly visible functions need parameters that are ABI types. As an example of a parameter that is although valid in the internal functions but not the publicly visible functions is map. As one thing I have told you about maps is that they can be, their data location has to be storage, and we will see, I will give you an example also, that mapping we can pass it as a reference to the internal functions, but external functions, publicly visible functions, cannot contain mapping as their parameter, because of the fact that the data location of the mapping is always storage. I will explain this in detail later, but I just wanted to give you an example here. And for the valid API types, you can see it here in the contract API specification. They have given you about all the types. So if you want to read, you can read. It is possible to mark state variable arrays as public and have Solidity create a getter. The numeric index becomes a required parameter for the getter. Here, I haven't covered this public yet, but if I am declaring a variable as a public variable, then just like how we call functions, there will be a function created from which I can query to get the element's value. For instance, I had this get function here, to which I pass in the index to get the element at that index inside my array. Similarly here, as this I have declared as public, I can, here this is this variable array in storage. Here if I give in the index, suppose 0th index, and if I call this function, I will get the element in that index. I am getting the error here because there was no element here. So let me first put the element. Suppose I am putting 27. Add. Now if I do this, I should get the answer as 27. So this is about it. We will cover the getter functions in detail later. So, but as such, the semantics I have explained you now. Accessing an array past its end causes a failing assertion, just like we saw now itself. Since the array was empty when I was accessing the first element, since there was no first element, I got this error. Methods .push and .push value can be used to append a new element at the end of the array. We saw for this push value, but if we push with empty thing, so they have explained that where push giving, if you don't give any value here, appends a zero initialized element and returns a reference to it. So I think this is clear to you about arrays. Now regarding these data location, storage, memory and call data, let us cover them one by one. So I have cooked up this example for you. Here this is a state variable. Let me also now clarify about state variable. So here is the line from the documentation. State variables are variables whose values are permanently stored in contract storage. I already showed you about contract storage. So whenever we have a variable inside that storage, then we call it as a state variable. So here although for our reference types we always specify their data location, like in this case I have specified here storage, but here I have not specified the data location. I have not written storage or memory or call data. Well, because only storage is possible here. When we are declaring the variable inside the contract but outside everywhere else, then it is in the storage, in the contract storage. So we cannot even specify here this line storage even though it is in storage. So that is about it, first thing. And this is an array part of the state and it is in storage. Now I have this function g, and what it does, since it can access the contract storage, it is going to push an integer 2 in it. Now I am calling this function f by passing the reference of L. Now what is this reference? Let me tell you. Also a bit about storage. It is concise. It is very compact. Our storage is very compact. Like suppose as we know, the word in the storage, it's a key value pair and the value word is of 32 bytes. One word is 32 bytes. One word is 32 bytes. Now suppose I have an int 8 and an int 16. That is an integer of 8 bits and an integer of 16 bits. This is 1 byte. I mean the size it needs is of 1 byte, and an integer of 16 bits need a size of 2 byte naturally. Now since our word is of 32 bytes, it is bigger than 1 byte and also 2 byte, and it can contain both these two values. So in the storage, instead of occupying two slots, that is two key value pairs, only one key value pair will be there and the value will contain both these elements. If you want to read more about it, you can read it in this article about the compactness, how the elements are stored in the storage. That's one thing I also wanted to say. Besides that, coming back to our reference point, now this is storage. For the simplicity, I'm going to ignore the keys part, and regarding value, suppose I have my array of int 256, basically 32 bytes. So my array is taking slots, one word size slots in my storage, right? Suppose these many slots it has taken 1, 2, 3, 4 slots, basically 4 key value pairs. Fine. And now what is this reference? Reference, you can simply understand that it is suppose containing the address of this slot. or somehow instead of saying address, let me call it a reference. So it is going to have it some value, you can say whatever, say 0x123. Like every location has some value, right? I told you initially all the other values inside this storage is 0, right? Everything has a value. Now suppose these four slots contain the array 7512. That is, my array is this 7, 5, 1 and 2. Now what is reference? You can think of as reference like an address of this array, like where in the storage my array is present. So that's something I haven't explicitly told you what is that which the reference is referring. Like it could be address, in like C it is usually address, but whatever it is in EVM, in Solidity, say some reference which it is having, suppose this value 0x123. Now what this function g is passing to f is this value reference, this value 0x123. What it is going to do, it is going to copy not the array remains in storage as it is. It is not going to copy this array, but it is going to copy the reference. So copy reference, not array. So it is declaring new variable which is going to have this reference. In our case 0x123. So what is happening here is that this value has been passed, this 0x123, which is the reference to my storage. And what this function is doing, there is also pop, just like we have push. The pop will remove the last element in that array, and then it is going to push then integer 3. So we started with an empty array. I inserted the element 2 in it. That is, if I draw the schematic, I have this empty array, then it had 2, then I popped the element, and then I inserted this element 3 in it. So looking at the example, from in the empty array we put it 2, then we call this function where we are passing the reference of that storage element. We popped it, we pushed in 3. Now we are back in our function g because this function f has finished executing. In the assertion, I am checking the length to be 1, just like for the fixed size bytes we had this length method. Similarly for arrays also we have this length method which tells me the length of the array. So length is 1, just like I showed you. It contains this element 3. Now its length should be 1 and the first element should be 3. So this is the example I wrote. Let me also deploy it and check whether it's working correctly or not, as expected or not. So I'm calling this function g and there should not be any exception raised. So this has ran successfully. So the thing to notice here is that firstly, this is the internal function, and what is internal function explicitly I will explain later. But if you were to understand here, like this is the function called of the same contract. For instance, if I had, instead of writing this, had written this dot f, what this will behave as, it will behave exactly how I would be calling some other contracts function. So if it was if this function was present in some other contract, then this is how it is I'm going to call it. But it won't be possible for me to call it like this, because storage, the other contract cannot access this contract storage. For example, suppose I have contract A which is having this function G. Now this function G is calling other contracts function F. Now when I'm calling this other contracts function, then a new context will get generated. A new context will get generated, like I would have a new set of stack, memory, and all those other things we saw, program counter, how much gas is left, and so on. So that is what is we will have. And now this function f has no possible way to access the storage of other contract. It cannot access storage of other contract. Even though here you might think then that when I'm doing this dot f, I am basically calling the same functions, same contracts function externally, but that is not how. I mean, this f function could very well be in some other contract. So that is not the way to do it. If you want to have the function access the storage, then call it internally. But if you are calling it like this, then it is just like some other contract, and some other contract cannot access this storage of your contract. So if when I do this dot f, then it won't compile. However, if you want to pass your storage array, then you can put it as call data. Now I can call this function f externally, and when I do this call data, what it is going to do, this had my array in storage. When I'm calling the function f, I have my call data, the payload, right? So if I want to give this function f an array, what I can do, I can copy it to my payload. To not my payload, to the transactions payload. So that is what will happen. A copy will get generated. When I'm going to put as call data, my array in storage, a copy will get generated, and that is what is going to get passed to f. F can do things with that array, but that is not going to impact my storage. Now there is slight difference here. Since it is a call data, and a call data is immutable structure, in the sense you cannot modify what you get as a call data. Here the things that you get in your payload, they are what they are. You cannot modify it. So here, if I'm going to save it, this will not compile, because this function is trying to modify the call data, because m.pop, m.push. Suppose if I save it now, you see I'm getting this error because call data cannot be modified. However, I mean, if I did not have these functions, if I had something like this, int something equals m0, then since I'm just viewing it, I'm just reading it, I'm not writing or deleting or anything like that, I'm not modifying, just reading, so it is fine like this. And if I modify this from internal to external, since when I'm doing this dot f, I'm calling it externally, or let us make it public, so it can be called both internally and externally. I mean, this is what public keyword signifies. So yeah, I'm saving it and it is getting compiled successfully. All I'm getting are just warnings, like uh, these warnings we can ignore for now. So this is fine for call data. However, if I want to modify my array, then I can copy this thing from the call data either to memory or to storage. And if I write here memory, then what this is going to do, it is going to copy what it got in the call data. The array will still come via call data. We are not escaping from that. But then it will copy to its memory, to this context's memory. And now if I go back to my contract, then I can now modify this array m, but there is a slight caveat in that I still cannot use this pop and push functions because they are not available for memory arrays. Like pop is available for this dynamic storage arrays and bytes, and similarly for push, but I can still play with it. Like first of all, let me change it from here call data to memory, and now let me make it a blank array, so say containing 5 elements. So new int, then yeah, I think this should compile, and I have an error. Okay, let's make it here like this, and this to be typecasted like this. Yeah, now this is compiling successfully. So now I have modified this input array which contained just one element to something, this, an array whose element is this 0, 1, 2, 3 and 4. It has this elements inside this array. Maybe now I see it appropriate to also explain you about this for loop. So let me just first quickly explain about for loop. Okay, for loop. What this is doing, this part, the very leftmost part, if I do something like this, u int I equals 0, and now if I remove this part, it's not this much, even now it is going to run exactly what it was doing before. So this part which was present inside it was simply declaring a variable I to be used only inside this code block. This variable I, its lifespan is limited inside this code block. I cannot access this variable outside. So for instance, I cannot do this u int j equals I. This I won't be able to do because I is not living here. Though if I had done something like this, now it is, just one second, now it is fine. This will compile successfully because now this i's lifespan is till below this line. You can access it. There is something about solidity in that. For this example, I lifespan is from this line onwards till the end of the code block, But this is but we will see later that if, for instance, I had something like this int k, then this k's lifespan is this entire block, not just after this but even before it was living you can access it. But this is something we will cover later, so I don't want to cover multiple things in a single part when we are covering about data locations. But I think since there is no further prerequisite required for this for loop, so let me cover this for loop. So uint I equals 0. So the very first part before this semicolon was just declaring a variable here. So I could have declared something else also here, but that is how for loop is commonly used. And then what we are going to do is that it will check this condition here. Since I is starting from 0, this condition is true, so it is going to run this. Once it has run everything inside this code block, it is going to go here, and what this is going to do, this is just a shorthand of writing this, which is the shorthand of writing this. Fine. I equals to I plus 1 can be written like this, I plus equals to 1, which can simply be written like this, I plus plus. So we increment I and then we check this condition again. Since this condition still holds, it is going to go inside, and what we are doing at the ith index, I'm just giving this value, that's all. And then again we are going to increment as, oh, one thing I just noticed, my array, instead of being this 0 1 2 3 4, it is actually this 5, because I have put less than equals to here. So at the fifth index, which is the sixth element, at the fifth index I am assigning the value 5. So this for loop will keep on incrementing I, and as soon as I becomes greater than 5, so when I will become 6, then it will see that this condition no longer holds, and so this block will now not be executed, and it is going to go to the next line here, right? So this is simply about for loop. So yeah, this is what I did with my memory array. So storage is not valid when you are calling this function externally, and if you are putting the keyword as storage, then your function visibility has to be internal. There is one more word known as private, which is a stronger than internal, but it is also internal in some sense. So internal visibility or private, it should be there. Secondly, I cannot make it public with storage keyword, because then this function as a public keyword will signify both internal and external calls are possible. Since external calls cannot have a storage reference passed, so this will not hold. You have to put either call data or public or call data or memory for our public functions, basically for external functions. And when we put memory, then what it is going to do, it is simply going to copy what it received in its call data to its own context memory. So I think with this everything is clear to you about the data location. I have told you about all these three things, about storage, memory and call data. Also, when I have put here memory, all the modifications I do when I'm calling this function externally will not have any change on my L storage array. For example, I passed in this L but it is going to copy it here. So it is actually going to be passed by value. When we talk of reference type, it is not always passed by reference. When the data location changes, like from here, it is changing from storage to memory, first from storage to call data, and then from call data to memory. Because of this change in data location, a copy operation has occurred. So it is actually passed by value in this case. For the pass by reference, I have shown you in the very first example when we use here storage keyword. So here, if I verify that in the end it should be 2, you will see that yes, indeed it is the case, because when I run it, deployed here, let me call my G function, and I have a revert, which is simply because I am accessing the index which is out of the size of my array, because I have put in 5 but actually my array has 6 elements. So let me now redeploy and run it, and yes, it has running successfully. So I hope the semantics of language is clear. They do not allow storage for external functions because they want you to know as such that you cannot share storage between contracts like this. And for call data, it is how the actual value is being transferred via our transaction message in payload, and memory when it is going to copy to its own memory from call data. So let us now read about this section, reference types. Values of reference type can be modified through multiple different names as we saw. Contrast this with value types where you get an independent copy whenever a variable of value type is used. When you assign a value type to some another variable or you pass it to some function, each time an independent copy is happening. Because of that, reference types have to be handled more carefully than value types. Basically, you should know when are you passing by reference and when by value for reference types. Currently, reference types comprise structs, arrays, and mappings, only these 3. If you use a reference type, you always have to explicitly provide the data area where the type is stored, as I showed you. But in case, when you are declaring the variable outside of all the functions in your contract, then it is by default storage and you don't provide data location in that case. But everywhere else you have to explicitly provide the data location. Memory, whose lifetime is limited to an external function call. We will see the examples of this more. I have shown you some examples where the memory word is used inside a function. So it is alive within that context of function. It is alive in that EVM context. Suppose that function then in turn calls some another function passing this memory as a reference. So it is alive even in that other function. But basically when we do an external function call, a new context gets generated and this memory variable is basically alive just for that context. Or if you are explicitly deleting it and such stuff, we will see examples of it and it will become clear. Storage, the location where the state variables are stored, where the lifetime is limited to the lifetime of the contract. Or call data, special data location that contains the function arguments. We saw all this. An assignment or type conversion that changes the data location will always incur an automatic copy operation, like I showed you when from storage to call data. Since the data location was changing, the copy operation was happening. While assignments inside the same data location only copy in some cases for storage types only. We will see various examples of it. So basically they are saying that within the same type, within the same data location also sometimes a copy operation can happen. So we will see examples for that. So these data locations, every reference type has an additional annotation, the data location, about where it is stored. There are 3 data locations: memory, storage, and call data. Call data is non-modifiable, non-persistent. It is just limited to that lifetime of that function. Non-persistent area, where function arguments are stored and behaves mostly like memory. Even here, in case of memory, lifetime is limited to an external function call. So even if that function is calling some another function, but that another function is called within this function, like if I show you the example, here in our previous example, suppose g is calling this function f externally. So a new context will get generated where we have this array. First from call data it is copied to memory. Now this array is alive only inside this function. Even if this function suppose calls some another function, but after calling that function it will return back to this function and it will start executing whatever is next. Only when this end of the curly bracket is reached is when this function's execution will finish, and that is when the memory part is lost. So it is not persistent and thus limited to the this function's lifetime. Just have a read again, whose lifetime is limited to an external function call. We saw different examples, so I hope this will be clear to you. Also, we have a note, which is an important note. If you can, try to use call data as a data location because it will avoid copies. In our case, from call data, we were copying to memory in this example. So unless we plan to, play with this instead of reading, like here I changed the size and inserted the elements in that array, assigned the elements in that array. So if you don't plan to modify, then putting memory keyword will just occur an extra gas cost because of this additional copy operations. So if you avoid to there is no need for that, then avoid it. And also make sure that the data cannot be modified because call data cannot be modified, it is non-modifiable. Arrays and structs with call data location can also be returned from functions, but it is not possible to allocate such type. Here I was allocating memory, but regarding this new keyword we will cover that shortly. Here I was allocating that memory, but in case of call data you get what you get and you can return that also. Also here, this thing, it does not mean that you can return only call data array or structs. You can return even memory, and for that matter even storage reference that can also be returned from internal functions. Here they are just saying that call data arrays can also be returned. Regarding that return part, I have a simple example for you. Here I have this function f which will take an input array in its, the array will come in the call data. Then it is going to call this function g, passing in this array, and this g is now going to return this same array to it to showcase the example that yes, call data array can be returned. Arrays and structs with call data location can also be returned from functions. Like in this case, we are returning this array, and here I also verify that the second element in that array is equal to 7, and here I am verifying that the returned array, the first element inside that array, is equals to 3. So let me run this function. First I am going to deploy, then I am going to call this function f. I am going to pass in an array. The first element will be 3 and the second element will be 7. So let's pass this array, and yes, everything has run successfully. So it is working as expected. Continuing, this note is as such not relevant, but I just wanted to tell you in case you might read some older articles, there they might mention that external functions can have arguments only in call data. As such, the argument first comes in call data only, but here as you saw in one of our example that we can also specify memory. like this. But earlier for external functions it had to be call data. So that you don't get confused, you should know that Solidity compiler version has upgraded, which allows for other data locations. So prior to version this, data location for reference type arguments was limited to call data in external functions, memory in public functions, and either memory or storage in internal and private ones. Now memory and call data are allowed in all functions regardless of their visibility. Now So let us now discuss about this data location and assignment behavior. As I told you that whenever you change the data location, then it is no longer passed by reference, but it is by value, and you are doing this independent copy operation. And only in case of storage, it can be at times passed by value or passed by reference. Basically, when from one storage variable you are assigning it to some another storage variable, only in that case we have to be a bit more careful that either it can be passed by value or passed by reference. Whereas from memory, it is always passed by reference. Assignments from memory to memory only create references. Here, I would like to add one thing. The second bullet point is saying that assignments from memory to memory only create references. But of course, if you are calling some external function which is expecting suppose it is expecting the array whose data location is set to memory, then even if your array was having data location memory, then when you are calling, actually it will be copied to the message calls data, that is payload, and then from that call data, in the new context of the EVM that will get generated there, in that from call data to memory it will be copied. So in case you are calling external functions, then memory to memory won't be reference, but actually it will be passed by value. I mean, this is something which we have seen before, so I don't think there should be any confusion. So let us see examples of these also. Like returning back to our same example. Here I have added one more line to this array m. I am copying it. I am not copying it. I am assigning it to another array which is in memory. So here, if I do some modifications to the m2 array, you will see that m array is also getting modified. So if I do m2, the last element, if I make it equals to suppose 10, then if I do assertion on this element whether it is equals to 10 or not, and if I run this program, you will see that m is indeed getting modified and it is equals to this 10. So I am going to deploy this contract and I'm going to call this function f, passing in the empty array, since anyway I'm making a new array inside. So let's call this, and yes, it has ran successfully. So you understood that it is by reference when you are doing from memory to memory. Then assignments from storage to a local storage variable only assigns a reference, and all other assignments to storage always copy. So in case you have your variable which is in storage, and now inside a function you are creating a variable which with data type storage, since that is a local to that function, it is going to assign a reference. So we'll see an example now. So looking at their example which they have, I'm going to copy this example to Remix so that I can better explain it. So they have this variable x which is in storage. The data location of x is storage. This is the only place where the data location can be omitted. Then we have this function f which has this array, memory array, which is in memory. Now to this storage array, they are assigning this memory array. Since the data location is different, a copy operation will occur. So works copies the whole array to storage. Then they have declared a local storage variable. So this variable is local because it is declared inside a function. This is not, we won't say this to be local, but we actually say them state variables. So since this has the data location of storage, it is, and we have assigned it a storage element, it is going to basically refer to this x itself. When we declare a local storage variable, then we must assign a storage variable itself, because we do not allocate as such, in the sense to say something. We storage is like a state part. So when you declare state variables, they have to be outside the function, because their lifetime is not limited to just a function, they exist beyond that. So that is why storage variables should be declared outside. Here we are just like changing the name of x to y. So we have a variable which is referencing to that variable x itself. So works assigns a pointer. Pointer, I told you, which is, it is actually pointing to that actual storage element. So data location of y is storage, basically the same same, it is same as x, basically you can say, just the name has been changed. So y of 7 will, it is fine, it is going to return the 8th element of x. Y dot pop is going to pop the last element of x. Delete x. Now here we are deleting. I haven't formally told you about the delete keyword, we will cover it later, but as of now understand that it is going to delete the array. So here the array gets deleted, since what was y referring to has been deleted, so y is now like a null pointer. Now they are saying that this thing y equal to memory array does not work. The following does not work. It will need to create a new temporary unnamed array in storage, but as I told you, it is actually storage part has to be declared outside, but storage is data statically allocated. We can modify storage inside function, like we do this y dot pop or x dot push we might do. So we can, storage can dynamically increase or decrease, you can say that storage can be modified inside a function, but storage is as such, if I were to make it to you clear, here this will not work, y equal to memory array, because to some storage thing which we don't do a new thing inside something which is context limited as of this function. So storage is part of the state, we don't do this equal to something in memory, because then it will have to copy it in storage, but where it will copy? For instance, this will work if I have this line x equals to memory array, then we know that where the storage of x is, this memory array will get copied to that storage. So if I save it, this is going to work completely fine. But this, when I save, I will get the error as you see here, and the reason is what they have mentioned, that storage is statically allocated. That is, at the very deployment of the contract, we have all the places where the storage element is present. So here when this contract is deployed, we know that the here in the storage I am going to put values of x. Now I can increase those values of x, increase the elements in that array inside a function, or decrease it, but that x part is available to me. Here I am declaring basically a new thing, so that will not happen. So what I'm saying, instead of here if I had put memory array, then this is invalid. So I hope this is clear to you. And this delete y does not work, because now y is a null pointer. What are you going to delete with it? And they have shown an example where they are calling this function g. Since it is internal, we can pass a storage data location element. So calls g, handing over a reference to x. Fine. And h of x, since it is memory and x is in storage, a copy operation will occur, and it will no longer be passed by reference, but it will be passed by value, as it will be an independent array. Any modification done to this will not be modifying our x array. So I hope this example is clear. Also, one more example I have to illustrate that local storage, when we are assigning it to local storage, then it is by reference, otherwise it is copied. So let me show that. Here I have these two state variables, my a and copies a. So to this state variable a, inside this function f, I am pushing these three values, making my a array this 1 2 3. Now I am declaring a local storage variable, of this dynamic int array, which is referencing to a. So to this, I modify the first value to 2, making my a array this, and I'm also checking that with this my a array has actually been modified. So I'm just checking whether the first element is indeed 2 or not. Next, I'm assigning to this other state variable copies a this value a. Now here copy operation has occurred instead of being passed by reference, because this variable is not a local storage variable, instead it is a state variable. So to this, the first element I am modifying it to be 7. So my this copies a is now this, whereas my a is still this. So if I now check whether the first element of a is 2 or not, then indeed this will be 2. So let me also deploy and show that. I'm going to deploy this and I will be calling this function f, and yes, it has passed successfully. Also in Solidity, as I would have told before, state variables are those whose values are permanently stored in contract storage. Besides state variables, there is one more thing known as global variables, which are available to us anyways. This is something which I cover later, not now, but in case we have say this block dot number, we are not defining this variable in our contract, etc. This is available to us even beforehand. So these are the global variables. If I use this block dot number, it will give me the current block number. So we call these global variables. And all other variables besides these global variables and state variables are said to be local variables. So any variable which I am declaring inside this function, say u int x, that is a local variable. We will also see scoping later, and all these variables declared inside these nested blocks are also local to that nested block. We will see this later, and at that time it will become much more clear. Now we will read about arrays. This part of the arrays I have already covered. So let us continue from here. Bytes and string as arrays. These are two special arrays. Variables of type bytes and string are special arrays. The bytes type is similar to bytes 1, but there is a catch, as this bytes is tightly packed also in call data and memory, whereas for this thing it was tightly packed only in storage but not in call data and memory. What do I mean by this? Let me explain. When we write bytes 1 square bracket, that means I have an array whose each element is this type, which is 1 byte. Now since our word both in memory and in storage, also in call data, we usually talk in terms of word, which is 32 bytes. In case of call data, I showed you that even if you are passing an integer of 8 bits long, even then the whole one word is reserved for it. So there are these padding rules, due to which even though this bytes 1 is taking 1 byte, the remaining 31 bytes gets wasted. Similarly for memory, that is how, even though in memory you can store a single byte, but the way it is happening due to padding rules, 31 bytes get wasted. We need not go much in detail about that. But in case of storage, as I showed you that storage is compact, this bytes 1 array is compactly put in case of storage, and in that case the 31 bytes are not wasted. So, but if you plan to use your bytes array in memory and call data, then this is a better choice. Yeah, bytes is a better choice because it is also tightly packed in call data and memory. String is equal to bytes but does not allow length or index access. I cannot do string dot length, or I cannot access the element inside a square brackets like what we were able to do for other arrays. But of course, you can explicitly convert your string to a bytes array and then you can do these things. Solidity does not have string manipulation functions like your push pop, which exist for arrays. However, they do not exist for string, as we will see. But there are third party string libraries which you can use if you want added functionality in your strings. You can also compare two strings by their catcheck 256 hash using this way. ABI.encode packed you use, and over that you do your catcheck hash, and you can compare and concatenate two strings using this method of concat, where you can concat two strings. You should use bytes over bytes 1 because it is cheaper, since using bytes 1 in memory adds 31 padding bytes between the elements, as we have covered. Note that in storage the padding is absent due to tight packing. See bytes and string. So this is we have already covered. As a general rule, use bytes for arbitrary length raw byte data, but in case your raw data is fixed, say bytes, it is of size say 16 bytes, then you obviously should use those 16 bytes type. And string for arbitrary length string UTF-8 data, but if you can limit to a certain number of bytes, always use one of the value types bytes 1 to bytes 32 because they are much cheaper in terms of gas. If you want to access the byte representation of a string S, as we saw the strings, they all the characters, they have their associated bytes. Each character, I show you the ASCII code previously. So yeah, the same thing. Use bytes s dot length to access the length, and you can access the index via this way first by typecasting it to bytes. Keep in mind that you are accessing the low level bytes. Here, when I'm doing the x, you can supposedly think that here this x will translate to its ASCII code because on the right hand side we are using it as a string. I think it will be better to see via an example. So I have this example here. Here I have this variable some string whose value is just hello. So the string hello, it is what this is containing. So the second character is E, and I can confirm that like this. Here right hand side I am passing in the string. But E, if I show you the ASCII table for E, you can look at it here. This is 4 plus 1 5, and this is 4 plus 2 6. So the hexadecimal characters corresponding are 6 5. So I can compare it like this, which is valid. And if I return this also, you can see that it will indeed return 0x65. So let me save it, deploy, and now I'm going to call this function f. Since it has successfully passed, it has returned me 0x65, and also both these assertions have successfully passed. So I hope with this example it is very much clear to you, and not the individual characters. Yeah, it is fine, but you can, even though this will return the characters byte representation, which is the low level byte, not the individual character, but you can still compare it like this and even assign. Now about the functions bytes.concat and string.concat. You can concatenate an arbitrary number of string values using string.concat. The function returns a single string memory, so yeah, it's in memory array that contains the content of the arguments without padding, so there is no additional padding added. If you want to use parameters of other types that are not implicitly convertible to string, you will of course need to first convert them to string. Analogously, we have bytes.concat function, which concatenate an arbitrary number of bytes, or bytes 1 to bytes 32 also, you can pass here them also. The function return a single bytes memory array that contains the content of the arguments without padding. if you want to use string parameters or other types that are not implicitly convertible to bytes, you need to convert them to bytes or bytes 1 to bytes 32 first. Like here they have an example, string s, which they have named storage because it is actually in storage, and then they have this function f, which are taking a bytes array bc, which is in call data and hence the name bytes call data bc. Then string memory sm and simple 16 bytes byte b. In this they have concatenate, since the string.concat returns a string in memory, so that is why they are preferring to use memory keyword here. And to this they concatenate this storage string bc. They are converting, typecasting it, the bytes to the string, and another string literal. When we will cover string literals, this will actually be in memory. And then sm string memory, they are concatenate, and they have verified that yes, its length is equals to the concatenate string length to make sure that there are no padding. Then they have done similar thing to the bytes. So concatenate bytes s to get the byte representation of s, explicitly converting the string s to its low level bytes. Bytes call data, this is called slicing. Basically they are taking the first two elements here of this bytes call data, then the literal, and then bytes sm. So if you add all of their individual lengths, here it is done 2 because as I told, the first two elements, and literal has length 1 2 3 4 5 6 7, so yeah, 7 here. So they are verifying the length is indeed equal. So a simple example. And if you call string.concat or bytes.concat without arguments, they return an empty array. Next, let us talk about allocating memory arrays. The thing which you need to understand about memory array, that in case of storage arrays we could increase or decrease their length, but in case of memory array you cannot as such increase or decrease. Basically the push pop are not available. You have to assign to that memory array a new array. Basically, if I show you the example which I had written here, this memory array, I could not do push pop to it, but I have to replace it with a new thing and then assign it. I made a new array of length 6 and I assigned it, but now if I want to change its length to say 7 or 8, I need to then again do this, m equals to new int 7, right? I cannot just push a value back. Maybe it will become more clear when we will read this description. Memory arrays with dynamic length. Here this memory array is indeed of dynamic length because I can assign any length to it, right? Can be created using the new operator as we just saw. As opposed to storage arrays, it is not possible to resize memory arrays. Example, the .push member functions are not available. You either have to calculate the required size in advance or create a new memory array and copy every element. So suppose here if I decide from 6 I need to say 10, then I will need to create a new array of 10 and copy the first 6 elements like that or something similar. So this is about memory array, that they have this restriction on them. Also, function can take as the input size and then I could declare the memory of that size. So that is also possible. Continuing, as all variables in Solidity, the elements of newly allocated arrays are always initialized with the default value. Basically the byte representation will be 0. Here initially all these 6 elements will be 0. So they have this simple example here. This function is taking the length, about which length they have to create this bytes array. For this another array which is of unsigned integer, they created this of length 7 and they have verified their length and have assigned the 7th element to 8. So a simple example, we have covered such examples before. Now let us talk about array literals. Basically, if I want to write something like this, so instead of this, some array, whatever. So uh, this expression would be an array literal. However, in this case, I won't be able to do it. We will see why. But this right-hand thing, if you focus on, this is called an array literal. So an array literal is a comma separated list of one or more expressions enclosed in square brackets. For example, this 1a f3, where f3 will return a type which is of these two types. A will also have the type of this. The type of the array literal is determined as follows. It is very important, this part, pay attention. It is always statically sized memory array whose length is the number of expressions. Basically, if I write something like this, means I'm going to return this int 3. This, let me write it here. Where is it? Yeah, it will be this int 3 static array. If I write something like 4, 5, 6, basically an array containing 3 elements, then the type will be int 3. It won't be this, it won't be dynamic array but static. And this was the part which I wanted you to pay attention. The base type of the array is the type of the first expression on the list, such that all other expressions can be implicitly converted to it. It is a type error if this is not possible. Here 1 will fit inside uint8, and the smallest type in which this integer can fit, which is provided to us by Solidity, is uint8. Unsigned integers, as I have told before, are considered smaller than their signed counterpart. So here a should also be of the type uint8, and similarly f3. Suppose if this was int 256, then the a could be int 8, int 32. Basically, it should be implicitly convertible to int 256. We will see about this implicit conversion shortly afterwards. So I hope this much is understood to you. And also, it is not enough that there is a type all the elements can be converted to, but one of the elements has to be of that type. And for the first expression, it will be determined the type of the first expression wins, and all other have to be implicitly convertible or either be of that same type. So they have an example below, and inside this 1 2 3 is uint83 memory. Since our array literals are always in memory, it is always statically sized memory array, so its type is this uint8 3, because 3, and uint8 I told you why, and memory keyword. Because the type of each of these constants is uint8. If you want the result to be uint3 memory, then you simply typecast the first one to uint, and all others, this uint8 will be implicitly convertible to that. You need to convert the first element to uint, as I have told you, like what they are doing it here. The array literal 1, -1 is invalid because the type of the first expression wins. In this case, it is uint8, whereas this is int8. Is invalid because the type of the first expression is uint8, while the type of the second is int8, and they cannot be implicitly converted to each other. To make it work, you can use this to make the first type int8, for example. Since fixed size memory arrays of different type cannot be converted into each other, even if the base types can, it is what it is. If you have a uint8 of size 3 memory array, and the other array is uint, simple uint, 256 bits of size 3 memory array, the uint8 one cannot be converted to the uint1, even though the base types can. You always have to specify a common base type explicitly if you want to use two-dimensional arrays. So let us see this example. Contract C, function f, public pure returns this uint24, 2,4 memory. They have this array uint24, 2,4 memory x, and now look at all these. This array which they have not named here, okay, we have an array x here. This array contains 4 elements, and each of those elements is this uint24 2. So each of these elements contain in on the other hand 2 elements of type uint24. So 4 elements of this type. Now all the other arrays should be of this type uint24 0x1. I mean, yeah, this all the other arrays should be of this type. Here, ignore this note which keeps on popping up. It is not correct either. I wrote it long time ago. So here, unlike in our previous example, where these, if they could be implicitly convert to this, they will convert, but it won't be here because all of these are arrays in themselves and they cannot implicitly convert to another thing. So each of these should be explicitly of this type only, uint24 2, basically an array of 2 uint24. So if we notice also, this array is indeed of this type because the first element is explicitly made uint24 and this element 1 of the arrays can be implicitly converted to uint24. So this array indeed is of this type uint24 2. Similarly for this array, because this number is 24 bits long, if you count the number of f's here, 1 2 3 4 5 6, 6 into 4 is 24. So it is 24 bits and the smallest type in which it can fit by default is uint24. So it is indeed of type uint24 and this 2 will be implicitly converted to this type. So the type of this whole array is this uint24 2. Similarly, here also we have made it explicit and here also we have made this explicit. So all of these is having this type only. Now they have written that the following does not work because some of the inner arrays are not of the right type. So that is what we can see here itself. Moving on, fixed size memory arrays cannot be assigned to dynamically sized memory arrays. That is, the following is not possible. This is something which you should keep in mind. So since this we have a memory, we have a array literal expression which is in memory and its type will be uint3 and its type is dynamic, so you cannot assign a fixed size one to dynamic one. So that is what they have written. It is planned to remove this restriction in future because it is quite cool, if I can write like this, but it creates some complications because of how arrays are passed in the ABI. So if you want to initialize dynamically sized arrays, you have to assign the individual elements like so, like how we did in our example of for loop, right? Next we have array members, not many, just 4 members here. The length, arrays have length member that contains their number of elements. The length of the memory array is fixed but dynamic, that is, it can depend on runtime parameters. As I showed you in the example, I told you that here I can give a size parameter and then initialize this using size. So that is all possible. The length, but whatever the size we give, ultimately we have the memory array of that size. I cannot push and pop on that. I can change the size, but whenever I change, I give it a new fixed size. So I hope that is clear. The length of memory arrays is fixed but dynamic, that is, it can depend on runtime parameters once they are created. So I hope this was clear. Push, dynamic storage arrays and bytes. Only for these two types we have the push method available. So it is not available for string. Have a member function called push that you can use to append a zero initialized element at the end of the array. It returns a reference to the element. So you can modify that element also so that it can be used like x.push. Now this will push a new element to the end of the array and it will return the reference to it. And suppose that new element has something known as t, basically a struct. It could be a struct. So we will see what are structs. So inside it, it can have some another element and we can assign the value 2 to it. Or simply once we do an array.push, I am getting a reference to the newly inserted element which was inserted at the last of the array, and suppose to that element I want to assign some value, I can simply do like this. Next we have push x, which is also applicable only to dynamic storage arrays and bytes, so not strings. Have a member function called pushx that you can use to append a given element at the end of the array. The function returns nothing. Then we have pop, which is also applicable only to dynamic storage arrays and bytes, but not strings. Not strings. Have a member function called pop that you can use to remove an element from the end of the array. This also implicitly calls delete on the removed element. Yeah, implicitly delete is being called. Basically, you yourself are not using this keyword delete, but pop will do that work for you. So regarding this delete, we will cover it later. We have a note here. Increasing the length of the storage array by calling push has a constant gas cost because storage is zero initialized. It is when you have a storage array, suppose it is an int 8 array, int 16, int 32, it could be a bigger type array also, array of arrays, yeah, things like that. And if we have suppose an array of structs or array of arrays, then the element of that outermost array, which itself would be either a struct or an array, is not a one word long, it could be more than one word in size, right? And when we do push, we get a reference to that zero initialized element. But since storage by default is zero initialized, even if that thing which the element size is suppose 20 words long, even then the gas cost is same as if the element size was say one word. So I hope this was clear, because we are not going to assign anything in push, we just get the reference to that, like a pointer to that storage location. And since storage is zero initialized, there is no additional work involved. While decreasing the length, however, by calling pop, it has a cost that depends on the size of the element being removed. So if the element is say 4 words long, to each of them four words, we have to make the byte representation 0. So yeah, it is dependent on that size of the element in case of pop. If that element is an array, it can be very costly because it includes explicitly clearing the removed elements, similar to calling delete on them. So I hope this thing is clear. Now let us try to understand this note. To use arrays of arrays in external instead of public functions, you need to activate ABI coder v2. Now personally, I don't find it much satisfactory, their description. So let us try to explain it. And first of all, regarding this arrays of arrays, this thing might work even if we are using v1, because if you try with integers, array of integers, array of integers, it will work with v1. But for the a little bit more complex, like say array of structs, we will see structs later soon, or array of strings because string in itself is an array, then you will see that we will need v2 ABI coder. So here I have an example, and also I would like to take this opportunity to explain about struct. There is no need to see structs for the example that I have, but I still feel like that I can cover it now. Suppose I need to have a compact and abstraction over my students, like each student might have variety of properties, the overall grade, the courses he or she has signed up for, and so on. Instead of having multiple arrays of say grades, this is already a 2D array because string in itself is an array, and I'm having an array of strings. So if I were to create a 3D array where the first index, if I were to create something like this, string this and this, where this one will map to the student index, and then here is that same as the courses part. Basically I created one more, I meant this, sorry, I meant this, where this is for the student part and then these are the courses for the student. And we name structs using cap word style. So if I had some another struct, say weather, forecast, and so I'm following this cap word style. I would suggest you to read the style guide which we saw at the very beginning of our course. Maybe initially, whenever you're writing something in Solidity, you can have a look at what the style guide recommends, because Solidity is a language where I see this to be more applicable, because you would want to have a peer review or to share your code with the auditors, and you should try to make their life easy while they are reading your code. So here I have a student S, a single student S. If I wanted multiple student, I can have an array of students itself, but for now let's keep the thing simple. I have a student S. Now notice these two functions which I wrote. This function is taking an array of strings. So it's an array of arrays because string in itself is an array. And this has the visibility of internal. And when I'm saving this file, I'm getting errors here, but this function is not giving me an error. And one more thing, I'm using specifically the version 1 of the ABI encoder, not the version 2, which is enabled by default. I'm using version 1. So in this function, this one is not compiling because this function can have visibility both internal as well as external, because public means that this function can be called either internally or externally. Regarding this internal external, we will see that later too, but I think you have an idea by now. So this one was compiling because it was internal, but this one is not compiling because the visibility also supports external here, and I can make it also explicitly external. Even then it is not compiling. Alright. Now what this function is taking, it is taking an grade which I will assign to this student, and also the courses which I'm going to assign to this student. So that is what I have done here. I have assigned the grade and I have assigned the courses. These two assertions we need not bother. And also I'm going to return my courses. Basically what I want to show via this return part is that if you look at the two errors which the Solidity is giving me, it is giving one for this return part and one for this part. And reason for both of these is because I'm using the version 1. If I were to comment this out, and that we need not enable because it is by default enabled, we need not explicitly write. So if I save it, you see the errors have disappeared. So in short, this is what they meant. This is the power of ABI coder v2, which is enabled by default. Even if I write it, this won't create any change. Now I hope you have understood this function. Basically, to this student element S, I am assigning the overall grade and also I am assigning the courses. This is in memory, this is in storage, so a copy operation will occur here. And then I'm just returning the courses part. This is again, I just added it here. It was not, but the thing which I want to show you about returning this s.courses part is that I'm returning an array of arrays, that too which is in memory, not in the call data, and it is fine. Even this is in the support of ABI coder v2. I mean, the support of the ABI encoder v2 is in this part, array of array, when I'm returning an array of array, not with regard to memory. I mean, that thing is valid even in v1. For instance, if I make this like this, and here let's return say one course, the very first course, and let's disable it and let's enable it, you will see that it still compiles with just one error. What is that? Oh, regarding this part, the error is only about this part, but it is not about the return part. So return part, I was just clarifying that it is, I mean, this memory thing which I have also said before, that you can return memory, and even for that matters storage reference can also be returned, but then in case of storage you use the internal visibility. So this returning of array of arrays is because of our ABI encoder v2. So these are the two supports I showed you, which is what ABI encoder v2 is helping us with. Also, they have this note, but it is actually quite irrelevant. What they are saying that in EVM versions before Byzantinium is an upgrade version of EVM. So it was not possible to access dynamic arrays returned from function call. If you call functions that return dynamic arrays, make sure to use an EVM that is set to Byzantinium mode. So we need not bother about it. It's a thing of past now. Let us now look at array slices. Array slices are a view on contiguous portion of an array. They are written as x start colon end, where start and end are expressions resulting in a uint 256 type. So your start and end should be implicitly at least convertible to uint 256. The first element of the slice is x start, whereas the last element is x end minus 1. Let us first read this, then I will explain with an example. If start is greater than end, or if end is greater than the length of the array, an exception is thrown. Both start and end are optional. Start defaults to 0 if you don't present it, and end defaults to the length of the array. So having read this, let me explain with the help of an example. Suppose my array x is this: 3, 8, 2, 5, 18, 200. This is my array, and if I change the color, this is at index 0, index 1, so on, 2, 3, 4, and this is at index 5. Array length is 6. Now if I want a view of say these 3 elements, then I can make a slice where I want it to start from this index 1. So I write here 1 and end it just before index 4. So this will translate to an array having this x1, x2, x3. This is what it will get translated to. So when we write this start and end, if this is start and this is end, then the slice elements are from x start till x end minus 1. X end is not included. And if you don't mention the start, if you have just written like this x, you don't mention start, but you mention some end, then it is equivalent to an array where it starts from x0 all the way to x end minus 1. Similarly, if you don't mention end, then it is the length of the array, and end defaults to the length of the array. Alright, array slices do not have any members. In case of array, we saw we had members like push, pop, length, etc. But when we do a slice, those members are no longer present. They are implicitly convertible to arrays of their underlying type, and support index access. Index access, that for this array I can access some index. Suppose if I do this, the second element, then I will get x2. This is the index access and implicitly convertible to the underlying type. I hope it will be clear to you also. Index access is not absolute in the underlying array but related to the start of the slice. As I showed you, when I did this one, then for this slice I am saying second element, not the second element of the original array, which was 8, right? Array slices do not have a type name, which means no variable can have array slice as type. For instance, for integers, like if I do this, then I know its type. Its type is an array of integers. But when we do a slice, we cannot have array slice type. Some variable. We cannot have like this. Just like, in case of our normal arrays, we had this array type, some variable name. But for array slices, we cannot do such a thing. They do not have a type name, which means no variable can have array slice as type. They only exist in intermediate expressions. As of now, array slices are only implemented for call data arrays. So if your input have a call data, the call data input, only in those you can do this array slice thing, not for your storage or memory arrays. They have a very simple example. Let's go over it, not for the sake of array slices, but even otherwise it will further clarify about signature and catch-check hash, which we used to compute signature. Now they have this address client constructor. We need not much bother about it. Then forward call to set owner address, that is implemented by client after doing basic validation on address argument. We'll make this clear. Basically, now some function is going to call, some contract is going to call this function of some other contract, but immediately calling that another contracts this function, it will first call this intermediary, this proxy contract, which will verify that indeed everything was done correctly. So we know the first 4 bytes will give us the signature, right? But they are saying there was no need to do array slice here, because even this typecasting to the first 4 bytes will give us the first 4 bytes. So irrespective of doing array slice or not, we would have gotten the first 4 bytes like this. Then they are verifying that yes, the signature is indeed correct or not. If it was correct, then we know that this function is taking as an input the address parameter. So after the signature, the input will be provided. So they are decoding that address input, just like how we also did previously. And now they are verifying. So this intermediary job is this: it is going to verify that whether the address of owner is correct or not, or here they are checking whether it's a null address or not. So this require simply means that if the condition is not true inside this parenthesis, an exception will be raised. So bool status, they are doing this delegate call. We will cover this delegate call later. And they are doing delegate call to this client, which they set the deployer of this contract gave this client address, which was stored in the contract's storage. So they have this note. We will cover these comments also. What this @dev means, we will cover. Address of the client contract managed by proxy, that is this contract. This contract name is proxy. So let's also read this comment now after we have seen the function. And in the end there was one more required statement, which was checking this condition whether it's true or false. If it is false, then an exception will be raised with this message that the forwarded call failed. And just the comments also, the forward call to set owner address that is implemented by client. This client is implementing this function after doing basic validation on the address argument. So I hope this is clear. Basically I wanted to show this line, how they are decoding. We also decoded ourselves, but this signature part and all. So yeah, the slice was also used here. Now let us just finish looking about structs. So Solidity provides a way to define new types in the form of structs, which is shown in the following example. Just like how we had a student data type, the abstraction. So that is what this struct is. One more thing, that declaring a struct outside of contract allows it to be shared by multiple contracts. So basically struct can be declared at the file level outside of contracts. So here like they have declared this struct which goes by the name funder. So this contract crowdfunding, and even if there is another contract, both can have a variable of this data type funder. So we have seen one more global variable, global symbol. Also struct types can be used inside mappings and arrays. We haven't seen mapping, we will see shortly. And they can themselves contain mappings and arrays. But pay attention that in case the struct contains a mapping, then the data location has to be storage, because mappings are only allowed in storage. Also, it is not possible for a struct to contain a member of its own type. In our example, we had the student structure. So inside the member of that structure, we had grade, we had courses. I cannot have one more member of type student. This is not allowed in Solidity structs. Although the struct itself can be the value type of a mapping member, or it can contain a dynamically sized array of its type. Basically, mapping, as we will see, it is a key value pair. So for a given key, the value can be a struct. That is something unrelated here. And the value can also be a dynamic array of that type. Their justification of why this restriction is there. This restriction is necessary as the size of the struct has to be finite. So if the struct can contain an element of its own type, then due to recursion, they are having this problem. And this is with regard to their example. I'm not going into their example because I have explained you as such. Now let us look at mapping types. So mapping types use the syntax, a keyword mapping, then you give it a key type, and then you write this arrow symbol and then a value type. We will see an example. And variables of mapping type are declared using this syntax. Here they have declared this variable of this mapping type. Let me first finish this para, then I will show you the example. The key type can be any built-in value type. So all the built-in value types which we saw, like bytes 1, bytes so on till bytes 32, address, different types of integers and so on. Then also the key can be this bytes array or strings array or any contract or enum type. So besides what they have told here, you cannot use any other thing as your key type. Other user-defined or complex types such as mappings, struct or arrays types are not allowed as keys. So your key cannot be a mapping again or a struct or an array. So the key cannot be like that. But value can be any type, even including mappings, arrays and structs. So let us now look at the example to have this cleared on our mind. So we have an example here. We have declared a contract which goes by the name mapping example. Now here we have declared this type, this variable balances of this mapping type. So how do we declare a mapping? We first write the keyword mapping, then inside the parenthesis we give it the key type. Here the key is address, and to the corresponding key I am going to assign an integer. Like we have this function update. which will take in an unsigned integer which goes by the name new balance. Now what it is going to do, inside my mapping, which is a key, which to the mapping you give it the key. In this case the key has to be of the address type, and to that key the corresponding value. In that value we are assigning this new balance. So this, by the way, this message dot sender is basically the address of the entity calling this function. So message dot sender contains that address, the person or whatever who is calling this update function. So you can think of mapping as hash tables which are virtually initialized such that every possible key exists and is mapped to a value whose byte representation is all zeros. So in this example we declare this mapping balances. Here you can put in any key. When you are assigning to your mapping, you can put in any key to put your value. Basically, like here we have our mapping. A way to visualize it, we have this key value pair. Now suppose I am thinking of some xyz key, then I need not worry because I can put in that key, and to that key I can put some value. So all the possible keys, like here in this address type, you can put in any address. It's fine. You can put in any address, and for to that address whatever the value you want to give, you can give. Initially that value will be 0. So in case in this example itself, if I were to do balances some key which I have not previously assigned some value, some non-zero value, then by default if I query this, this will have value to be 0. The byte representation would be 0 of the value type which you are assigning. In this case an unsigned integer, so output will be uint 0. So this is what they meant, and basically they have compared it to an hash table, just like a key value pair. A hash map, a hash table, like hash is the corresponding data to an output. So similarly, like usually in languages like C++, mapping use something like red black tree. Here they are comparing it to an hash table. So if you have studied previously about hash table, fine, then even otherwise there is like no need to worry. I have told you it's just like a key value pair. Okay, yeah, this we have done. The similarity however ends here. The key data is not stored in a mapping. So for this balances array, I have no method to get the keys which are inside this balances array. Suppose to this balances I have assigned some address having this value, then some other address having that value. Now after I have done those assignments, there is no way for me to ask my mapping, can you tell me what are the keys that I have assigned values to? No, I cannot do that. Now this is like difference in what you will see in other languages. In other languages, like you can get the keys which you have put in your mapping table or structure. I mean whatever data structure, need not be a table in other languages. So yeah, the similarity ends there. The key data is not stored in a mapping, only its catchex hash, catchex 256 hash is used to look up the value. When I am doing this address, what it is happening is that it will take the hash of this address and that will give me the key, and to that key I am assigning the value. So when I want to now query what is inside this balances, suppose I have now assigned this. Now I want to return a balance of a particular address. Then I can do this, return balances my address, whatever the address balance I want. So some address. Now in this case, when I do this key, actually the catcheck hash of this address will be computed, and that will be used as a key to get the value for that key inside this mapping. So I hope that part is clear. Because of this, mappings do not have a length or concept of a key or a value being set, and therefore cannot be erased without extra information regarding the assigned keys. Since this mapping table we are having, each element is virtually initialized to 0. So suppose in this mapping I am putting some balances. What I'm assigning is that for some address I am assigning its balance to be 0. Now since there are many addresses, every possible address is having the value already 0, and to some address I am assigning 0, I might assume that in my mapping I have one key added. This key for this address I have added a key which I can perhaps query later inside my balances. But since already all other addresses are having this equal to 0, so that concept cannot exist. I hope this made sense. So there is no concept of length. I cannot ask what all entries I have put inside this mapping. That is not possible, and I have given you an example also where you can make sense of that, or a concept of key or value being set, because that we are not doing here, and we cannot ask what are the values we have set. All you can do is that you give me a key, and to that key I can give you a value. You can assign a value on that key, and therefore cannot be erased without extra information regarding the assigned keys. So if you want to erase an element inside a mapping in Solidity, erasing is considered as assignment only, where you are just assigning the value 0, the default byte representation, because that is how initial state is. So if you want to erase a key, you simply put in that key and make it equal to 0, like that. But of course, if you can store your keys in some another data structure, you can have a mapping, and then you can perhaps have a other data structure built which can keep track of your keys. So that's possible. Mappings can only have a data location of storage, and thus are allowed for state variables as storage reference types in functions, or as parameters for library functions. I think this is very much clear to you, but the library part will become clear once we will do library. They cannot be used as parameters or return parameters of contract functions that are publicly visible. This also I have told before. These restrictions are also true for arrays and structs that contain mapping. We have covered this. You can mark state variables of mapping types as public, and Solidity creates a getter for you. Now let me just quickly tell about this public variables. When we declare a state variable as public, then what we get is a feature that anyone outside this contract can query this variable to get its value. But one caution I would like to add here: this public keyword is having this functionality. I will show you an example in Remix 2. But even otherwise, even if it was not public, then as such, as it is a state variable, it is stored in blockchain. So one can see in blockchain too. So it does not save you from that. But the public keyword, let me show you an example. Like here, I have a simple example. Here this variable a is of type unsigned integer. Now if I want to get the value of a, then either I have to write a function like this. The support should be there in the contract, like this get a function I have declared, which is going to simply return this value a. But if I have marked this variable with public keyword, then Solidity itself will declare a function like this. Let me just write it. This is what Solidity will write for us when we declare the variable as public. So if I were to show you, let me just deploy this contract. In this deployed contract, see, I already have a function a. Even though I have commented this out, even then I have this function a, and if I use this function, you see I'm getting 4, and I have declared my custom function also, that is also declaring the same thing. So when I declare the variable as public, Solidity automatically creates this function known as the getter function. Let us also cover a bit more about getter functions so that we are able to understand about a mappings getter function better. So I'm here in this part of the Solidity documentation. The compiler automatically creates getter functions for all public state variables for the contract given below. They have this contract, very simple contract. They have this contract which goes by the name C, and inside they have a public unsigned integer data variable having the value 42. Then they have another contract caller. Inside this caller contract, as I told you, contract types also exist. They have declared a variable small c of the contract type capital C, and they are creating this new contract, basically instantiating another contract whose layout is this, and layout is this, Solidity layout is this. So they are generating a new contract, just like how we can deploy multiple contracts having the same code. Similarly, what they have done is same thing here, instantiating a new contract having this code. Inside this contract, caller contract, they have declared this function f, which is simply accessing the getter function. When, as you can see, c dot data, since c is some other contract, I cannot access state variables like that. There has to be a function, and you can see the getter function was generated. So for the contract given below, the compiler will generate a function called data that does not take any arguments and return an unsigned integer. The value of the state variable data, which is the value of the state variable data. State variables can be initialized when they are declared, just like how they have initialized it here. The getter functions have external visibility, that is, they can be called by external functions. That is the whole point. But there is a small catch. If the symbol is accessed internally, that is without this keyword, we will see the example here, then it will become clear. It evaluates to a state variable. If it is accessed, however, externally, that is with this keyword, it evaluates to a function. Like we have this contract C, a public state variable named data. Inside we have a function x. Now when I'm just doing like this, data equals to 3 or return data, then I'm accessing this function internally. But when I'm doing this dot data, then I'm calling the getter function externally. A new EVM context will get generated where that function will be executed, and its value will be returned to me via memory, as we have seen all those things. A new transaction message will happen where this call data part will have the variable data. So that is how I am going to get when I'm doing this keyword. So this keyword is, as you saw here, used to access the contract externally, basically just like how some other contracts function I call, like I showed you in the very beginning, different ways of calling a function of some other contracts. So if you want to call a function of your own contract externally, you use this keyword. So I hope this thing has made sense. Continuing further, if you have a public state variable of array type, now this is a bit more complexity. For the array type, the support is there to return a single element of the array, not the entire array. Let us read. Then you can only retrieve single elements of the array via the generated getter function. This mechanism exists to avoid high gas costs while returning an entire array, and you will really want to return an entire array. But in case you want to return an entire array, you can write a function for it, of course. That is not an issue. So let's look at the example that they have. They have declared a contract by name array example. Inside it, they are declaring the variable myArray, which is a public array of unsigned integers. So since it is public, this function will get generated as they have shown. MyArray, same as the variable name, then the index which you will give to get the element at that index. So yeah, that is this function returning myArray at the ith index, the element. And here they have given another example in case you want to return an entire array. So yeah, they have shown an example for that also. So you can use arguments to specify which individual element to return. For example, myArray0, when you are calling this function, as it is taking the argument for the index, you need to give the index here. If you want to return an entire array in one call, then you need to write a function, for example, which they have shown here. Now you can use getArray to retrieve the entire array instead of myArray which returns a single element per call. Next, they have a cool example which is more complex than what we have done before. So they have this struct named data. Inside it, they are having this value type A, a value type B, then a reference type map, then again a reference type, but the fixed size array of 3 elements, C, a dynamic array, then a bytes array. And now they are declaring a mapping which takes the unsigned integer as a key and returns this value. Since this value in itself a mapping, you can give it a boolean key, either true or false, to get the array of data. So this array of this data type. And inside, since this is an array, you can again pass a key to get a particular data. Now they are saying that it will return this getter function. This is for this unsigned integer key. Next key is for this boolean part, and the next key is for this data array, and this is where it ends. They are like say giving up because they are not giving key for this inside map, this C array and this D array. So what it is going to return is only A part, B part and this E part. So let us also read. It generates a function of the following form: the mapping and arrays with the exception of byte arrays with the exception in the struct are omitted because there is no good way to select individual array members or provide a key for the mapping. Perhaps since the bytes array is compact, it's a sequence of bytes and you will really want to access the individual byte, but usually the whole bytes array. So they are returning that, but not the other things. Since they are not asking for the other things key, they are not returning them also. So this is, I think, quite enough to understand about getter functions. So if we now read this para, you can mark state variables of mapping type as public, and Solidity creates a getter for you. The key type becomes a parameter for the getter. If value type is a value type or a struct, the getter returns value type. But if value type in itself is an array or mapping, the getter has one parameter for each key type recursively, just like what we saw. Next, they have an example. We need not cover about this example as we have already understood mapping. Similarly, they have another example which we need not see. Regarding this iterable mappings, they have shown how to create such an iterable mapping. But again, this is of no concern to us. As such, we have learned about mapping. If you want to read about this section, you are free to read. As such, if you were to implement, say in practice, an iterable mapping, most likely you will be using a trusted library for that. Open Zeppelin, there is this word Open Zeppelin which has uh, sort of like released many such utility libraries, and they also have enumerable map to help us in that regard. Next we have operators. Arithmetic and bit operators can be applied even if two operators do not have the same type. For example, you can compute y equals to x plus z, where x is unsigned integer 8 bit size and z has the type integer 32 bits. In these cases, the following mechanism will be used to determine the type in which the operation is computed. That this is important in case of overflow, and the type of the operator's result. So as I told you previously that we will cover this later, so we are covering it now. If the type of the right operand, here z, can be implicitly converted to the type of the left operand, use the type of the left operand. But here, as we can see, we cannot convert because it is 32 bits, whereas the left part is 8 bits, and also it is unsigned. If the type of the left operand can be implicitly converted to the type of the right operand, use the type of the right operand. But in this example, it should not be possible to convert a type uint8 implicitly to int32. So I think they have an error here. I mean, this won't work, this plus symbol. So maybe the documentation has mistake here. Here the left operand cannot be converted to the type of z operand. But if it could be, then do that. Otherwise the operation is not allowed. So here the operation should not be allowed, in my understanding. You can see that in Remix 2. In case one of the operands is a literal number, it is first converted to its mobile type, which is the smallest type that can hold the value. Unsigned types of the same bit width are considered smaller than the signed counterparts. If both are literal numbers, the operation is computed with arbitrary precision. So I think this is clear in itself. The operator's result type is the same as the type the operation is performed in. Like here, we founded the type in which the operation is done, so that type will be the return type also. Except for comparison operators, where the result is always bool. The type is changed. Comparing ints does not give you an integer but a bool. The operators exponential and the shift operators use the type of the left operand for the operation and the result. This is something which we have seen previously also. Moving on, let us discuss about ternary operator. The ternary operator is used in expressions of the form this first expression. If the first expression is true, then this true expression is computed and returned. Otherwise, the false expression is computed and returned. We have seen this before. It evaluates one of the later two given expressions depending upon the result of the evaluation of the main expression. If expression evaluates to true, then true expression will be evaluated. Otherwise, false expression is evaluated. The result of the ternary operator does not have a rational number type. Basically, it even does not have a normal number literal type, because when we use this ternary operator, both of these expressions, the true expression and the false expression, must return a type. It cannot return our number literals. It should return a type. Like this is not valid, as I will show you later, because we don't have any type for 1.5, a rational number to which we can assign to. So even if all of its operands are rational number literals, the result type is determined from the types of the two operands in the same way as above, converting to their mobile type first if required. Like this ternary operator which we have, it won't return me a number literal, but will have to return me a value type for this example as a consequence. So here, since it is true, 1 is being returned, so 1, we will find the mobile type of 1, which is the smallest type where this can fit, and unsigned are considered smaller than the signed counterpart. So uint 8 here is what will be returned by the ternary operator. Now a uint 8 plus a literal expression, so its mobile type will be computed here. We had a rule for it, in case one of the operand is literal number. So again uint 8, so uint 8 plus uint 8, we can do this addition, but 255 plus 1 should be 256, which is above the range of uint 8, so an exception will be raised here, will revert due to arithmetic overflow. The reason is that true, this ternary operation is of uint 8 type, which forces the addition to be performed in uint 8 as well, and 256 exceed the range allowed for this type. Also, in case of ternary, we saw that both of these should return the same type. Another consequence is that an expression like this 1.5 plus 1.5 is valid, but 1.5 plus this ternary expression is not, because as we know that for ternary expression it has to return a type, and we don't have a rational number type, as at least as of now, in Solidity, to which we can assign some value. So since this cannot return, this whole expression is not valid. This is because the former is a rational expression. These are both can be evaluated, and since the result will fit into one of the Solidity type, this is valid. Evaluated in unlimited precision, and only its final value matters. The latter involves a conversion of a fractional rational number to an integer, which is currently disallowed. Next we have compound and increment decrement operators. If a is an L value, that is a variable or something that can be assigned to, the following operators are available as shorthands. A plus c you can simply write, which is equivalent to writing this a equals to a plus c. Similarly, the operators minus, equal to, and so on. Next we have a plus plus and a minus minus, which are equivalent to a plus equals to 1 and a minus equals to 1. But there is a small catch. Basically, just like in other languages, this postfix and prefix has a difference. Here when we do this plus plus a, then a plus equals to 1 and it will return the new value, the updated value. But when we do a plus plus, although a will be updated, but this expression in itself will return the previous value. So if I do something like int b equals to a plus plus, although a will get incremented, but a previous value of a will be assigned to b. But the expression itself still has the previous value of a. In contrast, minus minus a and plus plus a have the same effect on a but return the value after the change. Next, we have the delete keyword. Finally, we will understand this also now. Delete a assigns the initial value for the type to a. So it is basically like an assignment where we are assigning the initial value, which is the low level bytes having 0 value. So 0 representation of those bytes. That is for integers, it is equivalent to doing a equal to 0, basically assigning a to value 0. But it can also be used on arrays, where it assigns a dynamic array of length 0 or a static array of the same length with all the elements set to their initial value. So in case of dynamic array, you assign a dynamic array of length 0. In case of static array, you assign a static array where all the elements are having that elements as 0. Those elements as 0. So delete ax, however, will delete the item at index x. Basically, it will assign the 0 to that index x, 0 representation having of those bytes. I hope you get it. Of the array, and leaves all other elements and the length of the array untouched. This especially means that it leaves a gap in the array. If you plan to remove items, however, a mapping is probably a better choice. For structs, it assigns a struct with all members reset. In other words, the value of a after delete a is same as if a will be declared without assignment, with the following caveat. Delete has no effect on mappings, as the key of mappings may be arbitrary and are generally unknown, since we are not mapping in itself does not maintain them. So if you delete a struct, it will reset all members that are not mapping, and also recurs into the members unless they are mappings. Struct can contain some other struct, so like that recurs. However, individual keys and what they map to can be deleted. You can delete some individual key at a particular index where it will just assign 0 to it. If A is a mapping, then delete AX will delete the value stored at X. It is important to note that delete A really behaves like an assignment to A, that is, it stores a new object in A. This distinction is visible when A is reference variable. It will only reset A itself, not the value it referred to previously. To understand this, let us look at the example which they have provided to us. A function f, where first of all this contract has two state variables, a data variable which is a value type and a data array which is a reference type, a dynamic array of types. The elements are of type uint. So when we do this, uint x equals to data, a copy has appeared. Now both of these are independent. X and data both are independent. So if I delete x, it is assigning x the value 0, but the data is not changed. Similarly, delete that will change this data but does not affect x. Now I'm doing this uint storage y data array. Now if I do some changes to y, for instance, since y is referring the same data array, I can change data array using y. This is something which we have done, but there is a small catch here which is related to this, that delete A really behaves like an assignment to A. Here, if I do delete array, then delete this data array, then this data array is basically assigned a new dynamic array of length 0. So this sets data array length to 0, but as uint is a complex object, also y is affected, which is an alias to the storage object. So this data array is deleted since y is referencing to it. The y length is also, you can say, 0. On the other hand, instead of doing this delete data array, if I had done delete y, then it is basically like an assignment to y, that we are assigning something to y and a new dynamic array of length 0, but that is not allowed. Delete y is not valid, as assignments to local variables which reference storage objects can only be made from existing storage objects. So if I were to assign it something, that has to be done using some existing storage objects, not otherwise. So I hope this line is clear with the help of their example. Next, we have conversions between elementary types. So let us first discuss implicit conversions. This will also clarify many things which you might have as a doubt in your mind. An implicit type conversion is automatically applied by the compiler in some cases during assignments, when passing arguments to function and when applying operators. We will see some examples now. In general, an implicit conversion between value types is possible if it makes sense semantically and no information is lost. For example, uint 8 is convertible to uint 16 because uint 16 can hold uint 8 and no semantics are lost. And int 128 bits is also implicitly convertible to int 126, but int 8 is not convertible to uint 256 because uint 256 cannot hold, say, negative values like -1, which int 8 can very well hold. So here the semantics have changed. So it's possible if it makes sense semantically and no information is lost. Unsigned remains unsigned, things like that. If an operator is applied to different types, the compiler tries to implicitly convert one of the operands to the type of the other, like we saw. The same is true for assignments also, as we will see. This means that operations are always performed in the type of one of the operands. So this is important for you to understand. So for more details about which implicit conversions are possible, please consult the section about the types themselves. We have seen all that. So this example is of particular interest. In the example below, y and z, the operands of addition, do not have the same type. Here, y and z, y is having uint 8 type, but z is having uint 16 type. As we saw, the rules will suggest that y, since z cannot be converted to y, but y can be converted to a uint 16, so y will get converted implicitly to a uint 16 type, and thus addition will be performed in uint16 type. Now the right hand side is uint16, however the left hand side is uint32, but since uint16 can be implicitly converted to uint16, and therefore it will get implicitly converted to uint16. So if we read also, these y and z do not have the same type because uint8 can be, but uint8 can be implicitly converted to uint16 and not vice versa. Because of that, y is converted to the type of z before the addition is performed in the uint16 type. The resulting type of the expression y plus z is uint16. Because it is assigned to a variable of type uint32, another implicit conversion is performed after the addition. So I hope this concept is clear. Next we have explicit conversions. If the compiler does not allow implicit conversion, but you are confident a conversion will work, then an explicit conversion is sometimes possible. For instance, here they have this int y equals -3. Now if I explicitly convert this y to an unsigned integer, can you tell what we will get? Let me show you. -3. So if I were to write -3 in the 2's complement notation, first let us write 3, which is this, and this is 2 plus 1 equals 3, and all other bits are 0. This is a 256 bit number because it's an integer of size 256 bit. Now to get -3 from 3, first we do 1's complement, which is basically bit by bit negation. You just find the negation of this number. So if I change the color, what I will get as a 1's complement is this 1, these are also 1 1, and these are 0 0, and to this I add 1. So this is the representation of -3 in the bit representation. But now once I have converted this to an unsigned integer, then that unsigned integer will have this in its binary representation. So what is this number? This is 2 the power 0 plus 2 the power no plus 2 the power 2 plus 2 the power 3 and so on till plus 2 the power 255, because it's a 256 bit long number. So to this, if I add and subtract 2 the power 0 and 2 the power, sorry, not 2 the power 0 but 2 the power 1, 2 the power 1 and 2 the power 1, then this part will be my simple geometric progression. And if I were to do that, the answer will be 2 the power 256 minus 1, and then again this minus 2. So it is this value. And we can verify that also in Remix. So here I wrote a simple example to verify that. I have my unsigned integer a, which is this value 2 the power 256 minus 3, and x which is equal to -3, just like what they have done, and unsigned integer y. To get the unsigned integer representation of x, explicitly typecasting it, and then I am checking whether a is equals to y or not. And if I run this function after deploying this contract, then it runs successfully, and hence our assertion is verified. Let us continue reading. This may result in unexpected behavior and allows you to bypass some security features of the compiler, like it is obvious. So be sure to test that the result is what you want and expect. They have explaining this example which we have seen, and we have seen that all. If an integer is explicitly converted to a smaller type, then higher order bits are cut off. For example, here they are declaring an integer a which is 32 bits long. So can you tell me how many bytes it is? 8, 16, 24, 32, 4 bytes. So 8 hexadecimal characters, and that is what they have written, 8 hexadecimal characters. So this will be the lower order 8 bits, this will be the lower order 4 bits, and so on, you can understand. So when we are explicitly typecasting it to uint16, higher order bits will be cut off, and now since we want only 2 bytes, these 4 hexadecimal characters is what which will remain inside this B when we are explicitly typecasting it. So yeah, the higher order bits are cut off. If an integer is explicitly converted to a larger type, then it is padded on the left, that is at the higher order end, with zeros. The result of the conversion will compare equal to the original integer. For instance, we have this 16-bit number A, and now we are typecasting it. So they have also given you what will be the final output, and therefore we have found B. Now when we are doing this comparison to check whether A is equals to B, then again typecasting will occur. Since uint16 can be converted to uint32 implicitly, because the semantics are not lost, we can do this comparison, and they are checking that yes, indeed A is equals to B. Continuing, fixed size bytes types behave differently during conversions. They can be thought of as sequence of individual bytes, and converting to a smaller type will cut off the sequence. Now this bytes 2, it is, you can think of it as an array of 2 bytes, right? Where the first byte is this and the second byte is this. In case of integers, you were seeing this as the lower order byte and this was the higher order byte. But when we discuss about these data type bytes 2 or the bytes dynamic array, then we start from here. This is the first byte and this is the second byte. So when I am explicitly typecasting it to single bytes type of bytes 1, then I am taking the first byte. So B will be 0x12. If a fixed size bytes type is explicitly converted to a larger type, it is padded on the right, okay, with zeros. Accessing the byte at a fixed index will result in the same value before and after the conversion if the index is still in the range. So we can see the example. We have this 2 bytes long A variable, and then I am typecasting it. They are typecasting it to the 4 bytes. So we had 2 bytes, another 2 bytes, that is 4 hexadecimal characters will come, which are having these 0 values. And if I compare the 0th byte, then it is same, and even the first byte, which 0th byte basically means the first byte here, and the first index byte basically means the second byte. This we have done. Alright, since integers and fixed size byte arrays behave differently when truncating or padding, as we saw for integers and the byte, there is slight difference in the sequence, the higher order and the lower order part. Explicit conversions between integers and fixed size byte arrays are only allowed if both have the same size. So because of this, they have this restriction. If you want to convert between integers and fixed size byte arrays of different size, you can of course go by intermediate route. So you can use intermediate conversions that makes the desired truncation and padding rules explicit, as they have shown in the example. They have this 2 byte long A, and then this 4 bytes long B, which is 32 bits integer. Now they are making this A, since it is 2 bytes which is 16 bits, I can explicitly convert it to an unsigned integer. And now this is an unsigned integer 16 bits long, which will get implicitly converted to an unsigned integer 32 bits long. So they have this B. We got the 32 from the 16 bit, we got 32 bit, just like what we wanted. Now we have C, where they are making the first A 4 bytes long, which will make it 32 bits long, and then they are doing this typecasting here. But you see, because of how int and bits behave differently, the expression is different. Now uint 8d, so basically they are just playing with this more so that you can understand better. But I hope by now it is pretty much clear. You can just look at this example if you want further clarity. Bytes arrays and bytes called data slices can be converted explicitly to fixed bytes type, that is bytes 1 to bytes 32. In case the array is longer than the target fixed bytes type, truncation at the end will happen. So that is for these bytes array, and slices is for call data, as we saw. If the array is shorter than the target type, it will be padded with zeros at the end. So we have a very simple example. This bytes s, and it is having these value. The string is getting typecasted to the bytes type. So it is how many length? 1, 2, 3, 4, 5, 6, 7, 8. So 8 bytes. Then they have this call data bytes type call data c variable. And now for this m, they also have this bytes memory, which is in memory m. To this, they are explicitly typecasting it to 16 bytes type. So only the first 16 bytes they are taking. So if length of m is greater than 16, truncation will happen, which is clear. And now byte 16s, as I showed you, it is having 8 characters, right? 1, 2, 3, 4, 5, 6, yeah, 8 characters. So when we do 16, then it is padded on the right. So the result is this: 8 more bytes. So 8 more bytes is added. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And now this taking the first 3 bytes of this string. So that is only ABC, B1. So B1 is equals to ABC. And now they are taking the first 8 elements of this call data array C. So the slice 0, they have omitted this, so that means it is 0. So 0, 1, 2, 3, 4, so on till 7. So first 8 elements. Since 16, so it is also padded to the right with zeros. So pretty simple example. Next we have this small section, conversions between literal and elementary types. So for the integer types, decimal and hexadecimal number literals can be implicitly converted to any integer type that is large enough to represent it without truncation. So 12 fits in 8 bits integer, unsigned integer. This also fits in unsigned integer 32 bits. Now this is a hexadecimal number. It is not same as writing u in 16 equals to 1, 2, 3, 4, 5, 6. No, it is a hexadecimal number where each of one represents 4 bits. So this is 1 byte, this is second. So it is 3 bytes long. So 8, 16, 24. So 24 bits is above 16 bits. So this cannot happen implicitly, as here the truncation is happening. So fails, since it will truncate this part 3, 4. It will truncate to this part because these are the lower 16 bits and this is the higher order 8 bits, the remaining part. So this last line, as I've also written in my notes, this last line won't compile here. Next we have this fixed size byte arrays. Decimal number literals cannot be implicitly converted to a fixed size byte arrays. So things like this is not allowed. Hexadecimal number literals can be, but only if the number of hex digits, each hex digit represents 4 bits, exactly fits the size of the bytes type. So in case here 2 bytes, so in that case I have to put in 4 hexadecimal digits because that will correspond to 2 bytes. So this one is not allowed because only 2 digits are there, whereas this one is allowed because exactly 4 digits are there exactly. As an exception for the 0 we have, as an exception, both decimal and hexadecimal literals which have a value 0 can be converted to any fixed size bytes type. So as you can see, these last 2 lines is for that 0 case. String literals and hex string literals can be implicitly converted to a fixed size byte arrays if their number of characters matches the size of the bytes type. So in this case 2 bytes we will need 4 hexadecimal characters. So it is fine. But for the string we will need 2 string characters because each string character will take up 8 bits. So they have given simple examples which you can read. Now about addresses, as described in address literals, hex literals of the correct size that pass checksum test are of address type. No other literal can be implicitly converted to the address type. This I have explained in detail previously. Also this I have shown you. I told you about this. I had it in my comment when we were talking about conversions. I also covered this conversion there so that the comparison is clear. Like under this address section, I had this comment here where I explained you this is basically that last 2 lines only. So let us now read about this section, expressions and control structures. Here is the URL, and you can also see it is under the language description here, expressions and control structures. So firstly about control structures. Most of the control structures known from curly braces languages are available in Solidity. There is if, else, while, do, for, break, continue, return with the usual semantics known from C or JavaScript. They haven't explained you about these here because it is just like what is present in languages like C or JavaScript, basically in these curly braces languages. So let me quickly go over them. So here I have an example to explain about if-else statements. So this function, which goes by the name if-else, takes an input which I am labeling as input, and now this has the variable declared x here, and if input is less than 3, then the x is assigned the value 1, and here we are returning x also. But if this condition is false, suppose input is greater than or equal to 3, then we will come here and it will check whether if input is less than 5 or not. If input is less than 5, then this statement will get executed, and if this condition was false, it will come here and it will check whether input is less than 6 or not. If this condition is true, this statement will get executed, and if even this condition is false, it will come here, and here I have not put any if thing. This statement will get executed if this condition was false too along with other ones, then this statement will get executed. So let us run this. I'm going to deploy this contract. Now let me run this contract with some values. Suppose I put 2, then as 2 is less than 3, x gets the value 1, and I should get here 1. So let me run this, and yes, I'm getting 1. So let me make it say 3, because 3 is not less than 3. This statement will get executed and I should get x equals to 2 here. So yeah, 2. Now let me put it equals to 5, because 5 is not less than 5, but 5 is less than 6. So this condition is true and we should get this statement. Yeah, I got the value as 3. Now if all of these were false, suppose x is 6, 7, 8, then if I run this, then all these are false. So simply this else statement will get executed, and yeah, I'm getting x 9. So I hope this if else part is clear now. Now let me explain about while loop. Here I have this function underscore while. Inside I am declaring an integer, an unsigned integer I equals to 10, and here I have this while loop. Now what it is going to do, it is going to check this condition before executing this code block of the while loop. It is going to check this condition whether this condition is true or not. Here I am not putting any condition, but I am making it true. So this thing is always true. This while loop, since here it is always true, this code block will keep on getting executed infinitely. Basically what happens, this code block gets executed, then again it will check this condition. Here since this condition is true always, then again this code block will get executed, and so on. This loop will keep on getting executed, but here I am breaking out of this loop like so, because each time this loop we are getting inside this loop, I decrement I by 1, and it checks if I whether I is equal to 0 or not. If I is equal to 0, then I am assigning x something and I am breaking out of this loop, and in the end I am returning x. So let me check the return value. If I deploy this contract and call this while function, I am getting return value is 100, which is indeed what I assigned. Now can you think and tell how many times this while loop is getting executed? Let me do one change here. Let me do this. Make it x plus equals to 10, and let me put this line here. Yeah. So what I am asking you now, think and tell me what this return statement will return. So I hope that you have the correct answer. So I'm going to deploy it and run this, and I'm getting the same 100 value because this part will get executed 10 times. How so? We start with I equals 10, then I'm decrementing I, so I is now 9. This statement is executed, this condition is false, so fine. Then from 9 we get 8, 7, 6, 5, 4, 3, 2, 1, 0. So yeah, all 10 times we executed it, and when it checked that I is equal to 0, we breaked out of this, and x is now 100. It started from 0 since by default the value of x is 0, and now I'm getting 100 here. Lastly, let me make one more change. I greater than equal to say 0, and I'm going to remove this part, and I'm going to decrement I, then plus equals to 10. Now can you tell me what will be the value of x when this whole is executed? I want you to think carefully. Think carefully. Now I'm going to tell you the answer. It won't be 100, but it will be 110 because this part is getting executed 11 times. So let me show that to you too. I'm going to deploy this, and I'm going to run this. I have an error here. That revert is basically because I am making I negative. When I is equal to 0, then I minus minus will make it negative. So let us make it here integer. Now let us run it. So deploy, run this while, and yes, answer is 110. So why is it 110? Because at 10th time when I is equals to 10, this condition is true and we have incremented. This will be hold true till I equals to 1, 2. So 10 times here also. But even when I is equal to 0, this condition is true. I is greater than equal to 0 is true when I itself is 0. So 11th time executed again. So I hope with this, regarding this while part and the break part, I hope it is clear. This break statement can even be inside for loop. So whenever you put breaks inside a loop, it will break from that loop. So I hope it is clear. Now I have this example of do while. So what happens here? First of all, I have this function named do while, then a variable I having the value 10, variable x, by default it has value 0, then this do while statement, and I'm in the end returning x. So what does this do while does? It first of all executes this, then after executing this code block it checks for this condition. If this condition is true, it will then again execute this code block, and so on. Only once this condition is false, then it will move on to the next line. So if you have understood properly, let me first make this like this. I have changed the condition that while I is greater than 10. Can you tell me what this function will return? Think. Now I'm going to run this so that you can see whether what you thought you got that or not. So I'm running this, and yes, we got 10, because even if this condition was false, still this code block got executed, because first this code block will get execute, I will get the value 9, x will become 0 plus 10 is 10, and then it is going to check this. Since this condition is false, it is going to move to the next line. Now I'm going to change it back to what we had, I greater than equal to 0. I'm going to save it. Now can you tell what will be the returned value thing. And now I'm going to run this. So let me deploy, and you can see whether what you thought is correct or not. And we have got 110. So it is just like those while loops. So I hope with this example the do while part is clear. Next, I have this function underscore continue, and from this function I want to showcase this keyword, continue keyword. So this function is returning an integer which is this x. In the end I am returning this x. I start with making I equals 10, which is an unsigned integer. So while I is greater than 0, this is our simple while loop, right? Then I decrement I here, and what I'm doing, if I is less than 5, continue. So what this continue keyword does, first of all you use it inside a loop, and when you have this continue, what it is going to do, instead of going any further down in the loop, it is going to go back again to the top. So as soon as it encounters this continue keyword, it is going to jump back here, going to check the condition. If it is true, execute this code block, else go up. Initially I will not be less than 5, so this continue keyword will not get played, and x plus equal to 10 will happen, and so on. This loop will continue. So if you have understood properly, can you tell me what will be the returned value of x in this function? So I'm going to deploy this now. I hope you have thought now about it. Now I'm going to deploy it and run this continue function. And yes, we have got value 50 because it starts with I equals to 10. This condition is not to x get incremented by 10, so x is now 10. Then with I equals to 9, since this condition is true, it is going to go on. This condition is false, but this since this condition is false, we go to the next line, increment x by 10. Like for the 10th case, x got incremented by 10, then I is equals to 9, I equals to 8, I equal to 7, and I equal to 6. So when I was equal to 6, this statement also got executed. Now I is 5, then since I is minus minus, I becomes 4, and since 4 is less than 5, continue, we go back to the up. So I hope how we got x equals to 50 is clear, and with this I have explained the continue keyword. So we have now looked at all of these statements: if, else, while, do, for we saw previously, break, continue, return we have seen multiple times. So this part is done. Solidity also supports exception handling in the form of try-catch statements, but only for external functions calls and contract creation calls. Error can be created using the reverse statement. This section we will see in detail later, so currently there is no point going in depth over it. Also, parentheses cannot be omitted for conditionals, but curly braces can be omitted around single statement body. Basically, in like here, they are saying this parenthesis, I cannot write if input less than 3. I must put these parentheses. This is what they are saying. Along with that, they are saying that in case your curly braces contain only a single statement. As you know, I might have not mentioned it, but for the statements, whenever we write a statement, we use this semicolon, right, in the end. So that is how multiple statements are separated from each other. In case I had x equals to 3, then int y equals to 88, so on. So that means I am having multiple statements. Now in our example, each of these lines had a single statement. So in that case, what they are saying, that curly braces can be omitted around them. So if I omit this curly braces and save, yes, I am able to save. So in case of single statements, the curly braces can be omitted. Moving on, Note that there is no type conversion from non-boolean to boolean types as there is in C and JavaScript. Yeah, they have given the example also, this if one curly braces. Basically, in most of the languages, like if I were to do this if one and something, then usually those languages will treat one as true and zero as false. So many times you will see statements like this while I, since suppose I is starting from 10, then inside they might do this I minus minus. So as long as I was greater than 0, the while loop was getting executed, but as soon as I became equal to 0, then 0 will be treated as false in those languages, but that is not the case in Solidity. In Solidity, this parenthesis part must contain a boolean. Yeah, so now let us look at function calls. So they have internal function calls. Functions of the current contract can be called directly, that is internally. Externally will means that you send a those transaction message which we saw, that payload type thing where the new context gets generated. So you need not do that. If you call the function internally, they will be executed by a simple jump statements. And what they're saying, they can also be executed recursively as seen in this nonsensical example. So they have a function g which takes an unsigned integer a, and what it does is it returns a plus what f returns. But what f is doing, f in turn is calling g of 7 and then itself. So their recursion is having here in this example, this recursion I think will keep on going infinitely because there is no base case. Like a base case could be that if a, I mean they are not even decrementing anything here. So I mean it's a poor example of recursion. Let me then show you a good example for recursion. Also, I will take this opportunity. I have told you previously that I will show you an example of recursion and how you can in some cases replace that recursion with the iterable loop. So I will take this opportunity to tell that also. So here I have this factorial function which will compute the factorial of a given input. If you don't know what is this factorial means, kindly Google it. It's just a very simple sequence. Basically it does this only, that if the number is 0, return 1, else you multiply your given number with the n minus 1 factorial. So if I were to tell you 0 factorial, you use exclamation symbol for factorial is equals to 1, and if n is greater than equals to 1, then n factorial is equals to n times n minus 1 factorial. So I hope with this factorial example is clear to you, and this is what this function is does. So if I call factorial of 0, I should get the output 1. If I check here, decoded output they are saying as 1, and if I do factorial of 3, then 3 factorial will be 3 into 2 factorial, which would be 2 into 1 factorial, and 1 factorial is 1. So 3 into 2 into 1, which is 6. So if I do this and see the output, the answer is indeed 6. So yeah, I showed you the example using recursion. Now here I have implemented this factorial function using a for loop. So again the number of the whose factorial we want to find. If that number is 0, return 1, else I have this variable result to which I am going to multiply n and decrement it 1 at a time, and do this as long as n is greater than equal to 1, and in the end return result. So basically we are doing this stuff only here. So let's run this and see. So 4 factorial 3 should be 6, 0 should be 1, and yes, it is working as expected. So with this I hope recursion as such is cleared. Continuing, these function calls, the internal function calls, are translated into simple jumps inside the EVM. These has the effect that the current memory is not cleared. That is, passing memory references to internally called functions is very efficient. Only functions of the same contract instance can be called internally. I hope that this is clear to you because we have discussed about this many times. So basically, as you saw, if I do an external function call, then I'm calling some another contracts function. First I do a transaction where the data will contain the data will contain the payload of which will be the serve as the input of that other function. And when calling that another function, a new EVM context will get generated. So a new memory stack, etc. And that memory's lifetime is limited to the lifetime of the called function. Once that called function is over, memory is cleared, right? Now, in case I have my own contract, inside my own contract, suppose a function A is calling a function B internally, then I am within the same context, right? I need not do a new transaction and passing, because as such the data is always, you can say, copied when doing the external function call. Whenever I pass my any reference to an external function call, I cannot pass a reference to an external function call. I have to pass the entity by value whenever I'm doing external function call. But only when I'm doing an internal function call, a function A is calling function B internally, in that case I can pass reference. And since I am passing reference, I'm not doing a copy operation. That is why this is very efficient. If you are calling the function internally and passing memory references, and you can even pass the storage reference. Yeah, that is possible only for the internal function calls. External function calls, you cannot do that. And they are saying you should still avoid excessive recursion, because we have discussed this in great length, because as every internal function call uses up at least one stack slot, and there are only 1024 slots available. Next we have external function calls. Functions can also be called externally using the this dot, the function name notation. I have explained this also. And c.g notation, where c is the contract. We have seen that. And g is the function belonging to that contract. Calling the function g via either way results in it being called externally using a message call and not directly via jumps. We have seen that. Please note that function calls on this cannot be used in the constructor as the actual contract has not yet been created. When we are creating the code, we will talk about constructor. The constructor will act like an initialization. The constructor will set up the other variables, etc. to for our contract, and that is why we have, as I have told before, the initial bytecode and the deployed bytecode. Deployed bytecode is when the constructor has finished running. Functions of other contracts have to be called externally. Yeah. For an external call, all function arguments have to be copied to memory. We saw that in that EVM illustrated diagram. This diagram, here you can see for the external function calls, arguments and return values are passed using memory. So, yeah. A function call from one contract to another does not create its own transaction. It is a message call as part of the overall transaction. So when I am interacting, suppose I do a transaction, then inside a function is suppose calling some another contracts function, then a message call happen. You can think of it as a micro transaction. This contract function will calling some another contract. I have also used the transaction keyword, but that was in the sense like a message call. Even the high level transaction was a message call as such. Okay, let me show it with the help of the diagram. Firstly, I would like to take an example here. There is this app known as Firebird Finance. So in case if I want to swap one Bitcoin for the DAI stablecoin, this app will try to give me the maximum value, maximum DAIs for my Bitcoin. So what this app will do, this is the route it is planning to take. If I click on swap, it is going to do these many routes. So as such, individually I can swap USDC to DAI. That will be an individual transaction. But when I'm swapping via this app, it is going to swap 5% of my Bitcoin to USDT, then those USDT to USDC. All of this is going to happen via message calls. There will not be an individual transactions in themselves, but be part of this overall transaction. So all of these are happening inside. Basically, some function will be invoked in some contract which is going to swap WETH to USDC, and then so on. All these subcalls will happen as a part of one overall transaction to get me my DAIs for a given Bitcoin. If I were to now show diagrammatically, here suppose we invoke this function f of contract A. Just like how we do in Remix, right? Now this function f is calling function g. So b.g, it is calling this function. Now this is a message call. After the function g has finished executing, the control will reach back to the function f, and so on. The function f will get over. So this whole thing which the function f did to the function g via message call and then returned will be part of one single transaction. Even though we had multiple message calls in between, this function g might have some another message call and so on. We will do one example in damnvulnerabledefi CTF, capture the flag, where we will see that how we are trying to attack a contract and get funds in a single transaction, not multiple. So at that point, I hope it will become clear to you, if not now. Moving on, when calling functions of other contracts, you can specify the amount of V or gas sent, which you are going to forward to that called function, with special options like you can give the ether, the value which you are sending, the V. Here this will be 10 V, and 1 ether is 10 to the power 18 V. Note that it is discouraged to specify gas values explicitly, since the gas cost for opcode can change in future. You might specify this gas explicitly, thinking that my addition and all the opcodes are taking this particular gas, but those gas costs for a particular operator can change in future. So that is why they are discouraging this practice. And in case you don't specify the gas, then by default it will forward 63 by 64th of the available gas. So that is the rule. Any V you send to the contract is added to the total balance of that contract. Here they have an example where they have this contract named info feed having the function info and just returns this unsigned integer 42. Then I am having a variable feed of this contract type. Then this has set feed function where basically this feed gets assigned the value. So we might have some contract already instantiated and we are passing it in this function so that this variable can get updated. Then call feed, so basically they are calling this function with some value and gas, and actual call is happening because of these this parenthesis. Also we could pass value because this was payable. Payable will signify that the function can accept ethers, these units. So you need to use the modifier payable with the info function because otherwise the value option will not be available. Fine. Be careful that fee.info, what they have done, only locally sets the value and amount of gas sent with the function call, and the parenthesis at the end perform the actual call. Just like actual call we do usually, the calls, all the calls we do, we use these parentheses. So don't forget to put these parentheses. If you just write this, you're not actually calling it. You're just locally setting it for the time being. So this thing alone does not call the function, and the value and gas settings are lost. Only this thing perform the actual function call. Moving on, due to the fact that the EVM considers a call to a non-existing contract to always succeed, Solidity uses the ext code size opcode to check that the contract that is about to be called actually exists, basically whether it contains code or not, and causes an exception if it does not. So it will check whether the code size is greater than 0 or not. This check is skipped if the return data will be decoded because data decoded after the call, because ABI decoder will catch the case of a non-existing contract. So nothing much to understand. They have given a technical detail. Note that this check is not performed in case of low-level calls which operate on address rather than contract instances. So if you do that .call, .delegate call or .static call, etc. Call static call mainly, then you see that this ext code size check is not performed on them. But if you were to call a function from the contract instance, like I have showed you very previously, in that case this check is performed. Be careful when using high-level calls to pre-compiled contracts. We have not discussed pre-compiled contracts, so let's discuss them now. Pre-compiled contracts, which is in this section, Introduction to Smart Contracts. There is a small set of contract addresses that are special. Their address range between 1 to 8, which is included, including 8, contains pre-compiled contracts that can be called as any other contract, but their behavior and their gas consumption is not defined by the EVM code stored at that address. They do not contain code, but instead is implemented in the EVM execution environment itself. By the way, this address 1 to 8, they will be of this form. I hope that is clear. Different EVM compatible chains might use a different set of pre-compiled contracts. Ethereum is using these. Different chains might use different. It might also be possible that new pre-compiled contracts are added to the Ethereum main chain in the future, but you can reasonably expect them to always be in their range, in the given range 1 to 0x this 4 times f. So going back, since pre-compiled code does not contain any code, so let us read also. Since the compiler considers them non-existing according to the above logic, because their ext code size will be 0, even though they execute code and can return data. So be careful. Function calls also cause exception if the called contract itself throws an exception or goes out of gas. This is something very basic. We will also cover exceptions in great detail later. Now they have given a bit detail about reentrancy exploit. We will see reentrancy in detail, so we need not bother about this warning as of now. Moving on, named calls and anonymous function parameters. So function call arguments can be given by name in any order if they are enclosed in the curly braces, as can be seen in the following examples. So if we look at the example, we have a mapping named data, then this function f is calling the function set internally, and since this function accepts two parameters, an unsigned integer named key and an unsigned integer named value, so either you can call it like this: name of the function, then the first parameter key and the second parameter value. So you can put whatever unsigned integer here as the key and whatever unsigned integer here as value. So that is how the method which we have seen usually to call a function. Or you can give them by name, like here value they have given 2, key they have given 3, but then use these curly braces, and whatever you write here, the named parameters can be in arbitrary order. So the argument list has to coincide by name with the list of parameters from the function declaration, but can be in arbitrary order. So we have now seen that. Omitted function parameter names. The names of unused parameter, especially return parameters, can be omitted. Those parameters will still be present on the stack, but they are inaccessible. For example, here they have this function which goes by the name func. Now this variable, they are not declaring its name, so we cannot access it within our function, but although memory for it will be allocated as this variable is present on stack. Next, we have creating contracts via new. A contract can create other contracts using the new keyword. The full code of the contract being created has to be known when the creating contract is compiled, so recursive creation dependencies are not possible. So let us try to understand this with the example that they have provided. So they have provided a simple example. We have a contract D, and this contract in as such is not creating a new contract C variable. Basically, it's not instantiating the contract C. However, the contract C is instantiating a contract D. So we see that there is no recursion dependency. Recursion dependency would have occurred if in contract D we were doing new C, something like that. So just like how they are creating a D contract here. Since this contract has a constructor, we will see in constructor in detail later. So, and this constructor is taking as an input an unsigned integer. So whenever I am instantiating, creating a new contract D, I have to give in an unsigned integer value so that the constructor part is successfully executed. So they have this state variable D of contract type D having whatever they have given as input for the constructor part. Next, they have this function to create a new contract D. So they create a new contract D like that, and they are also calling this function x, which is the getter function for the public variable. We have seen getter functions in great detail. Then create and endo D. So basically, they are creating the new contract of type D, but with the value. So endo part here, basically they are also sending value to it. So the constructor should be payable. Yes, constructor is having the keyword payable, so we can send ether to it also. By default we are sending 0 for these cases. So as seen in the example, it is possible to send ether while creating an instance of D using the value option, but it is not possible to limit the amount of gas which you are for that contract. If the creation fails due to out of stack, not enough balance, or other problems, an exception is thrown. Moving on, we have this section, salted contract creations, also said to be create to. It's a simple section, so let's finish it. When creating a contract, the address of the contract is computed from the address of the creating contract and a counter that is increased with each contract creation. This counter is also said to be nonce. It is present even when you are doing your normal transactions. Suppose if you have used MetaMask, then when doing the transaction, MetaMask will show you that transaction number this confirmed. So this number is something which is not just created by MetaMask. It's not a MetaMask unique thing, but as such it exists besides it. It is called as nonce. If I show you in the Ethereum yellow paper, here we have its description, the description of the nonce. So a scalar value equal to the number of transactions sent from this address, it starts from 0, or in the case of accounts associated with code, as we have seen two types of account, EOA, external accounts, and the contract accounts. For the case of contract accounts, the number of contract creations made by this account. Alright, so we have this. If you specify the option salt, which should be a byte steady to value, then contract creation will use a different mechanism to come up with the address of a new contract. It will compute the address from the address of the creating contract, the given salt value, the creation bytecode of the created contract, and the constructor arguments. So, in particular, the counter, also said to be nonce, is not used. This allows for more flexibility in creating contracts. You are able to derive the address of the new contract even before it is created. Furthermore, you can rely on this address also in case the creating contract creates other contracts in the meantime. Because if the other contracts are creating, the nonce will get increased. So, if we are using this method, we already know the contract of the contract about to be created. So you can hard code it. The main use here is contracts that act as judges for off-chain interactions, which only need to be created if there is a dispute. So if they are created, we can already give them address, so that uh, I mean, even before we deploy them, we already have their address, which can be used as judges in case there is a dispute. So in case an entity needs to query a judge, it already has the address of it. Also note that we are using the creation bytecode of the created contract, not its deployed bytecode, or you can say it to be running bytecode, some people call it. They have this example. Let us go through this. We have this contract. A very simple contract contains a public variable which is initialized by the argument given in the constructor. So we have this function create d salted, which takes the salt and the argument for the initialization of this contract d. Now they are just showing that how this address, the salted address, is computed. So they have there this wizardry. We need not bother about this, but what you can look at, that the address of the creator, the salt, the creation code of the contract to be created, and the argument, just like what they told here. Address of the creating contract, address, the given salt value, the creation bytecode of the created contract, and the constructor arguments. If you want to know in detail about why this bytes 1, 0xff, and so on, but let me first tell you that there they have this salt given, and they have verified that yes, their predicted address is indeed same as this computed address for the contract they have deployed. And now if you want to know about all these things, you can read this EIP 1014, and also you may also read about this create to opcode. I see it to be beyond the scope of this course. So with that's done. And regarding warning, they have that there are some peculiarities in relation to salted creation. A contract can be recreated at the same address after having been destroyed, yet it is possible for that newly created contract to have different deployed bytecode even though the creation bytecode has been the same. And the reason for that is very simple. They have something here also, which is a requirement, because otherwise the address will change. I mean, here we are taking the creation bytecode, not the deployed bytecode. So it's good that we took creation bytecode, as the deployed bytecode might change. This is due to the fact that the constructor can query external state that might have changed between two creations and incorporate that into newly deployed bytecode for its before it is stored. Here, like suppose this constructor, here we are just putting in this argument, but this could be, I mean, this variable x could be initialized from some oracle, and different things are possible. Like this could be an immutable variable. We will see what is immutable later. But I hope the idea is clear. So with that, this section is over. Next section of interest is this one, assignment, destructuring assignments and returning multiple values. This in itself is clear by the example which they have provided. They have this contract C which has the unsigned integer variable named index, a function f which returns a tuple. Tuple is having what it is being returned is the tuple of unsigned integer, a boolean, and again an unsigned integer. Then they have this function g, variables declared with type and assigned from the return tuple. Not all elements have to be specified, but the number must match. Here, this function, as we saw, is returning this tuple. Out of them, they have only taken up x and y. This they have not given the name, so it won't be possible to access it also now later. This is a like a shorthand. If you don't intend to use that returned variable, you can as well omit it. Here they are showing a common trick to swap two elements, which does not work for storage reference types. So for storage reference types, don't do this. So here x is getting the value of y and y is getting this value x. Later again they have this same sort of an example just like this, that they are omitting these two, and index which existed previously is now getting the value, the first value returned by this function, which was a 7. So let us also read this. Solidity internally allows tuple types, that is a list of objects of potentially different types whose number is constant at compile time. Here it was 3. Those tuples can be used to return multiple values at the same time. These can either be then assigned to newly declared variables or to pre-existing variables or L values in general. This L values thing, if you have written a compiler in past, then you might understand, else you can ignore it. Tuples are not proper types in Solidity. They can only be used to form syntactic groupings of expressions. So here to the new created variable it was assigned, and here to the pre-existing variable this it was assigned. It is not possible to mix variable declarations and non-declaration assignments. That is, the following is not valid here, since the variable declaration is mixed with the non-declaration one. So that is why they are saying that it is not valid. This note is not of our interest. Then we have this warning. Be careful when assigning to multiple variables at the same time when reference types are involved, because it could lead to unexpected copying behavior. We have seen this for reference type. It could either be value to be copied or it could be a reference only. So be careful in that case. With that, this section is also over. Moving on to the next section under assignments. The next section is this, complication for arrays and structs. There is nothing to be learned here. We have already seen all that. Basically here, this function, when it is calling g of x, this g, the x is in storage, but here it is memory, so a copy operation will occur as the data location has changed. When this y is modified, the x does not get modified. Whereas here, also notice that it is an internal function, and only in internal functions we can pass a storage reference. Since this is in storage and we are passing to the storage, and here when we change y, the actual change in x is also happening. We have seen this before. So the semantics of assignments are more complicated for non-value types like arrays and structs, including bytes and strings, and they are saying to read the section which we have already covered. In the example below, call to g of x has no effect on x, as we have seen, because it creates an independent copy of the storage value in memory. However, h of x successfully modifies x because only a reference and not a copy is passed. So with that, this assignment section is now complete. Next, we have scoping and declarations. I would just like to say one thing in case I haven't mentioned it before. We have something known as state variables, right? And every variable besides state, you can think of it as a local variable. I mean, it is local to that part of where it is declared. And this scoping thing, I think, will make it further clarified. So a variable which is declared will have an initial default value whose byte representation is all 0. This thing I have already covered, but in case you want to read, the default values of variables are the typical 0 state of whatever the type is. For example, the default value for a bool is false. The default value for the unsigned integer or int types is 0. For statically sized array and bytes 1 to bytes 32, each individual element will be initialized to the default value corresponding to its type. For dynamically sized arrays, bytes and strings, the default value is an empty array or string. For the enum type, the default value is its first member, whose value is also 0, as we saw. Now, to understand scoping, I have made a very simple example here. So this contract scoping has just one function scope, and inside this function I am now declaring this unsigned integer x equals 8. It's not a state variable, it's a local variable local to this curly brackets. So this curly bracket starts the starting one and this ending one. So its lifespan is only till this place. Now I have declared a code block. Inside this code block, I am declaring one more x. Say here x equals to 7. Now what this does, now inside this code block, after the declaration of this variable, what all modifications I will do to x will happen to this x, right? So here, if I were to do x equals to 25, then it is going to modify this x, right? This will become clear with what I have done next. Inside this code block, I am changing my x. X is equals to 3. What x will get modified is this x. When I am doing here x equals to 3, this x will get modified, not this x, because this x declaration has shadowed this word, shadowed the previous declaration. I hope it is starting to make sense. Now I have modified this latest declaration value. Now inside this code block, I am declaring another x having the value 88. Now if I do this assertion to check whether is x my now 88, so that to make myself clear that this x is referring to the latest, the most nested scoping thing which is available to this code block, which is this one. So yes, this indeed will get passed. Now when I do this modification x equals to 5, can you think and tell what which x will get modified, this x or this x? Since this x has shadowed this x as it is the most nested one, when I'm doing this modification, this one will get modified. So yeah, this one will get modified. Now when this code block ends, the lifespan of the variables declared inside this code span, this code block, which were local to this code block, they have now, their lifespan is completed, they are now dead. So this x which was declared was alive only till the end of this part where it is no longer alive. So all this we did is now gone, and this x equals to 3 will indeed maintain that x equals to 3. If I had done something like this, x equal to 7, then this x would have gotten modified, right? Let's make it 71. And if I check here, then you can check, I mean, we will run and see, then that this x will get modified. I mean, this one, not this one actually, this one, yeah. This one would have gotten modified. And when I am declaring another x here, then the previous ones got shadowed. So, yeah. Let me remove this assert thing here, because this modification of this variable x I have already done here. So let's not further complicate the example. Yeah. So since this x is now this x declaration, I modified it to 3. So after this code block, I am checking whether x is indeed 3, then it is indeed will be true. Now this code block has ended, and I didn't declare anything inside this code block. I just created a useless nesting here. Now I am checking whether my x is 3 or not. And it should be 3, because even though you might think x is declared here 7, but I have modified it here. I changed this value to 3. So this one indeed should be 3. Now this code block is end, and whatever the variables which was declared here, for instance this x variable, their life is now complete. And we are back to our this x, and it was not modified inside. So checking whether x is equals to 8 or not. So let me save it. And now I'm going to deploy it. And I'm going to call this function. If it passes, I do not get any exception, then it means our logic is correct. So I'm running this, and it has passed successfully. So I hope with this scoping is clear to you. Moving on to what documentation has to say. Scoping in Solidity follows the widespread scoping rules of C99 and many other languages. Variables are visible from the point right after their declaration until the end of the smallest, this curly braces code block that contains the declaration. As an exception to this rule, variables declared in the initialization part of a for loop are only visible until the end of the for loop. When we did the for loop, inside the for loop, I did this declaration uint I equals to 0. Okay, let me show that to you. Like this for loop, here I have declared this new variable unsigned integer I. So this I is alive inside this code block. I won't be alive here. So I hope this about I is clear, even though I have not declared it inside this code block, but it is alive here as it is declared here. I mean, this is how for loop works. I can also access high inside this parenthesis. So I hope this part is clear. Variables that are parameter like function parameters, modifier parameters, catch parameters. These modifier parameters and catch parameters we will see later, but the function parameters you have seen many times. Whenever we declare a function or when we call the function, the parameters which are inside those declaration part, inside those curly, inside those parentheses, that is what is being talked about here, are visible inside the code block that follows, just like the for loop. The body of the function modifier, the body of the function or modifier for a function and modifier parameter, and the catch block for a catch parameter. They have just explained that. Moving on, variables and other items declared outside of a code block, for example functions, contracts, user defined type, etc., are visible even before they were declared. This means you can use state variables even before they are declared and call functions recursively. Now the language might not be that clear, but if you understand it, then it will seem easy. So what they are saying, that here I have not declared y as of now. Before the declaration of this function, I have not declared y. I have declared y here, this uint y, but even then I am able to access y here. This is true for all the variables which we have written outside these further code blocks, like this code block, this code block. So whatever we have written inside this code block, but outside any further code blocks, for them you can do this. Even the things which were written outside this code block we can access, just like structs which we saw, etc. So for the state variables, even when we did recursive functions, that was possible because they were available to us even before they were declared. Like this play function, this play y function could call suppose scope function here, even though I haven't declared scope function before this. So for, I hope that you have cleared, but this thing can be supported only for those things which were outside this code block, basically outside any further nested code blocks. So I hope with this it's clear. Let me run this function and check. I have this y equals to 5 assigned here. When declared y was 0, and I'm checking y, whether y is indeed 5 or not. So let me save this. Now I'm going to deploy this. In this deployed function, let me first call play_y to modify the value of y, which has run successfully. And now I'm going to call check_y to check whether the y got updated or not to 5. And yes, it has also run successfully. I did not get any revert or exception. But if I were to try something similar inside a nested code block here, you can see I'm not able to do it. I cannot access z before it got declared. So I hope this is clear. Further part is of no interest to you. All these things we have covered. So it's not relevant to us. Moving on, we have this section, checked or unchecked arithmetic. This also we have done in detail when we were discussing types. So we can move past this section. We have this message here. Explicit type conversions will always truncate and never cause a failing assertion, with the exception of a conversion from an integer to an enum type. So in that case, an exception will be raised. Enum is, as we know, uint8, but yeah, its range could be even further limited than uint8. Suppose an enum contains only 4 values. So in that case, the range is from 0 to 3. So for other cases, you could do explicit type conversions, but Solidity is not allowing you from an integer to an enum type in case you are out of the range. But in case you are inside the range, then it will work. For example, if your enum contains say 4 element and you are converting an integer whose value is say 3 to that enum type, then it will work fine. But if that integer value is say 5, anything above the range, then it will give you the failing assertion. Next, we have a very important section, error handling, assert, require, revert, and exceptions. So let us cover them all now. Solidity uses state reverting exceptions to handle errors. Such an exception undoes all changes made to the state in the current call and all its subcalls and flags an error to the caller. So in case an exception is encountered, all the changes which were done get reverted, and we are like to that point as such that the transaction didn't happen. We did not make that transaction. As I showed you previously, the transaction is an atomic operation. Either you do it or you don't do it. But of course, as such, it is possible to have some states modified even in case of an exception if you are using something like try catch. We will see that and then it will become very clear. When exceptions happen in subcall, they bubble up. Expressions are returned automatically unless they are caught in a try catch statement. Exceptions to this rule are sent and low level functions call, dedicated call, static call, because they don't raise an exception, they just return you a boolean value to denote the success. They return false as their first return value in case of an exception instead of bubbling up. So let me first diagrammatically show you. Like suppose I have a function f and this function calls a function g, which in turn calls a function h. All of these are message calls, so basically external calls that I'm referring to here. So this function h may encounter an error. Then what will happen? All the changes which were done to the state inside this function will get reverted. And now the call is transferred back to the function g, where the g will see that an exception was raised and this exception will bubble up unless I'm trying to catch it. there is this syntax of try catch which we will see. So in case I'm not using anything like try catch, then it will bubble up and G will again bubble up the exception and the whole transaction will get reverted. In case G does try to do something like try catch, then it can possibly handle the exception in its own way and a state changes could have happened, not of H, but G itself could do some state changes and F might have also done some state changes. So those state changes will remain in case G were to handle the exception. If G does not handle the exception, then as it will get bubble up, all the changes to the state which were done by G will also get reverted. And here, if F tries to catch the exception, fine. If it doesn't tries to catch that exception, all the changes which were done to the state by F will also get reverted. And we will see the exception, just like how we see that in Remix. So I hope with diagram it is clear. Next, they have this slight warning that the low level functions is call, delegate call, static call return true as their first return value if the account called is non-existent as part of the design of the EVM. So you can try to if you want to see whether the account exists or not, you can then check that before doing this stuff. So account existence must be checked prior to calling if needed. Now exceptions can contain error data that is passed back to the caller in the form of error instances. The built-in error, which is this error having string and panic having this unsigned integer of 256 bits, are used by special functions as explained below. Error is used for regular error conditions, while panic is used for errors that should not be present in bug-free code. So this part should be read very carefully as it is the essence of panic and error, which is that error is used for regular error conditions. When we will be using them, then it will become very clear. But for now, I want you to have this line very much embedded inside your brain, that error is used for regular error conditions, while panic is used for errors that should not be present in bug-free code. Suppose somebody gives you an input and you don't like that input. You say that I don't want to work from that input. Then you will raise an error. But in case something unexpected happened which you didn't account for in your code, say division by 0, in that case panic will happen. So panic is raised via assert and error is raised via require. We will see an example here itself, then it will become clear. The convenience functions assert and require can be used to check for conditions and throw an exception if the condition is not met, like I showed you, right, when we were using assert. The assert functions creates an error of the type this panic thing. The same error is created by the compiler in certain situations as listed below. Assert should only be used to test for internal errors, like how we were using, right, when we were checking about different variables, and to check invariants. Invariants is basically the thing, the property which should remain, which should not get changed. So we will also study Unidex, the Uniswap model. In that we will see some invariants. So I think that at that point it will become clear. Properly functioning code should never create a panic, not even on invalid external input. If this happens, then there is a bug in your contract which you should fix. Language analysis tools can evaluate your contract to identify the conditions, basically these this side the corner cases, the conditions and function calls which will cause a panic. A panic exception is generated in the following situations by the compiler. The error code supplied with the error data indicates the kind of panic, right? So 0x0, whenever the panic is returned, as you know, it returns an integer with it. So you can query that integer to see what is the actual cause. So 00 is used for general compiler inserted panics. This is just for your reference. Need not to have this in your head, but just for reference. but better to go through it at least once. If you call assert with an argument that evaluates to false, we saw that. If an arithmetic operation results in an underflow or an overflow, as we have seen, outside of course, the unchecked environment, that is in checked environment. If you divide or modulo by 0, if you convert a value that is too big or negative into an enum type, if you access a storage byte array that is incorrectly encoded, if you call pop on an empty array, if you access an array bytes and or array slice outside of its range, or if the index is negative, yeah, that falls, I mean that is outside only, or if you allocate too much memory or create an array that is too large than its size, if you call a zero initialized variable of internal function type. This function type we haven't covered yet, but when you see the function type, then this will become obvious. The require function, on the other hand, creates an error. I mean, the require comes in two form. If you just use the require keyword, we will see examples, then it will become clear, but for now have the reading also. The require function either creates an error without any data or an error of the type error string. It depends whether you give a string to this require or not. If you don't give a string, then the error without any data. If you give a string, then this type error string. It should be used to ensure valid conditions that cannot be detected until execution time. So in case a function wants an integer which should have value less than 5, then you can use this require thing. We will see an example that then it will become clear. This includes condition on inputs or return values from calls to external contracts. We will also be covering like the damn vulnerable DeFi problems. In that also you will see multiple times this require statement. It is currently not possible to use custom error in combination with require. Please use this revert statement. We will see revert later. So require is else something else, and this revert thing is something different, although both are used for like quite similar purposes. We will cover all them, just like this, all this will be covered, this revert also. Yeah, so okay, now I thought of showing you an example before we progress. Here I have declared the function underscore require, which takes an input unsigned integer and it checks whether that value is less than 5, and this is for the and, greater than 0. In case this condition turns out to be false, then I am showing this message input must be positive and less than 5. So let us check this. I'm going to deploy this smart contract and I'm going to call this underscore require function with say 0. 0 as we know is not positive. So I must get the exception. Now as you can see, the exception has been raised and the reason is provided by the contract that input must be positive and less than 5. In case I were to comment this out and have only this line, then if I were to deploy and run this function, say with 0 again, even though the exception is raised, but I am not getting the reason. Here I also provided the reason in the second line. So I hope with this the two forms are clear to you. Also, if I were to show you a very simple example of try catch, we will formally see the syntax later also and all the related ideas with try catch, but as a simple example so that we can relate to when we will be discussing it in more detail, is this function c require. It is basically going to call this underscore require function externally, as we can only do this try catch stuff for the external calls, and I'm going to call this function with 0 unsigned integer, and since I know the exception will be raised, I am catching that exception here, and what this function is doing, it is returning that reason. So an exception won't get raised now because I have catched that exception. Instead of in the catch statement also I can return an exception. So instead of returning an exception here, I am returning this string. I could have as well raised an exception in catch if I wanted, but I'm not doing this bubbling up. I'm catching this and returning that string. If in case there was this after this catch block, if it did not got executed this catch block, then I am returning this no error. Fine. So if I were to deploy it and call this cRequire function, maybe I should also give the argument here, and let's make it like this so that we can also see this no error stuff. So let's deploy it, and now let me call this cRequire with 0 first, so that I should get not an exception but this string that input must be positive and less than 5. So yeah, the input must be positive and less than 5. Now if I were to do say with 3, which falls inside the range, then I should get this no error. Yeah, no error. So I even when I did with 0, as such there was no error because the call went through successfully as I caught it. So I hope with this with these examples, the require part and try catch part, you have some clarity. So let's continue and read about it. An error string exception or an exception without data in case we were not not providing any string is generated by the compiler in the following situations: calling require x where x evaluates to false, if you use revert or revert description. So even though we haven't encountered revert, yes, but revert as such is not taking any condition, and if you just revert, then it is just going to revert to the caller, or revert description will just return this error string, just like how the require part returns the string. If you perform an external function call targeting a contract that contains no code, if your contract receives ether via a public function without payable modifier, including the constructor and the fallback function, as I have told you that in case you want to send an ether to a function, then the payable modifier must be used. We will see that formally also later. If your contract receives ether via a public getter function, so they have shown these examples. Just a second. Oh. Yeah, for the following cases, the error data from the external call, if provided, is forwarded. This means that it can either cause an error or a panic or whatever else was given. So let us see that. If a dot transfer fails, if you call a function via a message call but it does not finish properly, that is it runs out of gas, has no matching function, or throws an exception itself, except when a low level operation call send delegate call code and static call is used. We have seen this multiple times by now. They return a boolean. The low level operations never throw exceptions but indicate failures by returning false. If you create a contract using the new keyword but the contract creation does not finish properly, you can optionally provide a message string for require but not for assert. Yeah, this is clear in itself. If you do not provide a string argument to require, it will return with an empty error data, not even including the error selector. So not even having this error selector here. So they have a simple example. Let's also see that. So send half. So whatever it receives, it is going to send half of it, but it checks whether the number you are getting is even or not. So in case it is not even, it is going to revert. Exception will be raised with this string. So the number is even. If we have reached this line, that means the number is even. Then you transfer it, and now and as you know, transfer is different from send. If transfer fails, then an exception is raised. So in case we are here, that means the transfer went successfully. So this assertion is just for internal checking that whether yes address the balance of your address is now exactly half balance before minus message value by 2, and then this it is returning the balance of your address. So yeah, so I hope this example, which shows both require and assert, have given further clarity. In case of an exception, the internally Solidity performs a revert operation which is having this instruction. This causes the EVM to revert all changes made to the state. The reason for reverting is that there is no safe way to continue execution because an expected effect did not occur. Because we want to keep the atomicity of transactions, as I have explained before, the safest action is to revert all changes and make the whole transaction, or at least the call in case you were doing some try catch stuff, without effect. In both cases, the caller can react on such failures using try catch, but the changes in the callee will always be reverted. I think this is now very clear. Moving on, we have this revert statement. A direct revert can be triggered using this statement and the revert function. The revert statement takes a custom error as direct argument without parenthesis, like this. For backwards compatibility reasons, there is also the revert function which uses parenthesis and accepts a string like this. The error data will be passed back to the caller and can be caught there. Using revert causes revert without any error data, while revert description will create an error string data, just like our require. Using a custom error instance will usually be much cheaper than a string description because you can use the name of the error to describe it, which is encoded in only 4 bytes. A longer description can be supplied via natspec comment, which does not incur any costs. Let me explain it with the help of an example. Here I am having my custom error which goes by the name invalid character. The idea is I have a set of allowed symbols which my contract is initializing when you are deploying the contract. For instance, if I deploy the contract with these 3 allowed symbols, O, X and this subtract symbol, now I'm going to deploy it, and these 3 are my allowed symbols now to this string. Now I'm asking the player to enter his or her move, which first of all has to be a single character long. Input must be a single character, and the move of course must exist in this allowed symbols. So this is just a simple logic to check whether the move which the user has entered actually exists in my allowed symbol or not. Initially this bool variable is made false, and if a match is encountered for that symbol in the allowed symbols, then this what I have selected will return true, and in that case this false or true will become true. So it will remain true, and even a slight optimization, although this code can be optimized a lot further, but a good place to see the break use also. If exists ever become true, then we can simply break out of this for loop. We need not continue further because we wanted to simply check whether it exists or not. Once it becomes true, we need not look at for the other symbols. So if no match was found, then exist will be false, and exclamation of false basically means negation will become true. And then I'm doing this invalid character error where I'm saying that the user entered this character whereas the allowed symbols were these, and here I'm not passing any string, but I have included it as a natspec comment. We will see natspec comments in detail later, but basically just like how spdx is this comment which we write is a special comment, not like our other usual comments. Similarly, when we use these 3 forward slashes then those we use to give the natspec comments. Here this one is showing the basic description about what it is, that is invalid character, only allowed symbols allowed but sent input character, and then these param tags I have one for each parameter. So the parameters, if you want to specify them, you use this @param symbol. We will see all this later. So for this input character, I have told that it is the send character, and for this allowed symbols, I have told that it is the set of allowed symbols. Now we will run this code and then all this will become very clear. So let us deploy it with the allowed characters to be 0x minus. So I'm deployed it. Now let us see. First of all, let us enter a 2 character long string. So enter move. I have got the revert saying that input must be a single character. Okay. So let us enter the single character, but let us say single character is y, which is not in our allowed symbols. So when alright, before entering y, let me enter something which is inside. So I'm enter move and everything has run successfully. Now I'm going to enter something which is not in my allowed symbols. When I click on this enter move, now look at what I have got. Yes, I have got even the description of my error in this terminal, that invalid character, only allowed symbols allowed but sent input character, and these are the parameters, input character, value y, and then I have the documentation part also, that send character y. This input character means send character, allowed symbols and their documentation saying set of allowed symbols. So I hope with this the custom error part is clear. Continuing in the documentation, we need not bother about their example, but just one thing to see from their example is that they have used at one place revert with a string, and what they are saying that this if condition checking, that whether amount is greater than something, if it is, then not enough ether provided. Alternatively, what they are saying, that we could have done, instead of this require statement, instead of this if revert, we could have replaced it with the equivalent statement of this require form, where they are checking whether this is less than equal to, and if the negation of this condition is true, which is negation is simply this only, then revert with this message. So I just wanted to show you that these both are equivalent. The two ways, if not condition, revert, and require condition, are equivalent as long as the arguments to revert and require do not have side effects. For example, if they are just string. Next, the require function is evaluated just as any other function. This means that all arguments are evaluated before the function itself is executed. In particular, require condition f, the function f is executed even if condition is true. We might think that if this condition is false, then we will revert with whatever this thing is returning. But here is the catch: even if this condition is true, even then this function will be executed. So be careful if this function has some side effects. For instance, this function might modify the state variable and so on. Next is a bit of a technical detail. The provided string is ABI encoded as if we were just calling this function error string. In the above example, revert with this string returns the following hexadecimal as error data, just like how we will do the function selector. So the first 4 bytes, which is the 8 hexadecimal characters, and so on. The provided message can be retrieved by the caller using try catch as shown below, as what we will see now. So let us now read about try catch. A failure in an external call can be caught using try catch statement. Now when we use the revert, require, etc., in case of an exception, you can think of it that the current EVM context is taken away. So that is why we have this external call. You can use the revert, etc., inside your internal functions too, but then you cannot catch them by the caller. A caller, if it is calling the internal function and the internal function reverts, then though that whole EVM context is taken away. So you cannot catch that by the caller in that case. But if the caller of the caller was some other contracts function, was some external function, then you can catch it. So The try keyword has to be followed by an expression representing an external function call or a contract creation, that is this new contract name, whatever. Errors inside the expression are not caught. For example, if it is complex expression that also involves internal function calls, only a revert happening inside the external call itself. So what they mean is simply that in case you have an error inside this expression itself before doing this external function call, if inside the expression itself you are having the error, then it is not caught. So only a revert happening inside the external call itself. The returns part, which is optional, that follows, declares return variables matching the types returned by the external call. In case there was no error, these variables are assigned and the contract's execution continues inside the first success block. If the end of the success block is reached, execution continues after the catch blocks. So if we look at the example which they have provided, we have this interface who basically they have declared this interface to call the external contracts get data function, just like how I told you at the very beginning about the different ways to call functions of the other contracts. So data feed they have declared this variable uint error count. Then they have this rate function which takes the address of the token and returns a value and a bool. Permanently disable the mechanism if there are more than 10 errors. So we want the error count to be less than 10 here. Then they try to feed dot get data using this function, and this takes the address of the token. So we passed in the token and this function returns the uint value. So this v is for that value. In case the function executed properly, I mean there was no exception, then return v comma true, that it is indeed true. But for the other cases they are sending false because the success condition is not true. Next we have different matches for the catch. One of these block will be executed depending on the match. If what was returned was of this form, error string, and the reason they have not put that they haven't named that variable because they do not intend to use it. In case it was of this form, panic form, else if it was not of these two forms but anything general, for anything general we use this bytes thing. Let us also read their description so that it becomes more clear. Solidity supports different kinds of catch blocks depending on the type of error. Catch error strings memory reason. This catch clause is executed if the error was caused by revert this form or require this form. Basically that error parenthesis string form it should have, or an internal error that causes such an exception. Catch panic uint error code. If the error was caused by a panic, that is by failing a session, what all reasons that we have seen, division by zero, invalid error access, arithmetic overflow and others, this catch clause will be run. Catch bytes memory low level data. This clause is executed if the error signature does not match any other clause, if there was an error while decoding the error message, or if no error data was provided with the exception. The declared variable provides access to the low level error data in that case. So even if no error data was provided or there was an error while decoding that error message, so in that case also this clause will be matched. And lastly we have catch this. If you are not interested in the error data, you just want to catch it, even as the only catch clause instead of the previous clause. So instead of having all these catch error, catch panic, catch bytes memory, I can simply have this catch without having anything in parentheses if I am not interested in the error data. So in order to catch all error cases, you have to have at least the clause this one or the clause catch bytes memory low level data in case you want to catch all error cases. The variables declared in the returns and the catch clause are only in scope in the block that follows. So yeah, this v is only alive for this block. If they didn't put this reason inside a comment, then this reason will be alive only for this block. So I hope that part is clear. Next, we have these 3 error nodes. So let us read them one by one. The reason behind a failed call can be manifold. Do not assume that the error message is coming directly from the called contract. It could be coming from further down on the chain. A called contract might have called some another contract, and that might have raised an exception. The error might have happened deeper down in the call chain, and the called contract just forwarded it. Also, it could be due to an out of gas situation and not a deliberate error condition. I mean, there was not the error raised by the program as such, but maybe the gas out. We were out of gas. The caller always retain at least 1 by 64th of the gas in a call, as we told that at most it can forward is 63 by 64th of its. And thus, even if the called contract goes out of gas, the caller still have some gas left to do some of the operations like these. Next, note, if execution reaches a cache block, then the state changing effects of the external call, right, external, have been reverted. If execution reaches the success block, the effects were not reverted. If the effects have been reverted, then execution either continues in a cache block or the execution of the try catch statement itself reverts, for example due to decoding failures as noted above, or due to not providing a low level catch clause. So read this part carefully. For example, due to decoding failures as noted above, as in this note which I will read shortly, or due to not providing a low level catch clause. For instance, the error might have not been of the form this and this, but I did not provided any catch clause, right? So what is this the thing which they told about noted above? So let's read that. If an error happens during the decoding of the return data inside the try catch statement, this causes an exception in the current executing contract, and because of that it is not caught in the catch clause. If there is an error during decoding of catch error string memory reason, this, I mean, you have seen that catch clause, and there is a low level catch clause, this error is caught there. So in case there was an error decoding this return data, then since here we have this catch clause, it will be executed. But in case there was an error in suppose decoding this return data, then this try catch will itself raise the exception. Yeah. I think it will be better if I show you an example. So let us see an example. Like here, I have a very simple example. This contract try error decode, it has two functions. One is this a function, which is just returning an unsigned integer 88. The other function which I have is this one. This try catch function. So it is going to, okay, now there is a slight trick which I have done. I wanted to call this a function externally, so this dot a I would have used, and I'm putting string returns, returns a string, but we know that it returns an unsigned integer. It does not return string memory, but the compiler will not let me do that because the compiler has seen that it is this function a is returning integer. So what I'm doing, I'm using this interface thing, where the interface suggests that we are returning string memory. So I'm fooling the compiler by first typecasting the address to this contract type full compiler. So then I'm calling this a function because this expects to return memory, but this actually returns 88. So there will be an error decoding the return data, and this catch part will not get executed. So if I were to deploy it and run it, so first let's run this a function, and it is running perfectly. We have got 88. Now I'm using this try catch, and you see we have got an exception. So this is what they mean, that if there is an error in decoding these return data inside this try catch clause. And with this, we have covered this section on control structures.